Welcome everybody to lesson 5. And so we have officially peaked and everything is downhill from here as of halfway through the last lesson. We started with computer vision because it's the most mature, kind of out-of-the-box, ready-to-use deep learning application. It's something which, if you're not using deep learning, you won't be getting good results. So the difference, hopefully between not doing lesson 1 versus doing lesson 1, you've gained a new capability you didn't have before, and you kind of get to see a lot of the kind of trade craft of training an effective neural net. And so then we moved into NLP because text is kind of another one which you really kind of can't do really well without deep learning, generally speaking. And it's just got to the point where it's pretty, works pretty well now. In fact, the New York Times just featured an article about the latest advances in deep learning for text yesterday, and talked quite a lot about the work that we've done in that area, along with OpenAI and Google and the Allen Institute of Artificial Intelligence. And then we've kind of finished our application journey with tabular and collaborative filtering, partly because tabular and collaborative filtering are things that you can still do pretty well without deep learning, so it's not such a big step. It's not a kind of whole new thing that you could do that you couldn't used to do. And also because we're going to try to get to a point where we understand pretty much every line of code and the implementations of these things, and the implementations of those things, it's much less intricate than vision and NLP. So as we come down this other side of the journey, which is like all the stuff we've just done, how does it actually work? By starting where we just ended, which is starting with collaborative filtering and then tabular data, we're going to be able to see what all those lines of code do by the end of today's lesson. That's our goal. So, particularly this lesson, you should not expect to come away knowing how to solve, how to do applications you couldn't do before, but instead you should have a better understanding of how we've actually been solving the applications we've seen so far. Particularly, we're going to understand a lot more about regularization, which is how we go about managing over versus underfitting. And so hopefully you can use some of the tools from this lesson to go back to your previous projects and get a little bit more performance, or handle models where previously maybe you felt like your data was not enough, or maybe you were underfitting, and so forth. And it's also going to lay the groundwork for understanding convolutional neural networks and recurrent neural networks that we'll do deep dives into in the next 2 lessons. And as we do that, we're also going to look at some new applications, some new vision and NLP applications. Let's start where we left off last week. Do you remember this picture? So this picture, we were looking at kind of what does a deep neural net look like? And we had various layers. And the first thing we pointed out is that there are only and exactly 2 types of layer. There are layers that contain parameters, and there are layers that contain activations. Parameters are the things that your model learns. They're the things that you use gradient descent to go parameters minus equals learning rate times parameters.grad. Right? That's our basic, that's what we do. Okay? And those parameters are used by multiplying them by input activations, doing a matrix product. So the yellow things are our weight matrices, or weight tensors more generally, but that's close enough. So we take some input activations or some layer activations and we multiply it by a weight matrix to get a bunch of activations. So activations are numbers, but these are numbers that are calculated. Okay, so I find in our study group I keep getting questions about where does that number come from, and I always answer it in the same way. You tell me, is it a parameter or is it an activation? Because it's one of those two things. Okay, that's where numbers come from. I guess inputs are kind of a special activation, so they're not calculated, they're just there, so maybe that's a special case. So maybe it's an input or a parameter or an activation. Activations don't only come out of matrix multiplications, they also come out of activation functions. And the most important thing to remember about an activation function is that it's an element-wise function. So it's a function that is applied to each element of the input activations in turn and creates one activation for each input element. So if it starts with a 20 long vector, it creates a 20 long vector by looking at each one of those in turn, doing one thing to it and spitting out the answer. Okay, so an element-wise function. ReLU is the main one we've looked at, and honestly, it doesn't too much matter which you pick. So we don't spend much time talking about activation functions because if you just use ReLU, you'll get a pretty good answer pretty much all the time. And so then we learnt that this combination of matrix multiplications followed by ReLUs stacked together has this amazing mathematical property called the universal approximation theorem, which is if you have big enough weight matrices and enough of them, it can solve any arbitrarily complex mathematical function to any arbitrarily high level of accuracy. Assuming that you can train the parameters, both in terms of time and data availability and so forth. Okay? So that's the bit which I find particularly more advanced computer scientists get really confused about, is they're always asking like, where's the next bit? What's the trick? How does it work? But that's it. You know, you just do those things and you pass back the gradients and you update the weights with the learning rate and that's it. So that piece where we take the loss function between the actual targets and the output of the final layer, so the final activations, we calculate the gradients with respect to all of these yellow things, and then we update those yellow things by learning rate, by subtracting learning rate times the gradient. That process of calculating those gradients and then subtracting like that is called back propagation. Okay, so when you hear the term, well, that's just very small font. So when you hear the term back propagation, it's one of these terms that neural networking folks love to use. It sounds very impressive, okay, but you can replace it with your head with weights minus equals weights.grad times learning rate, or parameters, I should say, rather than weights, a bit more general. Okay, so that's what we covered last week. And then I mentioned last week that we're going to cover a couple more things. I'm going to come back to these ones, cross entropy and softmax, later today. Let's talk about fine-tuning now. So what happens when we take a ResNet34 and we do transfer learning? What's actually going on? So the first thing to notice is the ResNet34 that we grab from ImageNet has a very specific weight matrix at the end. It's a weight matrix that has 1,000 columns. Why is that? Because ImageNet, the problem they ask you to solve in the ImageNet competition is please figure out which one of these 1,000 image categories this picture is. So that's why they need 1,000 things here, because in ImageNet, this target vector is length 1,000. It's you've got to pick the probability that it's which one of those 1,000 things. So there's a couple of reasons this weight matrix is no good to you when you're doing transfer learning. The first is that you probably don't have 1,000 categories. You know, I was trying to do teddy bears, black bears, or brown bears, so I don't want 1,000 categories. And the second is even if I did have exactly 1,000 categories, they're not the same 1,000 categories that are in ImageNet. So basically, this whole weight matrix is a waste of time for me. So what do? We throw it away. So when you go create CNN in FastAI, it deletes that. And what does it do instead? Instead, it puts in 2 new weight matrices in there for you, with a ReLU in between. And so there are some defaults as to what size this first one is, but the second one, the size there is as big as you need it to be. So in your data bunch, which you pass to your learner, from that we know how many activations you need. If you're doing classification, it's however many classes you have. If you're doing regression, it's however many numbers you're trying to predict in the regression problem. And so remember that if your data bunch is called data, that'll be called data.c. So we'll add for you this weight matrix of size data.c by however much was in the previous layer. Okay, so now we need to train those because initially these weight matrices are full of random numbers. Okay, because new weight matrices are always full of random numbers if they're new, and these ones are new. We've grabbed them and thrown them in there. So we need to train them. But the other layers are not new. The other layers are good at something, right? And what are they good at? Well, let's remember that Zeiler and Fergus paper. Here are examples of some visualization of some filters, some weight matrices in the first layer, and some examples of some things that they found. Right? So the first layer had one part of the weight matrix was good at finding diagonal edges in this direction. And then in layer 2, one of the filters was good at finding corners in the top left. And then in layer 3, one of the filters was good at finding repeating patterns. Another one was good at finding round orange things. Another one was good at finding kind of like furry or floral textures. So as we go up, they're becoming more sophisticated, but also more specific, right? So like layer 4, I think, was finding like eyeballs, for instance. Now, if you're wanting to transfer learn to something for histopathology slides, there's probably going to be no eyeballs in that, right? So the later layers are no good for you. But there'll certainly be some repeating patterns, and there'll certainly be some diagonal edges, right? So the earlier you go in the model, the more likely it is that you want those weights to stay as they are. Well, to start with, we definitely need to train these new weights because they're random. So let's not bother training any of the other weights at all to start with. So what we do is we basically say, let's freeze. Let's freeze all of those other layers. So what does that mean? All it means is that we're asking FastAI and PyTorch that when we train, however many epochs we do, when we call fit, don't backpropagate the weights. Don't backpropagate the gradients back into those layers. In other words, when you go parameters equals parameters minus learning rate times gradient, only do it for the new layers, don't bother doing it for the other layers. That's what freezing means, okay? Just means don't update those parameters. So it'll be a little bit faster as well, because there's a few less calculations to do. It'll take up a little bit less memory because there's a few less gradients that we have to store. But most importantly, it's not going to change weights that are already better than nothing. They're better than random, at the very least. So that's what happens when you call freeze. It doesn't freeze the whole thing. It freezes everything except the randomly generated added layers that we put on for you. So then what happens next? Okay, after a while, we say, okay, this is looking pretty good. We probably should train the rest of the network now. So we unfreeze, right? And so now we're going to train the whole thing, but we still have a pretty good sense that these new layers we added to the end probably need more training, and these ones right at the start that might just be like diagonal edges, probably don't need much training at all. So we split our model into a few sections, right? And we say, let's give different parts of the model different learning rates. So this part of the model, we might give a learning rate of 1e neg 5. And this part of the model, we might give a learning rate of 1e neg 3, say. And so what's going to happen now is that we can keep training the entire network, but because the learning rate for the early layers is smaller, it's going to move them around less, because we think they're already pretty good. And also, like, if it's already pretty good to the optimal value, if you used a higher learning rate, it could kick it out, right? It could actually make it worse, which we really don't want to happen. Okay, so this process is called using discriminative learning rates. You won't find much online about it, because I think we were kind of the first to use it for this purpose, or at least talk about it extensively. Maybe probably other people used it without writing it down. So most of the stuff you'll find about this will be fast AI students. But it's starting to get more well known slowly now. But it's a really, really important concept. For transfer learning, without using this, you just can't get nearly as good results. So how do we do discriminative learning rates in fast AI? Anywhere you can put a learning rate in fast AI, such as with the fit function, the first thing you put in is the number of epochs, and then the second thing you put in is learning rate. Same if you use fit one cycle. The learning rate, you can put a number of things there. You can put a single number, like 1e neg 3. You can write a slice, so you can write slice, for example, 1e neg 3, with a single number, or you can write slice with two numbers. What do each of those mean? In the first case, just using a single number means every layer gets the same learning rate. So you're not using discriminative learning rates. If you pass a single number to slice, it means the final layers get a learning rate of whatever you wrote down, 1e neg 3. And then all the other layers get the same learning rate, which is that divided by 3. Okay, so all of the other layers will be 1e neg 3 divided by 3. The last layers will be 1e neg 3. Then in the last case, the final layers, these randomly added layers, will still be again 1e neg 3. The first layers will get 1e neg 5, and the other layers will get learning rates that are equally spread between those two, so multiplicatively equal, right? So if there were 3 layers, there would be 1e neg 5, 1e neg 4, 1e neg 3. So equal multiples each time. One slight tweak, to make things a little bit simpler to manage, we don't actually give a different learning rate to every layer. We give a different learning rate to every layer group, which is just we decide to put the groups together for you. And so specifically what we do is the randomly added extra layers, we call those one layer group. This is by default, you can modify it. And then all the rest, we split in half into 2 layer groups. So by default, at least with a CNN, you'll get 3 layer groups. And so if you say slice 1e neg 5, 1e neg 3, you will get 1e neg 5 learning rate for the first layer group, 1e neg 4 for the second, 1e neg 3 for the third. So now if you go back and look at the way that we're training, hopefully you'll see that this makes a lot of sense. This divided by 3 thing is a little weird, and we won't talk about why that is until part 2 of the course. It's a specific quirk around batch normalization. So we can discuss that in the advanced topic if anybody's interested. All right, so that is fine-tuning. So hopefully that makes that a little bit less mysterious. So we were looking at collaborative filtering last week. And in the collaborative filtering example, we called fit1 cycle and we passed in just a single number. And that makes sense because in collaborative filtering, we only have one layer. There's a few different pieces in it, but there isn't, you know, a matrix multiply followed by an activation function followed by another matrix multiply. I'm going to introduce another piece of jargon here. They're not always exactly matrix multiplications. There's something very similar. They're linear functions that we add together. But the more general term for these things that are a bit more general than matrix multiplications is affine functions. Okay, so if you hear me say the word affine function, you can replace it in your head with matrix multiplication. But as we'll see when we do convolutions, convolutions are matrix multiplications where some of the weights are tied. And so it would be slightly more accurate to call them affine functions. And I like to introduce a little bit more jargon each lesson so that when you read books or papers or watch other courses or read documentation, there will be more of the words you'll recognize. Okay? So when you see affine function, it just means a linear function, right? And it means something very, very close to matrix multiplication. A matrix multiplication is the most common kind of affine function, at least in deep learning. Specifically for collaborative filtering, the model we were using was this one. It was where we had a bunch of numbers here and a bunch of numbers here, and we took the dot product of them. And given that one here is a row and one is a column, we can actually, that's the same as a matrix product. So M mult in Excel multiplies matrices, so here is the matrix product of those two. And so I started this training last week by using Solver in Excel, and we never actually went back to see how it went, so let's go and have a look now. So the average sum of squared error got down to 0.39. So we're trying to predict something on a scale of 0.5 to 5. So on average, we're being wrong by about 0.4. That's pretty good. And you can kind of see it's pretty good if you look at like 351 is what it meant to be, 3.25, 5.1, 0.98. It's pretty close, right? So you get the general idea. And then I started to talk about this idea of embedding matrices. And so in order to understand that, let's put this worksheet aside and look at another worksheet. So here's another worksheet. And what I've done here is I have copied over those two weight matrices from the previous worksheet. Right? Here's the one for users, and here's the one for movies. And the movies one, I've transposed it, so it's now got exactly the same dimensions as the users one. Okay? So here are two weight matrices. Initially they were random. We can train them with gradient descent. In the original data, the user IDs and movie IDs were numbers like these. Okay? To make life more convenient, I've converted them to numbers from 1 to 15. Okay? So in these columns, I've got, for every rating, I've got user ID, movie ID, rating, using these mapped numbers so that they're contiguous starting at 1. Okay. Now I'm going to replace user ID number 1 with this vector. The vector contains a 1 followed by 14 zeros. And then user number 2, I'm going to replace with a vector of 0, and then 1, and then 13 zeros, and so forth. So movie ID 14, all these are movie ID 14, I've also replaced with another vector, which is 13 zeros, and then a 1, and then a 0. Okay. So these are called one-hot encodings, by the way. So this is not part of a neural net. This is just like some input pre-processing where I'm literally making this my new inputs. So this is my new inputs for my movies. This is my new inputs for my users. Okay, so these are the inputs to a neural net. So what I'm going to do now is I'm going to take this input matrix and I'm going to do a matrix multiply by this weight matrix. And that'll work because this has 15 rows and this has 15 columns. So I can multiply those two matrices together because they match. And you can do matrix multiplication in Excel using the mmult function. Just be careful if you're using Excel, because this is a function that returns multiple numbers. You can't just hit enter when you finish with it, you have to hit Control-Shift-Enter. Control-Shift-Enter means this is an array function, it's something that returns multiple values. So here is the matrix product of this input matrix of inputs and this parameter matrix or weight matrix. So that's just a normal neural network layer. Okay, it's just a regular matrix multiply. And so we can do the same thing for movies. And so here's the matrix multiply for movies. Well, here's the thing. This input we claim is this kind of one-hot encoded version of user ID number 1. And these activations are the activations for user ID number 1. Why is that? Because if you think about it, a matrix multiplication between a one-hot encoded vector and some matrix is actually going to find the nth row of that matrix when the 1 is in position n. Does that make sense? So what we've done here is we've actually got a matrix multiply that is creating these output activations, right? But it's doing it in a very interesting way, which is it's effectively finding a particular row in the input matrix. So having done that, we can then multiply those two sets together, just a dot product, and we can then find the loss squared, and then we can find the average loss, and lo and behold, that number, 0.39, is the same as this number, because they're doing the same thing. So this one was kind of finding this particular user's embedding vector. This one is just doing a matrix multiply, and therefore we know they are mathematically identical. So let's lay that out again. So here's our final version. This is the same weight matrices again, exactly the same, I've copied them over. And here's those user IDs and movie IDs again, right? But this time I've laid them out just in a normal kind of tabular form, just like you would expect to see in the input to your model. And this time, I've got exactly the same set of activations here that I had here. But in this case, I've calculated these activations using Excel's offset function, which is an array lookup, right? It says, find the first row of this. So this is doing it as an array lookup. So this version is identical to this version, but obviously it's much less memory intensive and much faster, because I don't actually create the one-hot encoded matrix, and I don't actually do a matrix multiply, because that matrix multiply is nearly all multiplying by 0, which is a total waste of time. So in other words, multiplying by a one-hot encoded matrix is identical to doing an array lookup. Therefore, we should always do the array lookup version. And therefore, we have a specific way of saying, I want to do a matrix multiplication by a one-hot encoded matrix without ever actually creating it. I'm just instead going to pass in a bunch of ints and pretend they're one-hot encoded. And that is called an embedding, right? So you might have heard this word embedding all over the place as if it's some magic advanced mathy thing. But embedding means look something up in an array. Okay? But it's interesting to note that looking something up in an array is mathematically identical to doing a matrix product by a one-hot encoded matrix, and therefore an embedding fits very nicely in our standard model of how neural networks work. So now, suddenly, it's as if we have another whole kind of layer. It's a kind of layer where we get to look things up in an array. But we actually didn't do anything special. Right? We just added this computational shortcut, this thing called an embedding, which is simply a fast and memory efficient way of multiplying by a one-hot encoded matrix. Okay? So this is really important because when you hear people say embedding, you need to replace it in your head with an array lookup, which we know is mathematically identical to a matrix multiplied by a one-hot encoded matrix. Here's the thing though, it has kind of interesting semantics, right? Because when you do multiply something by a one-hot encoded matrix, you get this nice feature where the rows of your weight matrix, the values only appear for row number 1, for example, where you get user ID number 1 in your inputs, right? So in other words, you kind of end up with this weight matrix where certain rows of weights correspond to certain values of your input. And that's pretty interesting. It's particularly interesting here because going back to a kind of most convenient way to look at this, because the only way that we can calculate an output activation is by doing a dot product of these two input vectors, that means that they kind of have to correspond with each other, right? Like there has to be some way of saying if this number for a user is high and this number for a movie is high, then the user will like the movie. So the only way that can possibly make sense is if these numbers represent features of personal taste and corresponding features of movies. For example, the movie has John Travolta in it, and user ID likes John Travolta, then you'll like this movie. Okay? So like, we're not actually deciding the rows mean anything. We're not doing anything to make the rows mean anything. But the only way that this gradient descent could possibly come up with a good answer is if it figures out what the aspects of movie taste are and the corresponding features of movies are. So those underlying kind of features that appear are called latent factors or latent features. They're these hidden things that were there all along, and once we train this neural net, they suddenly appear. Right? Now here's the problem. No one's going to like Battlefield Earth, right? It's not a good movie, even though it has John Travolta in it. So how are we going to deal with that, right? Because there's this feature called I like John Travolta movies, and this feature called this movie has John Travolta, and so this is now like, you're going to like the movie, but we need to have some way to say, unless it's Battlefield Earth, or you're a Scientologist, either one, right? So how do we do that? We need to add in bias, right? So here is the same thing again. Same weight matrix, sorry, not the same weight matrix, it's the same construct, right? Same shape of everything. But this time we've got an extra row. So now, this is not just the matrix product of that and that, but I'm also adding on this number and this number, which means now each movie can have an overall, this is a great movie versus this isn't a great movie. And every user can have an overall, this user rates movies highly or this user doesn't rate movies highly. So that's called the bias. So this is hopefully going to look very familiar, right? This is the same usual linear model concept or linear layer concept from a neural net, that you have a matrix product and a bias. And do you remember from lesson 2, the lesson 2 SGD notebook, you never actually need a bias. You could always just add a column of 1s to your input data, and then that gives you bias for free. But that's pretty inefficient, right? So in practice, all neural networks library explicitly have a concept of bias. We don't actually add the column of ones. So what does that do? Well, just before I came in today, I ran tools solver, or now it's data solver on this as well. And we can check the RMSE. And so the root mean squared here is 0.32 versus the version without bias was 0.39. Okay, so you can see that this slightly better model gives us a better result. And it's better because it's giving both more flexibility, right? And it's also just makes sense semantically that you need to be able to say, it's not whether I like the movie is not just about the combination of what actors it has and whether it's dialogue driven and how much action is in it, but just, is it a good movie? Okay, or am I somebody who rates movies highly? Okay, so there's all the pieces of this collaborative filtering model. How are we going, Francisco? Any questions? We have 3 questions. Okay. Okay. So our first question then is, when we load a pre-trained model, can we explore the activation grids to see what they might be good at recognizing? Yes, you can. And we will learn how to, should be in the next lesson. Can we have an explanation of what the first argument in fit one cycle actually represents? Is it equivalent to an epoch? Yes. The first argument to fit one cycle, or fit, is number of epochs. It's, in other words, an epoch is looking at every input once. So if you do 10 epochs, you're looking at every input 10 times. And so there's a chance you might start overfitting if you've got lots and lots of parameters and a high learning rate. If you only do 1 epoch, it's impossible to overfit. So that's why it's kind of useful to remember how many epochs you're doing. Can we have an explanation? No, did that one. What is an affine function? An affine function is a linear function. I don't know if we need much more detail than that. If you're multiplying things together and adding them up, it's an affine function. I'm not going to bother with the exact mathematical definition, partly because I'm a terrible mathematician and partly because it doesn't matter. But if you just remember that you're multiplying things together and then adding them up, that's the most important thing. It's linear. Okay? And therefore, if you put an affine function on top of an affine function, that's just another affine function. You haven't won anything at all. That's a total waste of time, right? So you need to sandwich it with any kind of nonlinearity, pretty much works, right? Including replacing the negatives with zeros, which we call ReLU. Okay? So if you do affine, ReLU, affine, ReLU, affine, ReLU, you have a deep neural network. Okay. So, so let's go back to the collaborative filtering notebook. And this time we're going to grab the whole movie lens 100K data set. There's also a 20 million data set, by the way. So really great project available, made by this group called Group Lens. They actually update the movie lens data sets on a regular basis, but they helpfully provide the original one. And we're going to use the original one because that means that we can compare to baselines. Because everybody, basically they say, hey, if you're going to compare to baselines, make sure you all use the same data set. Here's the one you should use. Unfortunately, it means that we're going to be restricted to movies that are before 1998. So maybe you won't have seen them all, but that's the price we pay. You can replace this with ML latest when you download it and use it if you want to play around with movies that are up to date. Okay, the original movie lens data set, the more recent ones are in a CSV file that's super convenient to use. The original one is a slightly messy. First of all, they don't use commas for delimiters, they use tabs. So in pandas, you can just say what's the delimiter when you load it in. The second is they don't add a header row so that you know what column is what. So you have to tell pandas there's no header row. And then since there's no header row, you have to tell pandas what are the names of the columns. Other than that, that's all we need. Okay, so we can then have a look at head, which remember is the first few rows, and there is our user ratings, user movie rating. And let's make it more fun. Let's see what the movies actually are. I'll just point something out here, which is there's this thing called encoding equals. I'm going to get rid of it. And I get this error, Unicode. I just want to point this out because you'll all see this at some point in your lives. Codec can't decode, blah, blah, blah. What this means is that this is not a Unicode file. This will be quite common when you're using data sets that are a little bit older. Back before, us folks in the West really realized that there are people that use languages other than, well, English people, languages other than English. Nowadays, we're much better at handling different languages. We use this standard called Unicode for it, and Python very helpfully uses Unicode by default. But so if you try to load an old file that's not Unicode, you actually, believe it or not, have to guess how it was coded. But since it's really likely that it was created by, some Western European or American person, they almost certainly used Latin 1. So if you just pop in encoding equals Latin 1, if you use file open in Python or pandas open or whatever, that will generally get around your problem. Again, they didn't have the names, so we had to list what the names are. This is kind of interesting. They had a separate column for every one of however many genres they had, 19 genres. And you'll see this looks one hot encoded, but it's actually not. It's actually n hot encoded. In other words, a movie can be in multiple genres. We're not going to look at genres today, but it's just interesting to point out that this is a way that sometimes people will represent something like genre. In the more recent version, they actually list the genres directly, which is much more convenient. Okay. So I find life is, so we've got 100,000 ratings. I find life is easier when you're modeling, when you actually denormalize the data. So I actually want the movie title directly in my ratings. So Pandas has a merge function to let us do that. So here's the ratings table with actual titles. So as per usual, we can create a data bunch for our application. So a Colab data bunch for the Colab application from what? From a data frame. There's our data frame. Set aside some validation data. Really, we should use the validation sets and cross-validation approach that they used if you're going to properly compare with a benchmark. So take these comparisons with a grain of salt. By default, Colab data bunch assumes that your first column is user, second column is item, third column is rating. But now we're actually going to use the title column as item, so we have to tell it what the item column name is. And then all of our data bunches support show batch, so you can just check what's in there, and there it is. Okay. So I'm going to try and get as good a result as I can. So I'm going to try and use whatever tricks I can come up with to get a good answer. Now, one of the tricks is to use the Y range. And remember, the Y range was the thing that made the final activation function a sigmoid. And specifically, last week we said, let's have a sigmoid that goes from 0 to 5. And that way it's going to ensure that it's going to help the neural network predict things that are in the right range. I actually didn't do that in my Excel version. And so you can see I've actually got some negatives, right? And there's also some things bigger than 5. So if you want to beat me in Excel, you could add the sigmoid to Excel and train this, and you'll get a slightly better answer. Now, the problem is that a sigmoid actually asymptotes at, say, whatever the maximum is. We said 5, right? Which means you can never actually predict 5. But plenty of movies have a rating of 5, so that's a problem. So actually, it's slightly better to make your Y range go from a little bit less than the minimum to a little bit more than the maximum. And the minimum of this data is 0.5, and the maximum is 5. So this range is just a little bit further. So that's one little trick to get a little bit more accuracy. The other trick I used is to add something called weight decay. and we're going to look at that next. Okay, after this section, we're going to learn about weight decay. So then, how many factors do you want? Well, what are factors? The number of factors is the width of the embedding matrix. So why don't we say embedding size? Maybe we should, but in the world of collaborative filtering, they don't use that word. They use the word factors because of this idea of latent factors. And because the standard way of doing collaborative filtering has been with something called matrix factorization. And in fact, what we just saw happens to actually be a way of doing matrix factorization. So we've actually accidentally learnt how to do matrix factorization today. So this is a term that's kind of specific to this domain, okay? But you can just remember it as the width of the embedding matrix. And so why 40? Well, this is one of these architectural decisions you have to play around with and see what works. So I tried 10, 20, 40, and 80, and I found 40 seemed to work pretty well. And it trained really quickly. So like you can chuck it in a little for loop to try a few things and see what looks best. And then for learning rates, I use the learning rate finder as usual. So 5e neg 3 seemed to work pretty well. Remember, this is just a rule of thumb, right? 5e neg 3 is a bit lower than both Sylvain's rule and my rule. So Sylvain's rule is find the bottom and go back by 10. So his rule would be more like 2e neg 2, I reckon. My rule is kind of find about the steepest section, which is about here, which again, like often it agrees with Sylvain, so that would be about 2e neg 2. I tried that, and I always like to try like 10x less and 10x more, just to check, and actually I found a bit less was helpful. So the answer to the question like, should I do blah, is always try blah and see. That's how you actually become a good practitioner. So that gave me 0.813, right? And as usual, you can save the result to save you another 33 seconds from having to do it again later. And so there's a library called librec, and they publish some benchmarks for movie lens 100K, and there's a root mean squared error section, and about 0.91 is about as good as they seem to have been able to get. 0.91 is the root mean squared error. We use the mean squared error, not the root. So we have to go 0.91 squared, which is 0.83, and we're getting 0.81. So that's cool. With this very simple model, we're doing a little bit better. Quite a lot better, actually. Although, as I said, take it with a grain of salt because we're not doing the same splits and the same cross-validation. So we're at least highly competitive with their approaches. Okay, so we're going to look at the Python code that does this in a moment. But for now, just take my word for it that we're going to see something that's just doing this, right? Looking things up in an array and then multiplying them together, adding them up, and doing the mean squared error loss function. So given that, and given that we noticed that the only way that that can do anything interesting is by trying to kind of find these latent factors, it makes sense to look and see what they found, right? Particularly since, as well as finding latent factors, we also now have a specific bias number for every user and every movie, right? Now, you could just say, what's the average rating for each movie? But there's a few issues with that. In particular, this is something you see a lot with like anime. People who like anime just love anime, right? And so they watch lots of anime and then they just rate all the anime highly. And so very often on kind of charts of movies, you'll see a lot of anime at the top, right? Particularly if it's like, 100 long series of anime, you'll find, every single item of that series in the top 1,000 movie list or something. So how do we deal with that? Well, the nice thing is that instead, if we look at the movie bias, right, the movie bias says kind of, once we've included the user bias, right, which for an anime lover might be a very high number because they're just rating a lot of movies highly. And once we account for the specifics of this kind of movie, which again might be people love anime, right? What's left over is something specific to that movie itself. So it's kind of interesting to look at movie bias numbers as a way of saying, what are the best movies, or what do people really like as movies, even if those people don't rate movies very highly, or even if that movie doesn't have the kind of features that people tend to have rate highly. So you get this kind of nice, it's funny to say this, by using the bias, we get an unbiased kind of movie score. So how do we do that? Well, to make it interesting, particularly because this data set only goes to 1998, let's only look at movies that plenty of people watch, right? So we'll use pandas to grab our rating movie table, group it by title, and then count the number of ratings. I'm not measuring how high they're rating, just how many ratings do they have, okay? And so the top 1,000 are the movies that have been rated the most, and so they're hopefully movies that we might have seen. Okay, that's the only reason I'm doing this. And so I've called this top movies, by which I mean not good movies, just movies we're likely to have seen. So not surprisingly, Star Wars is the one that at that point the most people had put a rating to. Independence Day. There you go. So we can then take our learner that we trained and ask it for the bias of the items listed here. Okay, so is item equals true, you would pass true to say I want the items, or false to say I want the users. So this is kind of like a pretty common piece of nomenclature for collaborative filtering. These IDs tend to be called users. These IDs tend to be called items. Even if your problem has got nothing to do with users and items at all, we just use these names for convenience. Okay, so they're just words. So in our case, we want the items. This is the list of items we want. We want the bias. So this is specific to collaborative filtering, and so that's going to give us back 1,000 numbers, right? Because we asked for this has 1,000 movies in it. So we can now take and just for comparison, let's also group the titles by the mean rating. So then we can zip through, so going through together, each of the movies along with the bias and grab their rating and the bias and the movie, and then we can sort them all by the zero index thing, which is the bias. So here are the lowest numbers. So I can say, Mortal Kombat Annihilation, not a great movie. Lawnmower Man 2, not a great movie. I haven't seen Children of the Corn, but we did have a long discussion at SF Study Group today, and people who have seen it agree, not a great movie. And you can kind of see, some of them actually have pretty decent ratings, even though, relative to, right? So this one's actually got a much higher rating than the next one, right? But, that's kind of saying, well, the kind of actors that were in this and the kind of movie that this was and the kind of people who like it, who watch it, you would expect it to be higher. And then here's the sort by reverse, okay? Schindler's List, Titanic, Shawshank Redemption, seems reasonable. And again, you can kind of look for ones where, the rating, isn't that high, but it's still very high here. So that's kind of at least in 1998, people weren't that into Leonardo DiCaprio, or, people aren't that into dialogue-driven movies, or people aren't that into romances or whatever, but still people liked it more than you would have expected. So it's interesting to kind of interpret our models in this way. We can go a bit further and grab not just the biases, but the weights. So that is these things. And again, we're going to grab the weights for the items for our top movies. And that is 1,000 by 40 because we asked for 40 factors. So rather than having a width of 5, we have a width of 40. Often, really there isn't really conceptually 40 latent factors involved in taste, and so trying to look at the 40 can be, not that intuitive. So what we want to do is we want to squish those 40 down to just 3. And there's something that we're not going to look into called PCA, stands for Principal Components Analysis. So this is movie W is a torch tensor, and FastAI adds the PCA method to torch tensors. And what PCA does, Principal Components Analysis, is it's a simple linear transformation that takes an input matrix and tries to find a smaller number of columns that kind of cover a lot of the space of that original matrix. If that sounds interesting, which it totally is, you should check out our course Computational Linear Algebra, which Rachel teaches, where we will show you how to calculate PCA from scratch and why you'd want to do it and lots of stuff like that. It is absolutely not a prerequisite for anything in this course, but it's definitely worth knowing that taking layers of neural nets and chucking them through PCA is very often a good idea. Because very often you have like way more activations than you want in a layer, and there's all kinds of reasons you might want to play with it. For example, Francisco, who's sitting next to me today, has been working on something to do image similarity, right? And for image similarity, a nice way to do that is to compare activations from a model, but often those activations will be huge, and therefore your thing could be really slow and unwieldy. So people often, for something like image similarity, will chuck it through a PCA first, and that's kind of cool. In our case, we're just going to do it so that we take our 40 components down to 3 components, so hopefully they'll be easier for us to interpret. So we can grab each of those 3 factors. We'll call them factor 0, 1, and 2. Let's grab that movie components and then sort. And now the thing is, we have no idea what this is going to mean, but we're pretty sure it's going to be some aspect of taste and movie feature. So if we print it out, the top and the bottom, we can see that the highest ranked things on this feature, you would kind of describe them as, connoisseurs movies, I guess. Like Chinatown, really classic Jack Nicholson movie. Everybody knows Casablanca. And even like Wrong Trousers is like this kind of classic claymation movie and so forth, right? So yeah, this is definitely measuring like things that are very high on the kind of connoisseur level, whereas maybe Home Alone 3, not such a favorite with connoisseurs, perhaps. Which is not to say that there aren't people who don't like it, right? But probably not the same kind of people that would appreciate Secrets and Lies. Okay? So you can kind of see this idea that this has found some feature of movies and a corresponding feature of the kind of things people like. So let's look at another feature. So here's factor number 1. So this seems to have found like, okay, these are just big hits that you could watch with the family, These are definitely not that, Trainspotting, very gritty kind of, thing. So again, it's kind of found this interesting feature of taste, and we could even like draw them on a graph, right? I've just colored them randomly to make them easier to see, and you can kind of see like, and this is just the top 50 most popular movies by rating, by how many times they've been rated. And so kind of on this one factor, you got the Terminators really high up here, and the kind of English Patient and Schindler's List at the other end, and then kind of here's your Godfather and Monty Python over here, and Independence Day and Liar Liar over there. So you get the idea. So it's kind of fun. It would be interesting to see if you can come up with some stuff at work or other kind of data sets where you could try to pull out some features and play with them. So how does that work? Any questions? One. Okay. The question is, why am I sometimes getting negative loss when training? You shouldn't be. So you're doing something wrong. So ask on, show us your, I mean, particularly since people are upvoting this, I guess other people have seen it too. So put it on the forum. I mean, they said they're doing negative log likelihood. Yeah, so we're going to be learning about cross entropy and negative log likelihood after the break today. They are loss functions that have very specific expectations about what your input looks like, and if your input doesn't look like that, then they're going to give very weird answers. So probably you pressed the wrong buttons, so don't do that. Okay, so we said collab learner. And so here is the collab learner function. The collab learner function, as per usual, takes a data bunch. And normally learners also take something where you ask for a particular architectural details. In this case, there's only one thing which does that, which is basically, do you want to use a multi-layer neural net, or do you want to use a classic collaborative filtering? And we're only going to look at the classic collaborative filtering today, or maybe we'll briefly look at the other one too. We'll see. And so what actually happens here? Well, basically, we're going to we create an embedding dot bias model, and then we pass back a learner which has our data and that model. So obviously all the interesting stuff is happening here in embedding.bias. So let's take a look at that. I clearly pressed the wrong button. Embedding.bias. There we go. Okay, so here's our embedding.bias model. It is a nn.module. So in PyTorch, to remind you, all PyTorch layers and models are nn.modules. They are things that, once you create them, look exactly like a function. You call them with parentheses and you pass them arguments. But they're not functions. They don't even have, normally in Python, to make something look like a function, you have to give it a method called dunder call. Remember, that means underscore, underscore, call, underscore, underscore, which doesn't exist here. And the reason is that PyTorch actually expects you to have something called forward. And that's what PyTorch will call for you when you call it like a function. So when this model is being trained to get the predictions, it's actually going to call forward for us. So this is where we do the calculations, right? To calculate our predictions. So this is where you can see we grab our, why is this users rather than user? Well, that's because everything's done a mini batch at a time, right? So it's kind of, when I read the forward in a PyTorch module, I tend to ignore in my head the fact that there's a mini batch, and I pretend there's just one. Because PyTorch automatically handles all of the stuff about doing it to everything in the mini batch for you, right? So let's pretend there's just one user, right? So grab that user and what is this? Self.u_weight. Self.u_weight is an embedding. We create an embedding for each of users by factors, items by factors, users by one, items by one. Now that makes sense, right? So users by one is here. That's the user's bias, right? And then users by factor is here. So users by factors is the first tuple, so that's going to go in u_weight. And users, one is the third, so that's going to go in u_bias. So remember, when PyTorch creates our nn.module, it calls dunder init. And so this is where we have to create our weight matrices. right? And we don't normally create the actual weight matrix tensors. We normally use PyTorch's convenience functions to do that for us. And we're going to see some of that after the break. So for now, just recognize that this function is going to create an embedding matrix for us. It's going to be a PyTorch nn.module as well. So therefore, to actually pass stuff into that embedding matrix and get activations out, you treat it as if it was a function, okay? Stick it in parentheses. So if you want to look in the PyTorch source code and find nn.embedding, you will find there's something called .forward in there, which will do this array lookup for us. So here's where we grab the users. Here's where we grab the items. And so we've now got the embeddings for each, right? And so at this point, we're kind of like here, and we found that and that. So we multiply them together and sum them up, and then we add on the user bias and the item bias. And then if we've got a Y range, then we do our sigmoid trick. And so the nice thing is, you now understand the entirety of this model. And this is not just any model, this is a model that we just found is at the very least highly competitive with, and perhaps slightly better than, some published table of pretty good numbers from a software group that does nothing but this. So you're doing well, right? This is nice. So that's probably a good place to have a break. And so after the break, we're going to come back and we're going to talk about the one piece of this puzzle we haven't learnt yet, which is what the hell does this do? Okay, so let's come back at 7:50. Okay, so this idea of interpreting embeddings is really interesting, and as we'll see later in this lesson, the things that we create for categorical variables more generally in tabular data sets are also embedding matrices. And again, that's just a normal matrix multiply by a one-hot encoded input, where we skip the computational and memory burden of it by doing it in a more efficient way. And it happens to end up with these interesting semantics kind of accidentally. And there was this really interesting paper by these folks who came second in a Kaggle competition for something called Rossmann. We'll probably look in more detail at the Rossmann competition in part 2. I think we're going to run out of time in part 1, but it's basically this pretty standard tabular stuff. The main interesting stuff is in the pre-processing. And it was interesting because they came second, despite the fact that the person who came first and pretty much everybody else towards the top of the leaderboard did a massive amount of highly specific feature engineering, whereas these folks did way less feature engineering than anybody else. But instead they used a neural net, and this was at a time in 2016 when just no one did that. No one was doing neural nets for tabular data. So they have, you know, the kind of stuff that we've been talking about kind of arose there, or at least was kind of popularized there. And when I say popularized, I mean only popularized a tiny bit. Still, most people aren't aware of this idea. But it's pretty cool because in their paper, they showed that the mean average percentage error for various techniques, k-nearest neighbors, random forest, and gradient boosted trees. Well, first, you know, neural nets just worked a lot better, but then with entity embeddings, which is what they call this, just using entity matrices in tabular data, they actually added the entity embeddings to all of these different tasks after training them, and they all got way better, right? So neural nets with entity embeddings are still the best, but a random forest with entity embeddings was not at all far behind, and you know that's often kind of nice, right? Because you could train these entity matrices for products or stores or genome motifs or whatever, and then use them in lots of different models, possibly, you know, using faster things like random forests, but getting a lot of the benefits. But here was something interesting. They took a two-dimensional projection of their embedding matrix for state, for example, German state, because this was a German supermarket chain, I think, using the same kind of approach we did. I don't remember if they used PCA or something else slightly different. And then here's the interesting thing. I've circled here, a few things in this embedding space, and I've circled it with the same color over here. And here I've circled some, same color over here. And it's like, oh my God, the embedding projection has actually discovered geography. Like they didn't do that, right? But it's found things that are nearby each other in grocery purchasing patterns, because this was about predicting how many sales there will be. There is some geographic element of that. In fact, here is a graph of the distance between two embedding vectors. So you can just take an embedding vector and say, what's the sum of squared, compared to some other embedding vector, and that's the Euclidean distance. What's the distance in embedding space, and then plot it against the distance in real life between shops, and you get this very strong positive correlation. Here is an embedding space for the days of the week, and as you can see, there's a very clear path through them. Here's the embedding space for the months of the year, and again, there's a very clear path through them. So, embeddings are amazing, and I don't feel like anybody's even close to exploring the kind of interpretation that you could get, right? So if you've got genome motifs or plant species or products that your shop sells or whatever, it would be really interesting to train a few models and try and kind of fine-tune some embeddings and then start looking at them in these ways in terms of similarity to other ones and clustering them and projecting them into 2D spaces and whatever. I think it's really interesting. So we were trying to make sure we understood what every line of code did in this pretty good Colab learner model we built. And so the one piece missing is this WD piece. And WD stands for weight decay. So what is weight decay? Weight decay is a type of regularization. What is regularization? Well, let's start by going back to this nice little chart that Andrew Ng did in his terrific machine learning course, where he plotted some data and then showed a few different lines through it. This one here, because Andrew's at Stanford, he has to use Greek letters. Okay, so we can say this is A plus BX, but if you want to go there, theta naught plus theta 1x is a line, right? It's a line even if it's got Greek letters, it's still a line. So here's a second degree polynomial, A plus BX plus CX squared, bit of curve, right? And here's a high degree polynomial, which is curvy as anything. So models with more parameters tend to look more like this. And so in traditional statistics, we say, hey, let's use less parameters because we don't want it to look like this. Because if it looks like this, then the predictions over here and over here, they're going to be all wrong, right? It's not going to generalize well. We're overfitting. So we avoid overfitting by using less parameters. And so if any of you are unlucky enough to have been brainwashed by a background in statistics or psychology or econometrics or any of these kinds of courses, you're going to have to unlearn the idea that you need less parameters. Because what you instead need to realize this is you were fed this lie that you need less parameters because it's a convenient fiction for the real truth, which is you don't want your function to be too complex. And having less parameters is one way of making it less complex. But what if you had 1,000 parameters and 999 of those parameters were 1e neg 9? Well, what if they were 0? If they're 0, they're not really there. Or if they're 1e neg 9, they're hardly there. right? So like, why can't I have lots of parameters if like lots of them are really small? And the answer is you can. Okay, you know, so this thing of like counting the number of parameters is how we limit complexity is actually extremely limiting. It's a fiction that really has a lot of problems, right? And so if in your head complexity is scored by how many parameters you have, you're doing it all wrong, right? Score it properly, right? So why do we care? Why would I want to use more parameters? Because more parameters means more nonlinearities, more interactions, more curvy bits, right? And real life is full of curvy bits, right? Real life does not look like this. But we don't want them to be more curvy than necessary, or more interacting than necessary. So therefore, let's use lots of parameters and then penalize complexity. Okay, so one way to penalize complexity is, as I kind of suggested before, is let's sum up the value of your parameters. Now that doesn't quite work because some parameters are positive and some are negative, right? So what if we sum up the square of the parameters, right? And that's actually a really good idea. Right? Let's actually create a model, and in the loss function we're going to add the sum of the square of the parameters. Now here's the problem with that though. Maybe that number is way too big, and it's so big that the best loss is to set all of the parameters to 0. Now that would be no good, right? So actually we want to make sure that doesn't happen. So therefore, let's not just add the sum of the squares of the parameters to the model, but let's multiply that by some number that we choose. And that number that we choose in FastAI is called WD. Okay? So that's what we're going to do. We're going to take our loss function and we're going to add to it the sum of the squares of the parameters multiplied by some number. WD. What should that number be? Well, generally it should be 0.1. Okay. People with fancy machine learning PhDs are extremely skeptical and dismissive of any claims that a learning rate can be 3e neg 3 most of the time, or a weight decay can be 0.1 most of the time. But here's the thing. We've done a lot of experiments on a lot of data sets, and we've had a lot of trouble finding anywhere a weight decay of 0.1 isn't great. However, we don't make that the default. We actually make the default 0.01. Why? Because in those rare occasions where you have too much weight decay, no matter how much you train, it just never quite fits well enough. Whereas if you have too little weight decay, you can still train well. You'll just start to overfit, so you just have to stop a little bit early. So we've been a little bit conservative with our defaults, but my suggestion to you is this. Now that you know that every learner has a WD argument, and I should mention, you won't always see it in this list, right? Because there's this concept of KW args in Python, which is basically parameters that are going to get passed up the chain to the next thing that we call. And so basically all of the learners will call eventually this constructor, and this constructor has a WD, right? So this is just one of those things that you can either look in the docs or you now know it. Anytime you're constructing a learner from pretty much any kind of function in FastAI, you can pass WD. Okay, and so passing 0.1 instead of the default 0.01 will often help. Okay, so give it a go. So what's really going on here? It would be helpful, I think, to go back to lesson 2 SGD, because everything we're doing for the rest of today really is based on this, right? And this is where we created some data, and then we added a loss function, MSE, and then we created a function called update, which calculated our predictions. That's our matrix multiply. This is just a one layer, so there's no ReLU. We calculated our loss using that mean squared error. We calculated the gradients using loss.backward. We then subtracted in place the learning rate times the gradients, and that is gradient descent. So if you haven't reviewed lesson 2 SGD, please do, because this is our starting point. So if you don't get this, then none of this is going to make sense. If you're watching the video, maybe pause now, go back, rewatch this part of lesson 2, make sure you get it. Remember, a.sub underscore is basically the same as a minus equals, because a.sub is subtract, and everything in PyTorch, if you add an underscore to it, means do it in place. So this is updating our a parameters, which started out as minus 0.11. We just arbitrarily picked those numbers, and it gradually makes them better. Right? So let's write that down. So we are trying to calculate the parameters. I'm going to call them weights because this is just more common. In kind of epoch t or time t, and they're going to be equal to whatever the weights were in the previous epoch minus our learning rate multiplied by, it's the derivative of our loss function with respect to our weights at time t minus 1. Okay, so that's what this is doing. Okay, and we don't have to calculate the derivative because it's boring and because computers do it for us fast, and then they store it here for us, so we're good to go. Okay, so make sure you're exceptionally comfortable with either that equation or that line of code, because they're the same thing. Where do we go from here? All right. So what's that? What's our loss? Our loss is some function of our independent variables, x, and our weights, right? And in our case, we're using mean squared error, for example, and it's between our predictions and our actuals, right? So where does x and w come in? Well, our predictions come from running some model, we'll call it m, on those predictions, and that model contains some weights, right? So that's what our loss function might be. And this might be all kinds of other loss functions. We'll see some more today. And so that's what ends up creating a.grad over here. So we're going to do something else. We're going to add weight decay, some number, which in our case is 0.1, times the sum of weights squared. Okay? So let's do that. And let's make it interesting by not using synthetic data, but let's use some real data. And we're going to use MNIST, the hand-drawn digits, right? But we're going to do this as a standard, fully connected net, not as a convolutional net, because we haven't learnt the details of how to really create one of those from scratch. So in this case, there's actually deeplearning.net provides MNIST as a Python pickle file. In other words, it's a file that Python can just open up, and it'll give you NumPy arrays straight away, and they're flat NumPy arrays. We don't have to do anything to them. So go grab that. And it's a gzipped file, so you can actually just gzip.open it directly. And then you can pickle.load it directly. And again, encoding equals Latin 1 because, yeah, you know. And then we can just put that'll give us the training, the validation, and the test set. I don't care about the test set. So generally in Python, if there's like something you don't care about, you tend to use this special variable called underscore. There's no reason you have to. It's just kind of, people know you mean I don't care about this, right? So there's our training X and Y and our valid X and Y. Now this actually comes in as you can see, if I print the shape, 50,000 rows by 784 columns. But those 784 columns are actually 28 by 28 pixel pictures. So if I reshape one of them into a 28 by 28 pixel picture and plot it, right, then you can see it's the number 5. Okay, so that's our data. We've seen MNIST before in its kind of pre-reshaped version. Here it is in its flattened version. So I'm going to be using it in its flattened version, okay? Currently they are NumPy arrays. I need them to be tensors, so I can just map torch.tensor across all of them, and so now they're tensors. Okay. I may as well create a variable with the number of things I have, which we normally call n, and remember we normally have a thing called, we tend to use c to mean the number of activations we need. Well, actually, sorry, this is not going to be activations. Sorry, this is going to be number of columns. That's not a great name for it, sorry. Okay, so there we are. And then the y, not surprisingly, the minimum value is 0, and the maximum value is 9, because that's the actual number we're trying to predict. Great. So in lesson 2 SGD, we created a data where we actually added a column of 1s on so that we didn't have to worry about bias. We're not going to do that. We're going to have PyTorch do that kind of implicitly for us. We had to write our own MSE function. We're not going to do that. We had to write our own little matrix multiplication thing. We're not going to do that. We're going to have PyTorch do all this stuff for us now. Okay? And what's more, and really important, we're going to do mini batches. Right, because this is a big enough data set, we probably don't want to do it all at once. So if you want to do mini batches, so we're not going to use too much fast AI stuff here. PyTorch has something called tensor dataset that basically grabs any kind of tensor, two tensors, and creates a dataset. Remember, a dataset is something where if you index into it, you get back an X value and a Y value, just one of them, okay? So it kind of looks a lot like a list of X, Y tuples. Once you have a data set, then you can use a little bit of convenience by calling databunch.create, and what's that going to do is it's going to create data loaders for you. A data loader is something which you don't say, I want the first thing or the fifth thing, you just say, I want the next thing, and it will give you a batch, a mini batch of whatever size you asked for. And specifically, it'll give you the X and the Y of a mini batch. So if I just grab the next of the iterator, this is just standard Python, if you haven't used iterators in Python before. Here's my training data loader that databunch.create creates for you. And you can check that, as you would expect, the X is 64 by 784, because there's 784 pixels flattened out, 64 in a mini batch. And the Y is just 64 numbers. There are things we're trying to predict. So, if you look at the source code for databunch.create, you'll see there's not much there, right? So feel free to do so. We just make sure that your training set gets shuffled, randomly shuffled for you. We make sure that the data is put on the GPU for you. Just a couple of little convenience things like that. But don't let it be magic. If it feels magic, check out the source code to make sure you see what's going on. Okay. So rather than do this y hat equals x at a thing, we're going to create an nn.module. Right? If you want to create an nn.module that does something different to what's already out there, you have to subclass it. Right? So subclassing is very, very, very normal in PyTorch. So if you're not comfortable with subclassing stuff in Python, go read a couple of tutorials to make sure you are. Main thing is you have to override the constructor done to init and make sure that you call the superclasses constructor, because nn.modules superclasses constructor is going to like set it all up to be a proper nn.module for you. So if you're trying to create your own PyTorch subclass and things don't work, it's almost certainly because you forgot this line of code. All right, so the only thing we want to add is we want to create an attribute in our class which contains a linear layer, an nn.linear module. What is an nn.linear module? It's something which does that, but actually it doesn't only do that, it actually is x at a plus b. So in other words, we don't have to add the column of ones. Okay, that's all it does. Okay, so if you want to play around, why don't you try and create your own nn.linear class? You could create something called myLinear, and it'll take you, depending on your PyTorch background, an hour or two. And then you'll feel like, okay, we don't want any of this to be magic. And you know all of the things necessary to create this now. So, these are the kind of things that you should be doing for your assignments this week, is not so much new applications, but try to start writing more of these things from scratch and get them to work. Learn how to debug them, check what's going in and out, and so forth. Okay. But we can just use nn.linear, and that's just going to do, so it's going to have a def forward in it that goes a at x plus b, right? And so then in our forward, how do we calculate the result of this? Well, remember, every nn.module looks like a function. So we pass our x mini batch, so I tend to use xb to mean a batch of x, to self.lin, and that's going to give us back the result of the a at x plus b on this mini batch. So this is a logistic regression model. A logistic regression model is also known as a neural net with no hidden layers. So it's a one-layer neural net, no nonlinearities. Because we're doing stuff ourselves a little bit, we have to put the weight matrices, the parameters, onto the GPU manually. So just type .CUDA to do that. So here's our model. And as you can see, the nn.module machinery has automatically given us a representation of it. It's automatically stored the .lin thing, and it's telling us what's inside it. So there's a lot of little conveniences that PyTorch does for us. So if you look now at model.lin, you can see, not surprisingly, here it is. Perhaps the most interesting thing to point out is that our model automatically gets a bunch of methods and properties, and perhaps the most interesting one is the one called parameters, which contains all of the yellow squares from our picture, right? It contains our parameters. It contains our weight matrices and bias matrices in as much as they're different. So if we have a look at p.shape for p and model.parameters, there's something of 10 by 784, and there's something of 10. So what are they? Well, 10 by 784, okay, so that's the thing that's going to take in 784 dimensional input and spit out a 10-dimensional output, because that's handy, because our input is 784 dimensional, and we need something that's going to give us the probability of 10 numbers. After that happens, we've got 10 activations, which we then want to add the bias to. So there we go, here's a vector of length 10. So you can see why this model we've created has exactly the stuff that we need to do our AX plus B. So let's grab a learning rate. We're going to come back to this loss function in a moment, but we can't use we can't really use MSE for this, right? Because we're not trying to say how close are you. Did you predict 3 and actually it was 4? Gosh, you were really close. It's like, no, 3 is just as far away from 4 as 0 is away from 4 when you're trying to predict what number did somebody draw. So we're not going to use MSE. We're going to use cross-entropy loss, which we'll look at in a moment. And here's our update function. I copied it from lesson 2 SGD. But now we're calling our model rather than going a at x. We're calling our model as if it was a function to get y hat. And we're calling our loss func rather than calling MSE to get our loss. And then this is all the same as before, except rather than going through each parameter and going parameter dot sub underscore learning rate times gradient, we loop through the parameters. Okay? Because very nicely for us, PyTorch will automatically create this list of the parameters of anything that we created in our dunder init. And look, I've added something else. I've got this thing called W2. I go through each P and model.parameters and I add to W2 the sum of squareds. So W2 now contains my sum of squareds weights. And then I multiply it by some number, which I set to 1a neg 5. So now I just implemented weight decay. Okay, so when people talk about weight decay, it's not an amazing, magic, complex thing containing thousands of lines of CUDA, C++ code. It's those 2 lines of Python. That's weight decay. This is not a simplified version that's just enough for now. This is weight decay. That's it. Okay? And so here's the thing. There's a really interesting kind of dual way of thinking about weight decay. One is that we're adding the sum of squared weights. And that seems like a very sound thing to do, and it is. And well, let's go ahead and run this. So here I've just got a list comprehension that's going through my data loader. So the data loader gives you back one mini batch and for the whole thing, giving you X, Y each time. I'm going to call update for each. Each one returns loss. Now, PyTorch tensors, since I did it all on the GPU, that's sitting in the GPU, and it's like got all this stuff attached to it to calculate gradients. It's going to use up a lot of memory. So if you call .item on a scalar tensor, it turns it into an actual normal Python number. So this is just means I'm returning back normal Python numbers. And then I can plot them, and yeah, there you go. My loss function is going down. And you know, it's really nice to try this stuff to see it behaves as you expect. Like we thought this is what would happen. As we get closer and closer to the answer, it bounces around more and more, right? Because we're kind of close to where we should be. It's kind of getting flat, probably flatter in weight space, so we're kind of jumping further. And so you can see why we would probably want to be reducing our learning rate as we go. Learning rate annealing. Okay, now, here's the thing. That is only interesting for training a neural net because it appears here. Because we take the gradient of it. That's the thing that actually updates the weights, right? So actually the only thing interesting about WD times sum of W squared is its gradient. So we don't do a lot of math here, but I think we can handle that. The gradient of this whole thing, if you remember back to your high school math, is equal to the gradient of each part taken separately and then add them together. So let's just take the gradient of that, right? Because we already know the gradient of this is just whatever we had before, right? So what's the gradient of WD times the sum of W squared, right? Let's remove the sum and pretend there's just one parameter. It doesn't change the generality of it. So the gradient of WD times W squared. So what's the gradient of that with respect to W? It's just 2 WD times W. Right? And so remember, this is our constant, which in our case was like, well, in that little loop it was 1e neg 5. Okay? And that's our weights. And like, we could replace WD with like 2 WD without loss of generality, so let's throw away the 2. So in other words, all weight decay does is it subtracts some constant times the weights every time we do a batch. So that's why it's called weight decay, right? When it's in this form where we add the square to the loss function, that's called L2 regularization. When it's in this form, where we subtract WD times weights from the gradients. That's called weight decay. And they are kind of mathematically identical. For everything we've seen so far, in fact, they are mathematically identical. Right? And we'll see in a moment a place where they're not, where things get interesting. Okay, so this is just a really important tool you now have in your toolbox. You can make giant neural networks, right, and still avoid overfitting by adding more weight decay. Okay? Or you could use really small data sets with moderately large-sized models and avoid overfitting with weight decay. It's not magic, right? Like, you might still find you don't have enough data, in which case, like, you get to the point where you're not overfitting by adding lots of weight decay and it's just not training very well. That can happen, right? But at least this is something that you can now play around with. Just to kind of go on here, now that we've got this update function, we could replace this MNIST logistic with MNIST neural network and build a neural network from scratch. Right, now we just need 2 linear layers. Right? And the first one, we could use a weight matrix of size 50. And so we then need to make sure that the second linear layer has an input of size 50, so it matches. The final layer has to have an output of size 10, because that's the number of classes we're predicting. And so now our forward just goes, do a linear layer, calculate ReLU, do a second linear layer, and now we've actually created a neural net from scratch. I mean, we didn't write it in linear, but you can write it yourself, or you could like do the matrices directly. You know how to. So again, you know, if we go model.CUDA, and then we can calculate losses with the exact same update function, there it goes, right? So this is why this kind of idea of neural nets is so easy, right? Once you have something that can do gradient descent, right, then you can try different models. And then you can start to add more PyTorch stuff. So like, rather than doing all this stuff yourself, why not just go opt equals optim dot something. So the something we've done so far is SGD. And so now you're saying to PyTorch, I want you to take these parameters and optimize them using SGD. And so this now, rather than saying for P in parameters, P minus equals LR times P dot grad, you just say opt dot step. It's the same thing. Okay, it's just less code, right? But, and it does the same thing. But the reason it's kind of particularly interesting is that now you can replace SGD with Atom, for example, and you can even add things like weight decay, right? Because like, there's more stuff that's kind of in these things for you, right? So that's why we tend to use, you know, optim.blah. So behind the scenes, this is actually what we do in FastAI. So if I go optim.sgd, okay, so there's that, right? And so that's just that picture. But if we change to a different optimizer, so look what happened. It diverged, right? We've seen a great picture of that from one of our students who showed what divergence looks like. This is what it looks like when you try to train something. So let's use, we're using a different optimizer, so we need a different learning rate. And you can't just continue training, because by the time it's diverged, the weights are like really, really big and really, really small. They're not going to come back. So start again. Okay, there's a better learning rate. But look at this. We're down underneath 0.5 by about epoch 200, whereas before, I'm not even sure we ever got to quite that level. So what's going on? What's Atom? Let me show you. And we're going to do gradient descent in Excel, because why wouldn't you? Okay, so here is some randomly generated data. Okay, some X's and some Y's. Well, they're randomly generated X's, and the Y's are all calculated by doing AX plus B, where A is 2 and B is 30. Okay, so this is some data that we're going to try and match. And here is SGD. And so we're going to do it with SGD. Now, in our lesson 2 SGD notebook, we did the whole data set at once as a batch. In the notebook we just looked at, we did mini batches. In this spreadsheet, we're going to do online gradient descent, which means every single row of data is a batch. So it's kind of batch size of 1. Okay. So as per usual, we're going to start by picking an intercept and slope kind of arbitrarily. So I'm just going to pick them at 1. Doesn't really matter. So here I've copied over the data. This is my x and y. And so my intercept and slope, as I said, is 1. Right? I'm just literally referring back to this cell here. So my prediction for this particular intercept and slope would be 14 times 1 plus 1, which is 15. And so there's my error, means there's my sum of squareds. Well, not even a sum at this point. It's the squared error. Okay? So now I need to calculate the gradient so that I can update. There's 2 ways you can calculate the gradient. One is analytically, and so you can just look them up on Wolfram Alpha or whatever. So there's the gradients if you write it out by hand or look it up. Or you can do something called finite differencing, because remember, gradients just how far you move in how far the outcome moves divided by how far your change was for really small changes. So let's just make a really small change. So here we've taken our intercept and added 0.01 to it, right? And then calculated our loss. And you can see that our loss went down a little bit, right? And we added 0.01 here. So our derivative is that difference divided by that 0.01. Okay, and that's called finite differencing. You can always do derivatives with finite differencing. It's slow. We don't do it in practice, but it's nice for just checking stuff out. So we can do the same thing for our A term, add 0.01 to that, take the difference and divide by 0.01. Or, as I say, we can calculate it directly using the actual derivative analytical. And you can see that, that and that are, as you'd expect, very similar. And that and that are very similar. So gradient descent then just says, let's take our current value of that weight and subtract the learning rate times the derivative. There it is, right? And so now we can copy that intercept and that slope to the next row and do it again. And do it lots of times. And at the end, we've done 1 epoch. So at the end of that epoch, we could say, oh, great. So this is our slope. So let's copy that over to where it says slope. And this is our intercept. So we'll copy it to where it says intercept. And now it's done another epoch. Okay? So that's kind of boring, copying and pasting. So I created a very sophisticated macro which copies and pastes for you. And so I just recorded it basically. And so and then I created a very sophisticated for loop that goes through and does it 5 times. And I attached that to the run button. So if I press run, it'll go ahead and do it 5 times and just keep track of the error each time. Okay, so that is SGD. And as you can see, it is just infuriatingly slow. Like particularly the intercept is meant to be 30. And we're still only up to 1.57. And it's just going so slowly. So let's speed it up. So the first thing we can do to speed it up is to use something called momentum, right? So here's the exact same spreadsheet as the last worksheet. I've removed the finite differencing version of the derivatives because they're not that useful, just the analytical ones here. And here's the thing where I take the derivative and I'm going to update by the derivative. But what I do, it's kind of more interesting to look at this one, is I take the derivative and I multiply it by 0.1. And what I do is I look at the previous update and I multiply that by 0.9 and I add the two together. So in other words, the update that I do is not just based on the derivative, but 1/10 of it is the derivative, and 90% of it is just the same direction I went last time. And this is called momentum, right? What it means is, remember how we kind of thought about what might happen if you're trying to find the minimum of this, and you were here and your learning rate was too small, right? And you just keep doing the same steps. Or if you keep doing the same steps, then if you also add in the step you took last time, then your steps are going to get bigger and bigger, aren't they? Okay, until eventually they go too far. But now, of course, your gradient's pointing the other direction to where your momentum's pointing, so you might just take a little step over here, and then you'll start going small steps, bigger steps, small steps, bigger steps, like that, right? So that's kind of what momentum does. Or if you're kind of going too far, like this, which is also slow, right, then the average of your last few steps is actually somewhere kind of between the two, isn't it? Right? So this is a really common idea, right? It's like when you have something that says kind of my, what is it in this case? It's like my step at time t equals some number. People often use alpha because, like I say, you've got to love these Greek letters. Some number times the actual thing I want to do, right? So it might, in this case, it's like the gradient, right? Plus 1 minus alpha times whatever you had last time, st minus 1. This thing here is called an exponentially weighted moving average. And the reason why is that if you think about it, these 1 minus alphas are going to multiply. So st minus 2 is in here with a kind of a 1 minus alpha squared. And st minus 3 is in there with a 1 minus alpha cubed. So in other words, this ends up being the actual thing I want plus a weighted average of the last few time periods where the most recent ones are exponentially higher weighted. Okay? And this is going to keep popping up again and again. Right? So that's what momentum is. It says I want to go based on the current gradient plus the exponentially weighted moving average of my last few steps. So that's useful. That's called SGD with momentum. And we can do it by changing this here to saying SGD momentum. And momentum 0.9 is really common. It's, I don't know, it's so common it's always 0.9 just about for basic stuff. So that's how you do SGD with momentum. And again, it's not, I didn't show you some simplified version, I showed you the version that is SGD. Okay, that's you, again, you can write your own, try it out. That would be a great assignment, would be to take lesson 2 SGD and add momentum to it. Or even the new notebook we've got for MNIST, get rid of the optim dot and write your own update function with momentum. Then there's a cool thing called RMS prop. One of the really cool things about RMS prop is that Geoffrey Hinton created it, a famous neural net guy. Everybody uses it. It's like really popular. It's really common. The correct citation for RMS prop is the Coursera online free MOOC. That's where he first mentioned RMS prop. So I love this thing that, like, you know, cool new things appear in MOOCs, not a paper. So RMS prop is very similar to momentum, but this time we have an exponentially weighted moving average, not of the gradient updates, but of f8 squared. That's the gradient squared. So I've got the gradient squared times 0.1 plus the previous value times 0.9. So it's this is an exponentially weighted moving average of the gradient squared. So what's this number going to mean? Well, if my gradient's really small and consistently really small, this will be a small number. If my gradient is highly volatile, it's going to be a big number. Or if it's just really big all the time, it'll be a big number. And why is that interesting? Because when we do our update this time, we say weight minus learning rate times gradient divided by the square root of this. So in other words, if our gradient's consistently very small and not volatile, let's take bigger jumps. And that's kind of what we want, right? When we watched how the intercept moved so damn slowly, but it's like, obviously you need to just go faster. So if I now run this, after just 5 epochs, this is already up to 3, right? Whereas with the basic version, after 5 epochs, it's still at 1.27. And remember, we have to get to 30. So the obvious thing to do, and by obvious I mean only a couple of years ago did anybody actually figure this out, is do both. Right? So, and that's called ADAM. So ADAM is simply keep track of the exponentially weighted moving average of the gradient squared, and also keep track of the exponentially weighted moving average of my steps, right? And both divide by the exponentially weighted moving average of the squared terms, and take 0.9 of a step in the same direction as last time. So it's momentum and RMS prop. That's called ADAM. And look at this. Okay, 5 steps, we're at 25. Okay, so these optimizers, people call them dynamic learning rates. A lot of people have the misunderstanding that you don't have to set a learning rate. Of course you do, right? It's just like trying to identify parameters that need to move faster, or are consistently going in the same direction. It doesn't mean you don't need learning rates. We still have a learning rate. Okay, and in fact, if I run this again, currently my my error. No, just do it again. So we're trying to get to 30,2. So if I run it again, it's getting better, but eventually, now it's just moving around the same place, right? So you can see what's happened is the learning rate's too high. So we could just go in here and drop it down and run it some more. Getting pretty close now, right? So you can see how you still need learning rate annealing, even with ADAM. Okay, so that spreadsheet's fun to play around with. I do have a Google Sheets version of basic SGD that actually works and the macros work and everything. Google Sheets is so awful and I went so insane making that work, I gave up on making the other ones work. So I'll share a link to the Google Sheets version. Oh my God. They do have a macro language, but it's just ridiculous. So anyway, if somebody feels like fighting it to actually get all the other ones to work, they will work. It's just annoying. So maybe somebody can get this working on Google Sheets too. Okay, so that's weight decay and ADAM. And ADAM is amazingly fast. And let's go back to this one. But we don't tend to use optim.whatever and create the optimizer ourselves and all that stuff, because instead we tend to use Learner. But Learner's just doing those things for you, right? Again, there's no magic, right? So if you create a Learner, you say, here's my data bunch, here's my PyTorch nn.module instance, here's my loss function, and here are my metrics. Remember, the metrics are just stuff to print out, That's it, right? Then you just get a few nice things like learn.lrfind starts working and it starts recording this. And you can say fit one cycle instead of just fit. But like these things really help a lot. Like by using the learning rate finder, I found a good learning rate. And then like look at this, my loss here, 0.13. Here I wasn't getting much beneath 0.5. Right? So these tweaks make huge differences, not tiny differences. And this is still just one epoch. Now, what does fit one cycle do? What does it really do? This is what it really does. Right? And we've seen this chart on the left before. Just to remind you, this is plotting the learning rate per batch. Right? Remember, Adam has a learning rate. And we use Adam by default, or minor variation, which we might try to talk about. So the learning rate starts really low and it increases about half the time, and then it decreases about half the time. Because at the very start, we don't know where we are, right? So we're in some part of function space that's just bumpy as all hell, right? So if you start jumping around, those bumps have big gradients and it'll throw you into crazy parts of the space, right? So start slow. And then you'll gradually move into parts of the weight space that, you know, they're kind of sensible. And as you get to the points where they're sensible, you can increase the learning rate, you know, because the gradients are actually in the direction you want to go. Right? And then, as we've discussed a few times, as you get close to the final answer, you need to anneal your learning rate to hone in on it. But here's the interesting thing. On the left is the momentum plot. And actually, every time our learning rate is small, our momentum is high. Why is that? Because if you do have a small learning rate, but you keep going in the same direction, you may as well go faster. Right? But if you're jumping really far, don't like jump really far because it's going to throw you off, right? And then as you get to the end again, you're fine-tuning in, but actually if you keep going in the same direction again and again, go faster, right? So this combination is called one cycle, and it's just this amazing, like it's a simple thing, but it's astonishing. Like this can help you get what's called superconvergence that can let you train 10 times faster. And this is just last year's paper. And some of you may have seen the interview with Leslie Smith that I did last week. Amazing guy, incredibly humble. And also, I should say, somebody who is doing groundbreaking research well into his 60s. And all of these things are inspiring. I'll show you something else interesting. When you plot the losses with FastAI, it doesn't look like that. It looks like that. Why is that? Because FastAI calculates the exponentially weighted moving average of the losses for you. Right? So this concept of exponentially weighted stuff, it's just really handy. And I use it all the time. And one of the things that is to make it easier to read these charts. Okay? It does mean that these charts from FastAI might be kind of an epoch or two, a batch or two behind where they should be. You know, there's that slight downside when you use an exponentially weighted moving average is you've got a little bit of history in there as well, but it can make it much easier to see what's going on. So, we're now at a point coming to the end of this Colab and tabular section where we're going to try to understand all of the code in our tabular model. So remember the tabular model uses this data set called adult, which is trying to predict who's going to make more money. It's a classification problem. And we've got a number of categorical variables and a number of continuous variables. So the first thing we realize is we actually don't know how to predict a categorical variable yet, because so far we did some hand waving around the fact that our loss function was nn.cross-entropy loss. What is that? Let's find out. And of course, we're going to find out by looking at Microsoft Excel. So, cross-entropy loss is just another loss function. We already know one loss function, which is mean squared error, y hat minus y squared. Okay, so that's not a good loss function for us, because in our case we have, like for MNIST, 10 possible digits, and we have 10 activations, each with a probability of that digit. Okay. So we need something where predicting the right thing correctly and confidently should have very little loss. Predicting the wrong thing confidently should have a lot of loss. So that's what we want. Okay, so here's an example. Here is cat versus dog, one hot encoded. Okay? And here are my two activations for each one from some model that I built. Probability cat, probability dog. This one's not very confident of anything. This one's very confident of it being a cat and it's right. This one's very confident of being a cat and it's wrong. So we want a loss that for this one should be a moderate loss, because not predicting anything confidently is not really what we want. So here's a 0.3. This thing's predicting the correct thing very confidently, so 0.01. This thing's predicting the wrong thing very confidently, so 1. So how do we do that? This is the cross-entropy loss, and it is equal to whether it's a cat multiplied by log of the probability of cat, or this is actually an activation, so I should say. So it's multiplied by the log of the cat activation, negative that, minus, is it a dog, times the log of the dog activation. And that's it. Okay, so in other words, it's the sum of all of your one hot encoded variables times all of your activations. So interestingly, these ones here are exactly the same numbers as these ones here, but I've written it differently. I've written it with an if function, because it's exactly this, because the zeros don't actually add anything, right? So actually it's exactly the same as saying, if it's a cat, then take the log of cattiness, and if it's a dog, so otherwise, take the log of 1 minus cattiness, in other words, the log of dogginess. So the sum of the one hot encoded times the activations is the same as an if function, which if you think about it, it's actually, because this is just a matrix multiply, this is, we now know from our embedding discussion, that's the same as an index lookup. So you can also, to do cross entropy, you can also just look up the log of the activation for the correct answer. Now that's only going to work if these rows add up to 1. And this is one reason that you can get screwy cross entropy numbers, is that's why I said you press the wrong button. If they don't add up to 1, you've got a trouble. So how do you make sure that they add up to 1? You make sure they add up to 1 by using the correct activation function in your last layer, and the correct activation function to use for this is softmax. Softmax is an activation function where all of the activations add up to 1, all of the activations are greater than 0, and all of the activations are less than 1. So that's what we want, right? That's what we need. How do you do that? Well, let's say we were predicting one of 5 things: cat, dog, plane, fish, building. And these were the numbers that came out of our neural net for one set of predictions. Well, what if I did e to the power of that? So that's one step in the right direction, because e to the power of something is always bigger than 0. So there's a bunch of numbers that are always bigger than 0. Here's the sum of those numbers. Here is e to the number divided by the sum of e to the number. Now this number is always less than 1, right? Because all of the things were positive, so you can't possibly have one of the pieces be bigger than 100% of its sum. Okay? And all of those things must add up to 1, right? Because each one of them was just that percentage of the total. So that's it. So this thing, softmax, is equal to e to the activation divided by the sum of e to the activations. And that's called softmax. And so when we're doing single label multi-class classification, You generally want softmax as your activation function, and you generally want cross-entropy as your loss. And because these things go together in such friendly ways, PyTorch will do them both for you. Right? So you might have noticed that in this MNIST example, I never added a softmax here. And that's because if you ask for cross-entropy loss, it actually does the softmax inside the loss function. So it's not really just cross-entropy loss, it's actually softmax then cross-entropy loss. So you've probably noticed this, but sometimes your predictions from your models will come out looking more like this, pretty big numbers with negatives in, rather than this, numbers between 0 and 1 that add up to 1. The reason would be that PyTorch, it's a PyTorch model that doesn't have a softmax in, because we're using cross-entropy loss, and so you might have to do the softmax for it. FastAI is getting increasingly good at knowing when this is happening. Generally, if you're using a loss function that we recognize, when you get the predictions, we will try to add the softmax in there for you. But particularly if you're using a custom loss function that might call an n.cross-entropy loss behind the scenes or something like that, you might find yourself with this situation. We only have 3 minutes left, but I'm going to point something out to you, which is that next week, when we finish off tabular, which we'll do in like the first 10 minutes, this is forward in tabular. And it basically goes through a bunch of embeddings, right? It's going to call each one of those embeddings E, and you can use it like a function, of course. So it's going to pass in each categorical variable to each embedding. It's going to concatenate them together into a single matrix. It's going to then call a bunch of layers, which are basically a bunch of linear layers. And then it's going to do our sigmoid trick. And then there's only 2 new things we need to learn. One is dropout, and the other is, the end cont, batch norm. And these are 2 additional regularization strategies. Right? They're basically, batch norm does more than just regularization, but amongst other things it does regularization. And the basic ways you regularize your model are weight decay, batch norm, and dropout. Okay, and then you can also avoid overfitting using something called data augmentation. So batch norm and dropout we're going to touch on at the start of next week. And we're also going to look at data augmentation, and then we're also going to look at what convolutions are, and we're going to learn some new computer vision architectures and some new computer vision applications. But basically, we're very nearly there. You already know how the entirety of collab.py, fastai.collab works. You know why it's there and what it does, and you're very close to knowing what the entirety of tabular model does. And this tabular model is actually the one that if you run it on Rossmann, you'll get the same answer that I showed you in that paper. You'll get that second place result. In fact, even a little bit better. I'll show you next week, if I remember, how I actually ran some additional experiments where I figured out some minor tweaks that can do even slightly better than that. So yeah, we'll see you next week. Thanks very much, and enjoy the smoke outside. All right, welcome to lesson 6, where we're going to do a deep dive into computer vision, convolutional neural networks, what is a convolution, and we're also going to learn the final regularization tricks after last lesson learning about weight decay and /L2 regularization. I want to start by showing you something that I'm really excited about, and I've had a small hand in helping to create. For those of you that saw my talk on TED.com, you might have noticed this really interesting demo that we did about 4 years ago, showing a way to quickly build models with unlabeled data. It's been 4 years, but we're finally at a point where we're ready to put this out in the world and let people use it. And the first people we're going to let use it are you folks. So the company is called Platform.ai, and the reason I'm mentioning it here is that it's going to let you create models on different types of data sets to what you can do now. That is to say, data sets that you don't have labels for yet. We're actually going to help you label them. So this is the first time this has been shown before. So I'm pretty thrilled about it. Let me give you a quick demo. So if you go to platform.ai and choose Get Started, you'll be able to create a new project. And if you create a new project, you can either upload your own images. Uploading about 500 or so works pretty well. You can upload a few thousand, but you know, to start, upload 500 or so. They all have to be in a single folder. And so we're assuming that you've got a whole bunch of images that you haven't got any labels for. Or you can start with one of the existing collections if you want to play around. So I've started with the cars collection, kind of going back to what we did 4 years ago. And so this is what happens when you first go into Platform AI and look at the collection of images you uploaded. A random sample of them will appear on the screen. And as you'll recognize probably, they are projected from a deep learning space into a 2D space using a pre-trained model. And for this initial version, it's an ImageNet model we're using. As things move along, we'll be adding more and more pre-trained models. And what I'm going to do is I want to add labels to this data set representing which angle a photo of the car was taken from, which is something that actually ImageNet's going to be really bad at, isn't it? Because ImageNet has learnt to recognize the difference between cars versus bicycles, and ImageNet knows that the angle you take a photo on actually doesn't matter. So we want to try and create labels using the kind of thing that actually ImageNet specifically learned to ignore. So the projection that you see, we can click these layer buttons at the top to switch to user projection using a different layer of the neural net, right? And so here's the last layer, which is going to be a total waste of time for us because it's really going to be projecting things based on what kind of thing it thinks it is. And the first layer is probably going to be a waste of time for us as well because there's very little interesting semantic content there. But if I go into the middle in layer 3, we may well be able to find some differences there. So then what you can do is you can click on the projection button here, and you can actually just press up and down rather than just pressing the arrows at the top to switch between projections, or left and right to switch between layers. And what you can do is you can basically look around until you notice that there's a projection which has kind of separated out things you're interested in. And so this one actually, I notice that it's got a whole bunch of cars that are kind of from the top front right over here. Okay, so if we zoom in a little bit, we can double check. It's like, yeah, that looks pretty good. They're all kind of front right. So we can click on here to go to selection mode, and we can kind of grab a few, and then you should check. And so what we're doing here is we're trying to take advantage of the combination of human plus machine. The machine's pretty good at quickly doing calculations, but as a human, I'm pretty good at looking at a lot of things at once and seeing the odd one out. So in this case, I'm looking for cars that aren't front right. And so by laying them all in front of me, I can do that really quickly. It's like, okay, definitely that one. So just click on the ones that you don't want. All right, it's all good. So then you can just go back. And so then what you can do is you can either put them into a new category by typing create new label, or you can click on one of the existing ones. So before I came, I just created a few. So here's front right, so I just click on it here. There we go, okay. And so that's the basic idea, is that you kind of keep flicking through different layers or projections to try and find groups that represent the things you're interested in. And then over time, you'll start to realize that there are some things that are a little bit harder. So for example, I'm having trouble finding sides. So what I can do is, I can see over here there's a few sides. So I can zoom in here and click on a couple of them, like this one, and this one, that one, that one. Okay, and then I'll say find similar. And so this is going to basically look in that, that projection space, and not just at the images that are currently displayed, but all of the images that you uploaded. And hopefully I might be able to label now a few more side images at that point. So it's going through and checking, you know, all of the images that you uploaded to see if any of them have projections in this space which are similar to the ones I've selected, and hopefully we'll find a few more of what I'm interested in. Okay, so now if I want to try to find a projection that separates the sides from the front right, I can click on each of those two, and then over here this button's now called switch to the projection that maximizes the distance between the labels. So now what this is going to do is going to try and find the best projection that separates out those classes. And so the goal here is to, you know, help me visually inspect and quickly find a bunch of things that I can use to label. So like, they're the kind of the key features, and it's done a good job. You can see down here, we've now got a whole bunch of sides, which I can now grab, because I was having a lot of trouble finding them before. And it's always worth double checking. And it's kind of interesting to see how the neural nets behave. Like, there seems to be more sports cars in this group than average as well. So it's kind of found side angles of sports cars. So that's kind of interesting. So then I can click, all right, so I've got those. So now I'll click side. And there we go. So once you've done that a few times, I find if you've got, you know, 100 or so labels, you can then click on the train model button, and it'll take a couple of minutes and come back and show you your train model. And after it's trained, which I did it on a smaller number of labels earlier, you can then switch this vary opacity button, and it'll actually kind of fade out the ones that are already predicted pretty well, and it'll also give you an estimate as to how accurate it thinks the model is. The main reason I mention this for you is that so that you can now click the download button, and it'll download the predictions, which is what we hope will be interesting to most people. But what I think will be interesting to you as deep learning students is it'll download your labels. So now you can use that labeled subset of data along with the unlabeled set that you haven't labeled yet to see if you can, you know, see if you can build a better model than Platform AI has done for you. See if you can use that initial set of data to kind of get going, creating models of stuff which you weren't able to label before. Clearly, there are some things that this system's better at than others. For things that require, you know, really zooming in closely and taking a very, very close inspection, this isn't going to work very well. This is really designed for things that the human eye can kind of pick up fairly readily. But we'd love to get feedback as well, and you can click on the help button to get feedback, give feedback, and also there's a Platform AI discussion topic in our forum where, so Ashok, if you can stand up, Ashok's the CEO of the company. He'll be there helping out, answering questions and so forth. So yeah, I hope people find that useful. It's been many years getting to this point, and I'm glad we're finally there. Okay, so one of the reasons I wanted to mention this today is that we're going to be doing a big dive into convolutions later in this lesson. So I'm going to circle back to this to try and explain a little bit more about how that is working under the hood and give you a kind of a sense of what's going on. But before we do, we have to finish off last week's discussion of regularization. And so we were talking about regularization specifically in the context of the tabular learner, because the tabular learner, this was the forward method. This is the init method in the tabular learner, and our goal was to understand everything here. And we're not quite there yet. Last week we were looking at the adult data set, which is a really simple, kind of oversimple data set that's just for toy purposes. So this week, let's look at a data set that's much more interesting, a Kaggle competition data set. So we know kind of what the best in the world. And, you know, Kaggle competition results tend to be much harder to beat than academic state-of-the-art results tend to be, because a lot more people work on Kaggle competitions than most academic data sets. So it's a really good challenge to try and do well on a Kaggle competition data set. So this one, the Rossmann data set, they've got 3,000 drugstores in Europe, and you're trying to predict how many products they're going to sell in the next couple of weeks. So one of the interesting things about this is that the test set for this is from a time period that is more recent than the training set. And this is really common, right? If you want to predict things, there's no point predicting things that are in the middle of your training set. You want to predict things in the future. Another interesting thing about it is the evaluation metric they provided is the root mean squared percent error. So this is just a normal root mean squared error, except we go actual minus prediction divided by actual. So in other words, it's the percent error that we're taking the root mean squared of. So there's a couple of interesting features. Always interesting to look at the leaderboard. So the leaderboard, the winner was 0.1. The paper that we've roughly replicated was 0.105, 0.106, and 10th place out of 3,000 was 0.11-ish, a bit less. All right. So we're going to skip over a little bit, which is that the data that was provided here was, they provided a small number of files, but they also let competitors provide additional external data as long as they shared it with all the competitors. And so in practice, the data set we're going to use contains, I can't remember, 6 or 7 tables. The way that you join tables and stuff isn't really part of a deep learning course, so I'm going to skip over it. And instead, I'm going to refer you to Introduction to Machine Learning for Coders, which will take you step by step through the data preparation for this. We've provided it for you. We've provided it for you in Rossmann Data Clean. So you'll see the whole process there. And so you'll need to run through that notebook to create these pickle files that we read here. Can you see this in the back okay? Yep, great. I just want to mention one particularly interesting part of the Rossmann Data Clean notebook, which is you'll see there's something that says add date part. And I wanted to explain what's going on here. I've been mentioning for a while that we're going to look at time series. And pretty much everybody who I've spoken to about it has assumed that I'm going to do some kind of recurrent neural network. But I'm not. Interestingly, the main academic group that studies time series is econometrics, but they tend to study one very specific kind of time series, which is where the only data you have is a sequence of time points of one thing. Like that's the only thing you have is one sequence. In real life, that's almost never the case. Normally, you know, if we would have some information about the store that represents or the people that it represents, we'd have metadata, we'd have sequences of other things measured at similar time periods or different time periods. And so most of the time, I find in practice, the state-of-the-art results when it comes to competitions on kind of more real-world data sets don't tend to use recurrent neural networks, but instead they tend to take the time piece, which in this case it was a date we were given in the data, and they add a whole bunch of metadata. So in our case, for example, we've added day of week. So we were given a date, right? We've added day of week, year, month, week of year, day of month, day of week, day of year, and then a bunch of booleans. Is it the month start or end, quarter, year start or end, elapsed time since 1970, and so forth. If you run this one function, add date part, and pass it a date, it'll add all of these columns to your data set for you. And so what that means is that, let's take a very reasonable example. Purchasing behavior probably changes on payday. Payday might be the 15th of the month. So if you have a thing here called, this is day of month here, right? Then it'll be able to recognize every time something is a 15 there and associated it with a higher in this case, embedding matrix value, right? So this way, it basically, we can't expect a neural net to do all of our feature engineering for us. We can expect it to kind of find nonlinearities and interactions and stuff like that. But for something like taking a date like this and figuring out that the 15th of the month is something when interesting things happen, it's much better if we can provide that information for it. So this is a really useful function to use. And once you've done this, you can treat many kinds of time series problems as regular tabular problems. I say many kinds, not all. If there's very complex kind of state involved in a time series, such as, equity trading or something like that, this probably won't be the case, or this won't be the only thing you need. But in this case, it'll get us a really good result. And it's in practice most of the time I find this works well. Tabular data is normally in pandas, so we just stored them as standard Python pickle files. We can read them in. We can take a look at the first 5 records. And so the key thing here is that we're trying to, on a particular date, for a particular store ID, we want to predict the number of sales. Sales is the dependent variable. So the first thing I'm going to show you is something called preprocessors. You've already learned about transforms. Transforms are bits of code that run every time something is grabbed from a data set. And so it's really good for data augmentation that we'll learn about today, which is that it's going to get a different random value every time it's sampled. Preprocessors are like transforms, but they're a little bit different, which is that they run once before you do any training. And really importantly, they run once on the training set, and then any kind of state or metadata that's created is then shared with the validation and test set. Let me give you an example. When we've been doing image recognition, and we've had a set of classes for like all the different pet breeds, and they've been turned into numbers, the thing that's actually doing that for us is a preprocessor that's being created in the background. So that makes sure that the classes for the training set are the same as the classes for the validation and the classes for the test set. So we're going to do something very similar here. For example, if we create a little small subset of the data for playing with, this is a really good idea when you start with a new data set. So I've just grabbed 2,000 IDs at random, okay? And then I'm just going to grab a little training set and a little test set, half and half of those 2,000 IDs. I'm just going to grab 5 columns, okay? And then we can just play around with this. Nice and easy. So here's the first few of those from the training set. And you can see one of them is called promo interval, and it has these strings. And sometimes it's missing. In pandas, missing is NAN. So the first preprocessor I'll show you is categorify. And categorify does basically the same thing that that classes thing for image recognition does for our dependent variable. It's going to take these strings, it's going to find all of the possible unique values of it, and it's going to create a list of them, and then it's going to turn the strings into numbers. So if I call it on my training set, that'll create categories there. And then I call it on my test set, passing in test equals true, that makes sure it's going to use the same categories that I had before. And now when I say .head, it looks exactly the same. And that's because pandas has turned this into a categorical variable, which internally is storing numbers, but externally is showing me the strings. But I can look inside promo interval to look at the cat categories. This is all standard pandas here, to show me a list of all of the what we would call classes in FastAI, or would be called just categories in pandas. And so then if I look at the cat.codes, you can see here, this list here is the numbers that are actually stored. -1, -1, -1, -1, 1, right? What are these -1s? The -1s represent NAN. They represent missing. So pandas uses the special code -1 to mean missing. Now, as you know, these are going to end up in an embedding matrix. And we can't look up item -1 in an embedding matrix. So internally in FastAI, we add 1 to all of these. Another useful preprocessor is fix missing. And so again, you can call it on the data frame, you can call it on the test, passing in test equals true. And this will create for everything that's missing, anything that has a missing value, it'll create an additional column with the column name underscore NA, so competition distance underscore NA, and it'll set it for true for any time that was missing. And then what we do is we replace competition distance with the median for those. Why do we do this? Well, because very commonly the fact that something's missing is of itself interesting. Like, it turns out the fact that this is missing helps you predict your outcome, right? So we certainly want to keep that information in a convenient Boolean column so that our deep learning model can use it to predict things. But then we need competition distance to be a continuous variable, so we can use it in the continuous variable part of our model. So we can replace it with almost any number, right? Because if it turns out that the missingness is important, it can use the interaction of competition distance NA and competition distance to make predictions. So that's what fixed missing does. You don't have to manually call preprocessors yourself. When you call any kind of item list creator, you can pass in a list of preprocessors, which you can create like this. Okay, so this is saying, okay, I want to fill missing, I want to categorify, I want to normalize. So for continuous variables, it'll subtract the mean and divide by the standard deviation to help it train more easily. And so you just say, those are my procs, and then you can just pass it in there, and that's it. And later on, you can go data.export, and it'll save all the metadata for that data bunch, so you can later on load it in, knowing exactly what your category codes are, exactly what median values you use for replacing the missing values, and exactly what means and standard deviations you normalize by. Okay, so the main thing you have to do if you want to create a data bunch of tabular data is find out, or tell it, what are your categorical variables and what are your continuous variables. And as we discussed last week briefly, your categorical variables are not just strings and things, but also I include things like day of week and day of month. Even though they're numbers, I make them categorical variables because, for example, day of month, I don't think it's going to have a nice smooth curve. I think that the 15th of the month and the 1st of the month and the 30th of the month are probably going to have different purchasing behavior to other days of the month. And so therefore, if I make it a categorical variable, it's going to end up creating an embedding matrix, and those different days of the month can get different behaviors. So you've actually got to think carefully about which things should be categorical variables. And on the whole, if in doubt, and there are not too many levels in your category, that's called the cardinality. If your cardinality is not too high, I would put it as a categorical variable. But you can always try in each and see which works best. So our final data frame that we're going to pass in is going to be our training set with the categorical variables and the continuous variables and the dependent variable and the date. And the date we're just going to use to create a validation set where we're basically going to say the validation set is going to be the same number of records at the end of the time period that the test set is for Kaggle. And so that way we should be able to validate our model nicely. Okay, so now we can create a tabular list. So this is our standard data block API that you've seen a few times from a data frame. Pass in all of that information, split it into valid versus train, label it with a dependent variable. And here's something I don't think you've seen before. Label class. This is our dependent variable. And as you can see, this is sales. It's not a float. It's an int64. If this was a float, then FastAI would automatically know or guess that you want to do a regression. Okay, but this is not a float, it's an int, so FastAI is going to assume you want to do a classification. So when we label it, we have to tell it that the class of the labels we want is a list of floats, okay, not a list of categories, which would otherwise be the default. So this is the thing that's going to automatically turn this into a regression problem for us. And then we create a data bunch. So I wanted to remind you again about doc, which is how we find out more information about this stuff. In this case, all of the labeling functions in the data blocks API will pass on any keywords they don't recognize to the label class. So one of the things I've passed in here is log, and so that's actually going to end up in float list. And so if I go doc float list, I can see a summary, okay, and I can even jump into the full documentation. And it shows me here that log is something which, if true, it's going to take the logarithm of my dependent variable. Why am I doing that? So this is the thing that's actually going to automatically take the log of my y. The reason I'm doing that is because, as I mentioned before, the evaluation metric is root mean squared percentage error, and FastAI, neither FastAI nor PyTorch has a root mean squared percentage error loss function built in. I don't even know if such a loss function would work super well, but if you want to spend the time thinking about it, you'll notice that this ratio, if you first take the log of y and y hat, then becomes a difference rather than a ratio. So in other words, if you take the log of y, then this becomes root mean squared error. So that's what we're going to do. We're going to take the log of y, and then we're just going to use root mean squared error, which is the default for a regression problem, so we won't even have to mention it. The reason that we have this here is because this is so common, right? Basically, anytime you're trying to predict something that's like a population or a dollar amount of sales, these kind of things tend to have long-tail distributions where you care more about percentage differences than exact differences, absolute differences. So you're very likely to want to do things with log equals true and to measure the root mean squared percent error. We've learnt about the y range before, which is going to use that sigmoid to help us get in the right range. Because this time the y values are going to be taken the log of at first, we need to make sure that the y range we want is also the log. So I'm going to take the maximum of the sales column. I'm going to multiply it by a little bit, so that, because remember how we said it's nice if your range is a bit wider than the range of the data. And then we're going to take the log. Okay, and that's going to be our maximum. So then our y range will be from 0 to a bit more than the maximum. So now we've got our data bunch. We can create a tabular learner from it, and then we have to pass in our architecture. And as we briefly discussed, for a tabular model, our architecture is literally the most basic, fully connected network, just like we showed in this picture. It's an input, matrix multiply, nonlinearity, matrix multiply, nonlinearity, matrix multiply, nonlinearity, done. Okay. One of the interesting things about this is that this competition is 3 years old, but I'm not aware of any significant advances, at least in terms of architecture, that would cause me to choose something different to what the third-placed folks did 3 years ago. We're still basically using simple, fully connected models for this problem. Now, the intermediate weight matrix is going to have to go from a 1,000 activation input to a 500 activation output, which means it's going to have to be 500,000 elements in that weight matrix. That's an awful lot for a data set with only a few 100,000 rows. So this is going to overfit, and we need to make sure it doesn't. So one way to make sure it does, well, the way to make sure it doesn't is to use regularization, right? Not to reduce the number of parameters, to use regularization. So one way to do that will be to use weight decay, which FastAI will use automatically, and you can vary it to something other than the default if you wish. It turns out in this case, we're going to want more regularization. And so we're going to pass in something called P's. This is going to provide dropout. And also this one here, emb_drop. This is going to provide embedding dropout. So let's learn about what is dropout. But the short version is dropout is a kind of regularization. This is the dropout paper. Nitish, how do you say this? Srivastava. It was Srivastava's master's thesis under Geoffrey Hinton. And this picture from the original paper is a really good picture of what's going on. This first picture is a picture of a standard fully connected network. It's a picture of this. And what each line shows is a multiplication of an activation times a weight. And then when you've got multiple arrows coming in, that represents a sum. So this activation here is the sum of all of these inputs times all of these activations. So that's what a normal fully connected neural net looks like. For dropout, we throw that away. At random, we throw away some percentage of the activations. Not the weights, right? Not the parameters. Remember, there's only two types of number in a neural net. Parameters, also called weights, kind of, and activations. So we're going to throw away some activations. So you can see that when we throw away this activation, all of the things that were connected to it are gone too. Okay? For each mini batch, we throw away a different subset of activations. How many do we throw away? We throw them each one away with a probability p. A common value of p is 0.5. So what does that mean? And you'll see in this case, not only have they deleted at random some of these hidden layers, but they've actually deleted some of the inputs as well. Deleting the inputs is pretty unusual. Normally, we only delete activations in the hidden layers. So what does this do? Well, every time I have a mini batch going through, I, at random, throw away some of the activations. And then the next mini batch, I put them back, and I throw away some different ones. Okay. So it means that no one activation can kind of memorize some part of the input. Because that's what happens if we overfit, right? If we overfit, some part of the model is basically learning to recognize a particular image rather than a feature in general or a particular item. With dropout, it's going to be very hard for it to do that. In fact, Geoffrey Hinton described one of the kind of part of the thinking behind this as follows. He said he noticed every time he went to his bank that all the tellers and staff moved around. And he realized the reason for this must be that they're trying to avoid fraud. If they keep moving them around, nobody can specialize so much in that one thing that they're doing that they can figure out kind of a conspiracy to defraud the bank. Now, of course, depends when you ask Hinton. At other times, he says that the reason for this was because he thought about how spiking neurons work. And there's a view, he's a neuroscientist by training, there's a view that spiking neurons might help regularization, and dropout is kind of a way of matching this idea of spiking neurons. I mean, it's interesting. When you actually ask people, where did your idea for some algorithm come from? It basically never comes from math. It always comes from intuition and kind of thinking about physical analogies and stuff like that. So anyway, the truth is a bunch of ideas, I guess, were all flowing around and they came up with this idea of dropout. But the important thing to know is it worked really, really well, right? And so we can use it in our models to get generalization for free. Now, too much dropout, of course, is reducing the capacity of your model, so it's going to underfit. And so you've got to play around with different dropout values for each of your layers to decide. So in pretty much every FastAI learner, there's a parameter called PS, which will be the P value for the dropout for each layer. So you can just pass in a list. Or you can pass in an int, and it'll create a list with that value everywhere. Sometimes it's a little different for CNN, for example. It actually, if you pass in an int, it will use that for the last layer and half that value for the earlier layers. We basically try to do things that kind of represent best practice. But you can always pass in your own list to get exactly the dropout that you want. There is an interesting feature of dropout, which is that we talk about training time and test time. Test time we also call inference time. Training time is when we're actually doing those weight updates, the backpropagation. In the training time, dropout works the way we just saw. At test time, we turn off dropout. Right? We're not going to do dropout anymore because we want it to be as accurate as possible. We're not training, so we can't cause it to overfit when we're doing inference. So we remove dropout. But what that means is if previously P was 0.5, then half the activations were being removed, which means when they're all there, now our overall activation level is twice what it used to be. And so therefore in the paper they suggest multiplying all of your weights at test time by p. Interestingly, you can dig into the PyTorch source code and you can find the actual C code where dropout is implemented. And here it is. And you can see what they're doing is something quite interesting. They first of all do a Bernoulli trial. So a Bernoulli trial is with a probability 1 minus p, return the value 1, otherwise return the value 0. That's all it means. Okay? So in this case, p is the probability of dropout. So 1 minus p is the probability that we keep the activation. So we end up here with either a 1 or a 0. Right? And then, this is interesting, we divide in place, remember underscore means in place in PyTorch, we divide in place that 1 or 0 by 1 minus p. If it's a 0, nothing happens, it's still 0. If it's a 1 and p was 0.5, that 1 now becomes 2. And then finally we multiply in place our input by this noise, this dropout mask. So in other words, we actually don't do, in PyTorch, we don't do the change at test time. We actually do the change at training time, which means that you don't have to do anything special at inference time with PyTorch. It's not just PyTorch, it's quite a common pattern. But it's kind of nice to look inside the PyTorch source code and see, you know, dropout, this incredibly cool, incredibly valuable thing, is really just these 3 lines of code, which they do in C because I guess it ends up a bit faster when it's all fused together, but lots of libraries do it in Python and that works well as well. You can even write your own dropout layer and it should give exactly the same results as this. So that'd be a good exercise to try. See if you can create your own dropout layer in Python and see if you can replicate the results that we get with this dropout layer. So that's dropout. And so in this case, we're going to use a tiny bit of dropout on the first layer and a little bit of dropout on the next layer. And then we're going to use special dropout on the embedding layer. Now, why do we use special dropout on the embedding layer? So if you look inside the FastAI source code, here's our tabular model. You'll see that in the section that checks that there's some embeddings, we call each embedding, and then we concatenate the embeddings into a single matrix, and then we call embedding dropout. And embedding dropout is simply just a dropout, right? So it's just an instance of a dropout module. This kind of makes sense, right? For continuous variables, that continuous variable is just in one column. You wouldn't want to do dropout on that because you're literally deleting the existence of that whole input, which is almost certainly not what you want. But for an embedding is just effectively a matrix multiply by a one-hot encoded matrix. So it's just another layer. So it makes perfect sense to have dropout on the output of the embedding because you're putting dropout on those activations of that layer. And so you're basically saying, let's delete at random some of the results of that embedding, some of those activations. So that makes sense. The other reason we do it that way is because I did very extensive experiments about a year ago where on this data set I tried lots of different ways of doing kind of everything. And you can actually see it here. I put it all in a spreadsheet, of course, Microsoft Excel, put them into a pivot table to summarize them all together. To find out kind of which different choices and hyperparameters and architectures worked well and worked less well. And then I created all these little graphs. And these are like little summary training graphs for different combinations of hyperparameters and architectures. And I found that there was one of them which ended up consistently getting a good predictive accuracy. The kind of bumpiness of the training was pretty low. And you can see it was just a nice, smooth curve. And so like this is an example of the kind of experiments that I do that end up in the FastAI library, right? So embedding dropout was one of those things that I just found worked really well. And basically the results of these experiments is why it looks like this rather than something else. Well, it's a combination of these experiments, but then why did I do these particular experiments? Well, because it was very influenced by what worked well in that Kaggle Prize winners paper. But there were quite a few parts of that paper I thought there were some other choices they could have made. I wonder why they didn't, and I tried them out and found out what actually works and what doesn't work as well, and found a few little improvements. So that's the kind of experiments that you can play around with as well when you try different models and architectures, different dropouts, layer numbers, number of activations, and so forth. So having created our learner, we can type learn.model to take a look at it. And as you would expect, in that there is a whole bunch of embeddings. Each of those embedding matrices tells you, well, this is the number of levels of the input for each input, right? And you can match these with your list cat vars, right? So the first one will be store. So that's not surprising. There are 1,116 stores. And then the second number, of course, is the size of the embedding. And that's a number that you get to choose. And so FastAI has some defaults which actually work really, really well nearly all the time. So I almost never change them. But when you create your tabular learner, you can absolutely pass in an embedding size dictionary, which maps variable names to embedding sizes for anything where you want to override the defaults. And then we've got our embedding dropout layer. And then we've got a batch norm layer with 16 inputs. Okay, the 16 inputs make sense because we have 16 continuous variables. The length of cont names is 16. So this is something for our continuous variables. And specifically, it's over here, bn cont on our continuous variables. And bn cont is a batch norm 1D. What's that? Well, the first short answer is it's one of the things that I experimented with as to having batch norm or not in this, and I found that it worked really well. And then specifically what it is extremely unclear. Let me describe it to you. It's kind of a bit of regularization. It's kind of a bit of training helper. It's called batch normalization. And it comes from this paper. Actually, before I do this, I just want to mention one other really funny thing. Dropout, I mentioned it was a master's thesis. Not only was it a master's thesis, one of the most influential papers of the last 10 years, it was rejected from the main neural nets conference, what was then called NIPS, now called NeurIPS. I think this is it's very interesting because it's just a reminder that, our academic community is generally extremely poor at recognizing which things are going to turn out to be important. Generally, people are looking for stuff that are in the field that they're working on and understand. So dropout kind of came out of left field. It's kind of hard to understand what's going on. And so that's kind of interesting. And so, it's a reminder that if you just follow, as you kind of develop it beyond being just a practitioner into actually doing your own research, don't just focus on the stuff everybody's talking about. Focus on the stuff you think might be interesting. Because the stuff everybody's talking about generally turns out not to be very interesting. The community is very poor at recognizing high impact papers when they come out. Batch normalization, on the other hand, was immediately recognized as high impact. I definitely remember everybody talking about it in 2015 when it came out. And that was because it was so obvious. They showed this picture showing the current, then state-of-the-art ImageNet model, Inception. This is how long it took them to get a pretty good result. And then they tried the same thing with this new thing called batch norm, and they just did it way, way, way quickly. And so that was enough for pretty much everybody to go, wow, this is interesting. And specifically, they said this thing's called batch normalization, and it's accelerating training by reducing internal covariate shift. So what is internal covariate shift? Well, it doesn't matter, because this is one of those things where researchers came up with some intuition and some idea about this thing they wanted to try, they did it, it worked well, they then post hoc added on some mathematical analysis to try and claim why it worked, and it turned out they were totally wrong. In the last 2 months, there's been 2 papers, so it took 3 years for people to really figure this out. In the last 2 months, there's been 2 papers that have shown batch normalization doesn't reduce covariate shift at all. And even if it did, that has nothing to do with why it works. So I think that's a kind of an interesting insight, again, which is like why we should be focusing on being practitioners and experimentalists and developing an intuition, right? What batch norm does is what you see in this picture here, in this paper. Here are steps or batches, right? And here is loss. And here, the red line is what happens when you train without batch norm. Very, very bumpy. And here the blue line is what happens when you train with batch norm. Not very bumpy at all. What that means is you can increase your learning rate with batch norm, because these big bumps represent times that you're really at risk of your set of weights jumping off into some awful part of the weight space that it can never get out of again. So if it's less bumpy, then you can train at a higher learning rate. So that's actually what's going on. And here's what it is. This is the algorithm. And it's really simple. The algorithm is going to take a mini batch, right? So we have a mini batch, and remember, this is a layer, so the thing coming into it is activations, okay? So it's a layer, and it's going to take in some activations. And so the activations, it's calling x1, x2, x3, and so forth. The first thing we do is we find the mean of those activations. Sum divided by the count, that's just the mean. And the second thing we do is we find the variance of those activations. Difference squared divided by the mean is the variance. And then we normalize. So the values minus the mean divided by the standard deviation is the normalized version. Okay, it turns out that bit's actually not that important. We used to think it was. Okay, but it turns out it's not. The really important bit is the next bit. We take those values and we add a vector of biases. They call it beta here. And we've seen that before. We've used a bias term before. Okay, so we're just going to add a bias term as per usual. And then we're going to use another thing that's a lot like a bias term, but rather than adding it, we're going to multiply by it. So there's these parameters gamma and beta, which are learnable parameters. Remember, in a neural net, there's only 2 kinds of number, activations and parameters. These are parameters. Okay, they're things that are learnt with gradient descent. This is just a normal bias layer, beta, and this is a multiplicative bias layer. Nobody calls it that, but that's all it is, right? It's just like bias, but we multiply rather than add. That's all batch norm is. That's what the layer does. So why is that able to achieve this fantastic result? I'm not sure anybody has exactly written this down before. If they have, I apologize for failing to cite it because I haven't seen it. But let me explain what's actually going on here. The value of our predictions y hat is some function of our various weights. There could be millions of them. Weight 1 million. And it's also a function, of course, of the inputs to our layer. This function here is our neural net function, whatever is going on in our neural net. And then our loss, let's say it's mean squared error, is just our actuals minus our predicted squared. Okay? So let's say we're trying to predict movie review outcomes, and they're between 1 and 5. Okay? And we've been trying to train our model, and the activations at the very end are currently between -1 and 1. So they're way off where they need to be. The scale is off, the mean is off. So what can we do? One thing we could do would be to try and come up with a new set of weights that cause the spread to increase and cause the mean to increase as well. But that's going to be really hard to do because remember, all these weights interact in very intricate ways, right? We've got all those nonlinearities and they all combine together. So to kind of just move up is going to require navigating through this complex landscape, and we use all these tricks like momentum and atom and stuff like that to help us, but it still requires a lot of twiddling around to get there. So that's going to take a long time, and it's going to be bumpy. But what if we did this? What if we went times G plus B? We added 2 more parameter vectors. Well, now it's really easy, right? In order to increase the scale, that number has a direct gradient to increase the scale. To change the mean, that number has a direct gradient to change the mean. There's no interactions or complexities, it's just straight up and down, straight in and out. And that's what batch norm does, right? So batch norm is basically making it easier for it to do this really important thing, which is to shift the outputs up and down and in and out. And that's why we end up with these results. So those details in some ways don't matter terribly. The really important thing to know is you definitely want to use it, right? Or if not it, something like it. There's various other types of normalization around nowadays, but batch norm works great. The other main normalization type we use in FastAI is something called weight norm, which is a much more, just in the last few months, development. Okay, so that's batch norm. And so what we do is we create a batch norm layer for every continuous variable. N cont is the number of continuous variables. In FastAI, n underscore something always means the count of that thing. Cont always means continuous. So then here is where we use it. We grab our continuous variables and we throw them through a batch norm layer. And so then over here, you can see it in our model. One interesting thing is this momentum here. This is not momentum like in optimization, but this is momentum as in exponentially weighted moving average. Specifically, this mean and standard deviation, we don't actually use a different mean and standard deviation for every mini batch. If we did, it would vary so much that it'd be very hard to train. So instead, we take an exponentially weighted moving average of the mean and standard deviation. Okay? And if you don't remember what I mean by that, look back at last week's lesson to remind yourself about exponentially weighted moving averages, which we implemented in Excel for the momentum and atom gradient squared terms. You can vary the amount of momentum in a batch norm layer by passing a different value to the constructor in PyTorch. If you use a smaller number, it means that the mean and standard deviation will vary less from mini batch to mini batch, and that will have less of a regularization effect. A larger number will mean the variation will be greater from mini batch to mini batch. That will have more of a regularization effect. So as well as this thing of training more nicely because it's parameterized better, this momentum term in the mean and standard deviation is the thing that adds this nice regularization piece. When you add batch norm, you should also be able to use a higher learning rate. So that's our model. So then you can go LR find, you can have a look, and then you can go fit, you can save it, you can plot the losses, you can fit a bit more, and we end up at 0.103. 10th place in the competition was 0.108, so it's looking good. All right. Again, take it with a slight grain of salt, because what you actually need to do is use the real training set and submit it to Kaggle. But you can see we're very much, amongst the kind of cutting edge of models, at least as of 2015. And as I say, there haven't really been any architectural improvements since then. There wasn't batch norm when this was around, so the fact we added batch norm means that we should get better results, and certainly more quickly. And if I remember correctly, in their model, they had to train at a lower learning rate for quite a lot longer. As you can see, this is about less than 45 minutes of training. So that's nice and fast. Any questions?
In what proportion would you use dropout versus other regularization errors like weight decay, L2 norms, etc.?
So remember that L2 regularization and weight decay are kind of two ways of doing the same thing. And we should always use the weight decay version, not the L2 regularization version. So there's weight decay, there's batch norm, which kind of has a regularizing effect. There's data augmentation, which we'll see soon, and there's dropout. So batch norm we pretty much always want, so that's easy. Data augmentation we'll see in a moment. So then it's really between dropout versus weight decay. I have no idea. I don't think I've seen anybody provide a compelling study of how to combine those two things. Can you always use one instead of the other? Why not? I don't think anybody has figured that out. I think in practice, it seems that you generally want a bit of both. You pretty much always want some weight decay, but you often also want a bit of dropout. But honestly, I don't know why. And I've not seen anybody really explain why or how to decide. So this is one of these things you have to try out and kind of get a feel for what tends to work for your kinds of problems. I think the defaults that we provide in most of our learners should work pretty well in most situations. But yeah, definitely play around with it. Okay, the next kind of regularization we're going to look at is data augmentation. And data augmentation is one of the least well-studied types of regularization, but it's the kind that I think I'm kind of the most excited about. The reason I'm kind of the most excited about it is that there's basically almost no cost to it. You can do data augmentation and get better generalization without it taking longer to train, without underfitting, to an extent, at least. So let me explain. So what we're going to do now is we're going to come back to computer vision, and we're going to come back to our pets data set again. So let's load it in. All right, our pets data set, the images were inside the images subfolder. And I'm going to call get transforms as per usual. But when we call get transforms, there's a whole long list of things that we can provide. And so far, we haven't been varying that much at all. But in order to really understand data augmentation, I'm going to kind of ratchet up all of the defaults. So there's a parameter here for what's the probability of an affine transform happening, what's the probability of a lighting transform happening. So I set them both to 1. So they're all going to get transformed. They're going to do more rotation, more zoom, more lighting transforms, and more warping. What do all those mean? Well, you should check the documentation. And you do that by typing doc. And there's the brief documentation, but the real documentation is in docs. So I'll click on show in docs. And here it is. Right? And so this tells you what all of those do. But generally the most interesting parts of the docs tend to be at the top, where you kind of get the summaries of what's going on. And so here there's something called list of transforms. And here you can see every transform has something showing you lots of different values of it, right? So here's brightness. So make sure you read these. And remember, these notebooks, you can open up and run this code yourself and get this output. All of these HTML documentation documents are auto-generated from the notebooks in the docs_source directory in the FastAI repo, right? So you will see the exact same cats if you try this. Sylvain really likes cats, so there's a lot of cats in the documentation. And I think, because he's been so awesome at creating great documentation, he gets to pick the cats. So, for example, looking at different values of brightness, what I do here is I look to see two things. The first is, for which of these levels of transformation is it still clear what the picture is a picture of? So this is kind of getting to a point where it's pretty unclear. This is possibly getting a little unclear. The second thing I do is I look at the actual data set that I'm modeling, or particularly the data set that I'll be using as validation set, and I try to get a sense of what the variation in this case in lighting is. So if they're like nearly all professionally taking photos, I would probably want them all to be about in the middle. But if the kind of their photos that are taken by some pretty amateur photographers, there are likely to be some that are very overexposed, some very underexposed, right? So you should pick a value of this data augmentation for brightness that both allows the image to still be seen clearly and also represents the kind of data that you're going to be using this to model on in practice. So you've got to say the same thing for contrast, right? It would be unusual to have a data set with such ridiculous contrast, but perhaps you do, in which case you should use data augmentation up to that level. But if you don't, then you shouldn't. This one called dihedral is just one that does every possible rotation and flip. And so obviously most of your pictures are not going to be upside down cats. Right? So you probably would say, hey, this doesn't make sense. I won't use this for this data set. But if you were looking at satellite images, of course you would. On the other hand, flip makes perfect sense. So you would include that. A lot of things that you can do with FastAI lets you pick a padding mode. And this is what padding mode looks like. You can pick zeros. You can pick border, which just replicates. Or you can pick reflection, which as you can see is it's as if the last little few pixels are in a mirror. Reflection's nearly always better, by the way. I don't know that anybody else has really studied this, but we have studied it in some depth. Haven't actually written a paper about it, but just enough for our own purposes to say reflection works best most of the time. So that's the default. Then there's a really cool bunch of perspective warping ones, which I'll probably show you by using symmetric warp. If you look at the kind of we've added black borders to this, so it's more obvious for what's going on. And as you can see, what symmetric warp is doing, it's as if the camera is being moved above or to the side of the object and literally warping the whole thing like that, right? And so the cool thing is that as you can see, each of these pictures, it's as if this cat was being taken kind of from different angles, right? So they're all kind of optically sensible, right? And so this is a really great type of data augmentation. It's also one which I don't know of any other library that does it, or at least certainly one that does it in a way that's both fast and keeps the image crisp, as it is in FastAI. So this is like, if you're looking to win a Kaggle competition, this is the kind of thing that's going to like get you above the people that aren't using the FastAI library. So having looked at all that, we are going to add this, have a little get data function that just does the usual data block stuff, but we're going to add padding mode explicitly so that we can turn on padding mode of zeros, just so we can see what's going on better. FastAI has this handy little function called plot multi, which is going to create a 3x3 grid of plots, and each one will contain the result of calling this function, which will receive the plot coordinates and the axis. And so I'm actually going to plot the exact same thing in every box, but because this is a training data set, it's going to use data augmentation. And so you can see the same doggy using lots of different kinds of data augmentation. And so you can see why this is going to work really well, because these pictures all look pretty different, right? But we didn't have to do any extra hand labeling or anything. It's like free extra data. Okay? So data augmentation is really, really great. And one of the big opportunities for research is to figure out ways to do data augmentation in other domains. So how can you do data augmentation with text data, or genomic data, or histopathology data, or whatever, right? Almost nobody's looking at that, and to me it's one of the biggest opportunities that could let you decrease data requirements by like 5 to 10x. So here's the same thing again, but with reflection padding instead of zero padding, and you can kind of see, like see this doggy's legs are actually being reflected at the bottom here. So reflection padding tends to create images that are kind of much more naturally reasonable. Like in the real world, you don't get black borders like this. So they do seem to work better. Okay. So because we're going to study convolutional neural networks, we are going to create a convolutional neural network. You know how to create them, so I'll go ahead and create one. I will fit it for a little bit. I will unfreeze it. I will then create a larger version of the data set, 352 by 352, and fit for a little bit more. And I will save it. Okay, so we have a CNN, and we're going to try and figure out what's going on in our CNN. And the way we're going to try and figure it out is specifically that we're going to try to learn how to create this picture. This is a heat map, right? This is a picture which shows me what part of the image did the CNN focus on when it was trying to decide what this picture is. So we're going to make this heat map from scratch. Okay? So we're kind of at a point now in the course where I'm assuming that if you've got to this point, and you're still here, thank you, then you're interested enough that you're prepared to kind of dig into some of these details. So we're actually going to learn how to create this heat map without almost any fast AI stuff. We're going to use pure kind of tensor arithmetic in PyTorch, and we're going to try and use that to really understand what's going on. So to warn you, none of it's rocket science, but a lot of it's going to look really new. So don't expect to get it the first time, but expect to listen, jump into the notebook, try a few things, test things out, look particularly at tensor shapes and inputs and outputs to check your understanding, then go back and listen again, right? And kind of try it a few times because you will get there, right? It's just that there's going to be a lot of new concepts because we haven't done that much stuff in pure PyTorch. Okay, so what we're going to do is we're going to have a 7-minute break, and then we're going to come back and we're going to learn all about the innards of a CNN. So I'll see you at 7:50. So let's learn about convolutional neural networks. The funny thing is, it's pretty unusual to get close to the end of a course and only then look at convolutions. But when you think about it, knowing actually how batch norm works or how dropout works or how convolutions work isn't nearly as important as knowing how it all goes together and what to do with them and how to figure out how to do those things better. But it's, we're kind of at a point now where we want to be able to do things like that. And although, we're adding this functionality directly into the library, so you can kind of run a function to do that, the more you do, the more you'll find things that you want to do a little bit differently to how we do them. Or there'll be something in your domain where you think oh, I could do a slight variation of that. So you're kind of getting to a point in your experience now where it helps to know how to do more stuff yourself, and that means you need to understand what's really going on behind the scenes. So what's really going on behind the scenes is that we are creating a neural network that looks a lot like this, right? But rather than doing a matrix multiply here and here and here, we're actually going to do instead a convolution. And a convolution is just a kind of matrix multiply which has some interesting properties. You should definitely check out this website, satosa.io/ev, explained visually, where we have stolen this beautiful animation. It's actually a JavaScript thing that you can actually play around with yourself in order to show you how convolutions work. And it's actually showing you a convolution as we move around these little red squares. So here's a picture, a black and white or a grayscale picture, right? And so each 3x3 bit of this picture, as this red thing moves around, it shows you a different 3x3 part, right? It shows you over here the values of the pixels, right? So in FastAI's case, our pixel values are between 0 and 1. In this case, they're between 0 and 255, right? So here are 9 pixel values. This area is pretty white, so they're pretty high numbers, okay? And so as we move around, you can see the 9 big numbers change, and you can also see their colours change. Up here, there's another 9 numbers. And you can see those in the little x1, x2, x1. Here we are, 1, 2, 1. And what you might see going on is as we move this little red block, as these numbers change, we then multiply them by the corresponding numbers up here. And so let's start using some nomenclature. The thing up here we are going to call the kernel, the convolutional kernel. So we're going to take each little 3 by 3 part of this image, and we're going to do an element-wise multiplication of each of the 9 pixels that we're mousing over with each of the 9 items in our kernel. And so once we multiply each set together, we can then add them all up. And that is what's shown on the right. As the little bunch of red things move over there, you can see there's one red thing that appears over here. The reason there's one red thing over here is because each set of 9, after getting through the element-wise multiplication of the kernel, get added together to create one output. So therefore, the size of this image has 1 pixel less on each edge than the original, as you can see. See how there's black borders on it? That's because at the edge, the 3 by 3 kernel can't quite go any further, right? So the furthest you can go is to end up with a dot in the middle, just off the corner, right? So why are we doing this? Well, perhaps you can see what's happened. This face has turned into some white parts outlining the horizontal edges. How? Well, the how is just by doing this element-wise multiplication of each set of 9 pixels with this kernel, adding them together and sticking the result in the corresponding spot over here. Why is that creating white spots where the horizontal edges are? Well, let's think about it. Let's look up here. So if we're just in this little bit here, right, then the spots above it are all pretty white, so they have high numbers. So the bits above it are big numbers that are getting multiplied by 1, 2, 1. So that's going to create a big number. And the ones in the middle are all zeros, so don't care about that. And then the ones underneath are all small numbers because they're all close to 0, so that really doesn't do much at all. So therefore, that little set there is going to end up with bright white, right? Whereas on the other side, right, down here, you've got light pixels underneath, so they're going to get a lot of negative. Dark pixels on top, which are very small, so not much happens. So therefore, over here, we're going to end up with very negative. So this thing where we take each 3 by 3 area and element-wise multiply them with a kernel and add each of those up together to create one output is called a convolution. That's it. That's a convolution. So that might look familiar to you, right? Because what we did back a while ago is we looked at that Zeiler and Fergus paper where we saw like each different layer and we visualized what the weights were doing. And do you remember how the first layer was basically like finding diagonal edges and gradients? That's because that's all a convolution can do, right? Each of our layers is just a convolution. So the first layer can do nothing more than this kind of thing. But the nice thing is the next layer could then take the results of this, right? And it could kind of combine one channel. So the output of one convolutional filter is called a channel. Right? So it could take one channel that found top edges and another channel that finds left edges, and then the layer above that could take those two as input and create something that finds top left corners, as we saw when we looked at those Zeiler and Fergus visualizations. So let's take a look at this from another angle, or quite a few other angles, and we're going to look at a fantastic post from a guy called Matt Kleinsmith, who was actually a student in the first year that we did this course, and he wrote this as part of his project work back then. And what he's going to show here is our image. It's a 3 by 3 image, and our kernel is a 2 by 2 kernel. And what we're going to do is we're going to apply this kernel to the top left 2 by 2 part of this image, and so the pink bit will be correspondingly multiplied by the pink bit, the green by the green, and so forth. And they all get added up together to create this top left in the output. So, in other words, P equals alpha times A, beta times B, gamma times D, delta times E. There it is. Plus B, which is a bias. Okay, so that's fine. That's just a normal bias. So you can see how basically each of these output pixels is the result of some different linear equation. That makes sense? And you can see these same 4 weights are being moved around because this is our convolutional kernel. Here's another way of looking at it from Matt, which is, here is a classic neural network view. And so P now is a result of multiplying every one of these inputs by a weight and then adding them all together, except the grey ones are going to have a value of 0, right? Because remember, P was only connected to A, B, D, and E. A, B, D, and E. So in other words, remembering that this represents a matrix multiplication, therefore we can represent this as a matrix multiplication. So here is our list of pixels in our 3 by 3 image flattened out into a vector, and here is a matrix vector multiplication plus bias, and then a whole bunch of them we're just going to set to 0. Right? So you can see here we've got a 0, 0, 0, 0, 0, which corresponds to 0, 0, 0, 0, 0. So in other words, a convolution is just a matrix multiplication where 2 things happen. Some of the entries are set to 0 all the time, and all of the ones of the same color always have the same weight. So when you've got multiple things with the same weight, that's called weight tying. Okay? So, clearly, we could implement a convolution using matrix multiplication, but we don't because it's slow. Right? So in practice, our libraries have specific convolution functions that we use. And they're basically doing this, which is this equation, which is the same as this matrix multiplication. And, as we discussed, we have to think about padding, because if you have a 3 by 3 kernel and a 3 by 3 image, then that can only create 1 pixel of output. There's only one place that this 3 by 3 can go. So if we want to create more than 1 pixel of output, we have to do something called padding, which is to put additional numbers all around the outside. So what most libraries do is that they just put a layer of zeros, not a layer, a bunch of zeros all around the outside. So for a 3 by 3 kernel, a single 0 on every edge piece here. And so once you've padded it like that, you can now move your 3 by 3 kernel all the way across and give you the same output size that you started with. Okay? Now, as we mentioned in FastAI, we don't normally necessarily use zero padding. Where possible, we use reflection padding, although for these simple convolutions, we often use zero padding because it doesn't matter too much in a big image. It doesn't make too much difference. Okay, so that's what a convolution is. So a convolutional neural network wouldn't be very interesting if it can only create top edges. So we have to take it a little bit further. So if we have an input, and it might be, standard kind of red, green, blue picture. Right? Then we can create a kernel, a 3x3 kernel, like so. And then we could pass that kernel over all of the different pixels. But if you think about it, we actually don't have a 2D input anymore. We have a 3D input, a rank 3 tensor. So we probably don't want to use the same kernel values for each of red and green and blue. Because, for example, if we're creating a green frog detector, we would want more activations on the green than we would on the blue. Right? Or if we're trying to find something that can actually find a gradient that goes from green to blue, then the different kernels for each channel need to have different values in. So therefore, we need to create a 3x3x3 kernel. Okay, so this is still our kernel. And we're still going to vary it across the height and the width. But rather than doing an element-wise multiplication of 9 things, we're going to do an element-wise multiplication of 27 things. 3x3x3. And we're still going to then add them up into a single number. So as we pass this cube over this and the kind of like the little bit that's going to be sitting behind it, right? As we do that part of the convolution, it's still going to create just one number, because we do an element-wise multiplication of all 27 and add them all together. So we can do that across the whole padded, single unit padded input. And so we started with 1, 2, 3, 4, 5 by 5. So we're going to end up with an output that's also 5 by 5. Right? But now, our input was 3 channels, and our output is only 1 channel. Now, we're not going to be able to do very much with just 1 channel, because all we've done now is found a top edge. How are we going to find a side edge, and a gradient, and an area of constant white? Well, we're going to have to create another kernel. And we're going to have to do that convolved over the input, and that's going to create another 5 by 5. And then we can just stack those together across this as another axis, and we can do that lots and lots of times, and that's going to give us another rank 3 tensor output. So that's what happens in practice. Right? In practice, we start with an input which is H by W by, for images, 3. We pass it through a bunch of convolutional kernels, right? And we can pick how many we want, and it gives us back an output of, height by width by however many kernels we had. And so often that might be something like 16 in the first layer. And so now we've got 16 channels, they're called. 16 channels representing things like how much left edge was on this pixel, how much top edge was in this pixel, how much blue to red gradient was on this, well, this set of 9 pixels each with RGB. And so then you can just do the same thing, right? You can have another bunch of kernels. And that's going to create another output, rank 3 tensor. Again, height by width by whatever, might still be 16. Now what we really like to do is, as we get deeper in the network, we actually want to have more and more channels. We want to be able to find like a richer and richer set of features, so that after a few, as we saw in the Zeiler and Fergus paper, by layer 4 or 5, we've kind of got eyeball detectors and fur detectors and things, right? So we really need a lot of channels. So in order to avoid our memory going out of control, from time to time, we create a convolution where we don't step over every single set of 3 by 3, but instead we skip over 2 at a time. So we would start with a 3 by 3 centered at 2, 2, and then we'd jump over to 2, 4, 2, 6, 2, 8, and so forth. And that's called a stride 2 convolution. And so what that does is it looks exactly the same, right? It's still just a bunch of kernels. But we're just jumping over 2 at a time, right? We're skipping every alternate input pixel. And so the output from that will be h over 2 by w over 2. And so when we do that, we generally create twice as many kernels. So we can now have, say, 32 activations in each of those spots. And so that's what modern convolutional neural networks kind of tend to look like, right? And so we can actually see that if we go into our pets and we grab our CNN, right? And we're going to take a look at this particular cat. So if we go x, y equals valid data set, some index, so let's grab the 0th. We'll go .show, and we'll print out the value of y. Apparently this cat is of category Maine Coon. So until a week ago, I was not at all familiar that there's a cat called a Maine Coon. Having spent all week with this particular cat, I am now deeply familiar with this Maine Coon. So we can, if we go learn.summary, remember that our input we asked for was 352 by 352 pixels. Generally speaking, the very first convolution tends to have a stride 2. So after the first layer, it's 176 by 176. So this is learn.summary. We'll print out for you the output shape after every layer. 176 by 176. And the first set of convolutions has 64 activations. And we can actually see that if we type in learn.model, you can see here it's a 2D conv with 3 input channels and 64 output channels and a stride of 2. Right? And interestingly, it actually starts with a kernel size of 7 by 7. So like nearly all of the convolutions are 3 by 3. See, they're all 3 by 3. Right? For reasons we'll talk about in part 2, we often use a larger kernel for the very first one. If you use a larger kernel, you have to use more padding. So we have to use kernel size int divide by 2 padding to make sure we don't lose anything. Anyway, so we now have 64 output channels, and since it was stride 2, it's now 176 by 176. And then, as we go along, you'll see that from time to time, we go from 88 by 88 to 40 by 44, the grid size, so that was a 2D conv. And then when we do that, we generally double the number of channels. So we keep going through a few more convs, and as you can see, they've got batch norm and ReLU. That's kind of pretty standard. And eventually we do it again, another stride 2 conv, which again doubles. Okay, we've now got 512 by 11 by 11. And that's basically where we finish the main part of the network. We end up with 512 channels, 11 by 11. Okay. So we're actually at a point where we're going to be able to do this heat map now. So let's try and work through it. Before we do, I want to show you how you can do your own manual convolutions, because it's kind of fun. So we're going to start with this picture of a Maine Coon, and I've created a convolutional kernel. And so as you can see, this one has a right edge and a bottom edge with positive numbers. And just inside that, it's got negative numbers. So I'm thinking this should show me bottom right edges. Okay. So that's my tensor. Now, one complexity is that 3 by 3 kernel cannot be used for this purpose because I need two more dimensions. The first is I need the third dimension to say how to combine the red, green, and blue. So what I do is I say dot expand, this is my 3 by 3, and I pop another 3 on the start. What dot expand does is it says create a 3 by 3 by 3 tensor by simply copying this one 3 times. I mean, honestly, it doesn't actually copy it. It pretends to have copied it, you know, but it just basically refers to the same block of memory. So it kind of copies it in a memory efficient way. So this one here is now 3 copies of that. And the reason for that is that I want to treat red and green and blue the same way for this little manual kernel I'm showing you. And then we need one more axis, because rather than actually having a separate kernel, like I kind of printed these as if they were multiple kernels, what we actually do is we use a rank 4 tensor. And so the very first axis is for the every separate kernel that we have. So in this case, I'm just going to create one kernel. So to do a convolution, I still have to put this unit axis on the front. So you can see k dot shape is now 1, 3, 3, 3. So it's a 3 by 3 kernel. There are 3 of them, and then that's just the one kernel that I have. So it kind of takes a while to get the feel for these higher dimensional tensors because we're not used to writing out a 4D tensor. But like, just think of them like this. A 4D tensor is just a bunch of 3D tensors sitting on top of each other. Okay? So this is our 4D tensor, and then you can just call conv2D, passing in some image, and so the image I'm going to use is the first part of my validation data set and the kernel. There's one more trick, which is that in PyTorch, pretty much everything is expecting to work on a mini batch, not on an individual thing. Okay, so in our case, we have to create a mini batch of size 1. So our original image is 3 channels by 352 by 352, height by width. Right? So remember, PyTorch is channel by height by width. I want to create a mini, so I need to create a rank 4 tensor where the first axis is 1. In other words, it's a mini batch of size 1, because that's what PyTorch expects. So there's something you can do in both PyTorch and NumPy, which is you can index into an array or a tensor with a special value none, and that creates a new unit axis in that point. So T is my image of dimensions 3 by 352 by 352. T none is a rank 4 tensor, a mini batch of 1 image of 1 by 3 by 352 by 352. And so now I can go conv2D and get back my cat, specifically my Maine Coon. Okay, so that's how you can play around with convolutions yourself. So how are we going to do this to create a heat map? This is where things get fun. Remember what I mentioned was that I basically have like my input, red, green, blue, and it goes through a bunch of convolutional layers. I'll just write a little line to say a convolutional layer to create activations which have more and more channels and eventually less and less, smaller and smaller height by width. Until eventually, remember we looked at the summary, we ended up with something which was 11 by 11 by 512. Right? There's a whole bunch more layers that we skipped over. Now, there are 37 classes, because remember data.c is the number of classes we have. And we can see that at the end here, we end up with 37 features in our model. So that means that we end up with a probability for every one of the 37 breeds of cat and dog. So it's a vector of length 37. That's our final output that we need, because that's what we're going to compare implicitly to our one-hot encoded matrix, which will have a 1 in the location for Maine Coon. Okay? So somehow we need to get from this 11 by 11 by 512 to this 37. And so the way we do it is we actually take the average of every one of these 11 by 11 faces. We just take the mean. So we're going to take the mean of this first face, take the mean, that gives us one value. And then we'll take the second of the 512 faces and take that mean, and that'll give us one more value. Right? So we're going to do that for every face, and that will give us a 512 long vector. Okay? And so now, all we need to do is pop that through a single matrix multiply of 512 by 37. And that's going to give us an output vector of length 37. Okay? So this step here, where we take the average of each face, is called average pooling. So let's go back to our model and take a look. Here it is. Here is our final 512. And here is, we'll talk about what a concat pooling is in part 2. For now, we'll just focus on this is a fast AI specialty. Everybody else just does this. Average pool. Average pool 2D with an output size of 1. So here it is. Output, average pool 2D with an output size of 1. And then, again, there's a bit of a special fast AI thing that we actually have 2 layers here, but normally people then just have the one linear layer with the input of 512 and the output of 37. Okay, so what that means is that this little box over here, where we want a 1 for Maine Coon, we've got to have a box over here which needs to have a high value in that place so that the loss will be low. So if we're going to have a high value there, the only way to get it is with this matrix multiplication, is that it's going to represent a simple weighted linear combination of all of the 512 values here. So if we're going to be able to say, I'm pretty confident this is a Maine Coon, just by taking the weighted sum of a bunch of inputs, those inputs are going to have to represent features like how fluffy is it? What color is its nose? How long is its legs? How pointy are its ears? You know, all the kinds of things that can be used, because for the other thing which figures out, is this a bulldog, it's got to use exactly the same kind of 512 inputs with a different set of weights, because that's all a matrix multiplication is, right? It's just a bunch of weighted sums, a different weighted sum for each output. Okay? So therefore, we know that this, you know, potentially dozens or even hundreds of layers of convolutions must have eventually come up with an 11 by 11 face for each of these features, saying, in this little bit here, how much is that part of the image like a pointy ear? How much is it fluffy? How much is it like a long leg? How much is it like a very red nose? Right? So that's what all of those things must represent. So each face is what we call, each of these represents a different feature. Right? So the outputs of these we can think of as different features. So what we really want to know then is not so much what's the average across the 11 by 11 to get this set of outputs, but what we really want to know is what's in each of these 11 by 11 spots. So what if instead of averaging across the 11 by 11, let's instead average across the 512. If we average across the 512, that's going to give us a single 11 by 11 matrix. And each item, each grid point in that 11 by 11 matrix will be the average of how activated was that area. When it came to figuring out that this was a Maine Coon, how many signs of Maine Coonishness was there in that part of the 11 by 11 grid? And so that's actually what we do to create our heat map. So I think maybe the easiest way is to kind of work backwards. Here's our heat map. And it comes from something called average activations. And it's just a little bit of matplotlib and fastai. Fastai to show the image, and then matplotlib to take the heat map, which we passed in, which was called average activations, HM for heat map. Alpha 0.6 means make it a bit transparent. In matplotlib, extent means expand it from 11 by 11 to 352 by 352. Use bilinear interpolation so it's not all blocky, and use a different color map to kind of highlight things. So that's just some matplotlib, it's not important. The key thing here is that average activations is the 11 by 11 matrix we wanted. Here it is, average activations.shape is 11 by 11. So to get there, we took the mean of activations across dimension 0, which is what I just said. In PyTorch, the channel dimension is the first dimension. So the mean across dimension 0 took us from something of size 512 by 11 by 11, as promised, to something of 11 by 11. So therefore, activations, acts, contains the activations we're averaging. Where did they come from? They came from something called a hook. So a hook is a really cool, more advanced PyTorch feature that lets you, as the name suggests, hook into the PyTorch machinery itself and run any arbitrary Python code you want to. It's a really amazing and nifty thing. Because, you know, normally when we do a forward pass through a PyTorch module, it gives us this set of outputs. But we know that in the process, it's calculated these. So what I would like to do is I would like to hook into that forward pass and tell PyTorch, hey, when you calculate this, can you store it for me, please? Okay, so what is this? This is the output of the convolutional part of the model. So the convolutional part of the model, which is everything before the average pool, is basically all of that. Right? And so thinking back to transfer learning, right? You remember with transfer learning, we actually cut off everything after the convolutional part of the model and replaced it with our own little bit, right? So with FastAI, the original convolutional part of the model is always going to be the first thing in the model. And specifically, it's always going to be called, so in this case, I'm taking my model and I'm just going to call it M, right? So you can see M is this big thing, but always, at least in FastAI, always M0 will be the convolutional part of the model. So in this case, we created a, let's go back and see, we created a ResNet 34. So the main part of the ResNet 34, the pre-trained bit we hold on to is in M0, and so this is basically it. This is the printout of the ResNet 34, and at the end of it, there is the 512 activations. So in other words, what we want to do is we want to grab M0 and we want to hook its output. So this is a really useful thing to be able to do. So FastAI has actually created something to do it for you, which is literally you say hook, output, and you pass in the PyTorch module that you want to hook the output of. And so most likely the thing you'll want to hook is the convolutional part of the model, and that's always going to be M0 or learn.model0. So we give that hook a name. Don't worry about this part, we'll learn about it next week. So having hooked the output, we now need to actually do the forward pass, right? And so remember, in PyTorch, to actually get it to calculate something, which is called doing the forward pass, you just act as if the model is a function, right? So we just pass in our x mini batch. So we already had a main coon image called x, right? But we can't quite pass that into our model. It has to be normalized and turned into a mini batch and put onto the GPU. So FastAI has a thing called a data bunch, which we have in data, and you can always say data.oneItem to create a mini batch with one thing in it. Okay, and as an exercise at home, you could try to create a mini batch without using data.oneItem to make sure that you kind of learn how to normalize and stuff yourself if you want to. But this is how you can create a mini batch with just one thing in it, and then I can pop that onto the GPU by saying .CUDA. And that's what I pass to my model. And so the predictions I get out, I actually don't care about, right? Because the predictions is this thing, which is not what I want, right? So I'm not actually going to do anything with the predictions. The thing I care about is the hook that I just created. Now, one thing to be aware of is that when you hook something in PyTorch, that means every single time you run that model, assuming you're hooking outputs, it's storing those outputs. And so you want to remove the hook when you've got what you want, because otherwise if you use the model again, it's going to keep hooking more and more outputs, which will be slow and memory intensive. So we've created this thing, Python calls it a context manager. You can use any hook as a context manager. At the end of that with block, it'll remove the hook, okay? So we've got our hook, and so now PyTorch hooks, FastAI hooks always give you something called, or at least the output hooks, always give you something called .stored, which is where it stores away the thing you asked it to hook. And so that's where the activations now are. Okay, so we did a forward pass after hooking the output of the convolutional section of the model. We grabbed what it stored. We checked the shape. It was 512 by 11 by 11, as we predicted. We then took the mean of the channel axis to get an 11 by 11 tensor. And then, if we look at that, that's our picture. So there's a lot to unpack, right? A lot to unpack. But if you take your time going through these two sections, the convolution kernel section and the heat map section of this notebook, like running those lines of code and changing them around a little bit, and remember, the most important thing to look at is shape. You might have noticed when I'm showing you these notebooks, I very often print out the shape. And when you look at the shape, you want to be looking at how many axes are there, that's the rank of the tensor, and how many things are there in each axis, and try and think why, right? Try going back to the printout of the summary, try going back to the actual list of the layers, and try and go back and think about the actual picture we drew, and think about what's actually going on. Okay. So that's a lot of technical content. So what I'm going to do now is switch from technical content to something much more important, unless we have some questions first. Okay, because in the next lesson, we're going to be looking at generative models, both text and image generative models. And generative models are where you can create a new piece of text or a new image or a new video or a new sound. And as you probably are aware, this is the area that deep learning has developed the most in the last 12 months. And we're now at a point where we can generate realistic looking videos, images, audio, and to some extent even text. And so there are many things in this journey which have ethical considerations, but perhaps this area of generative modeling is one of the largest ones. So before I got into it, I wanted to specifically touch on ethics and data science. Most of the stuff I'm showing you actually comes from Rachel, and Rachel has a really cool TEDx San Francisco talk that you can check out on YouTube, and a more extensive analysis of ethical principles and bias principles in AI, which you can find at this talk here. And she has a playlist that you can check out. We've already touched on an example of bias, which was this gender shades study, where if you remember, for example, lighter male skinned people on IBM's main computer vision system are 99.7% accurate, and darker females are some hundreds of times less accurate in terms of error. So like extraordinary differences. And so it's interesting to kind of like, okay, it's first of all important to be aware that not only can this happen technically, but this can happen on a massive company's rolled out, publicly available, highly marketed system that hundreds of quality control people have studied and lots of people are using, right? It's out there in the wild. They all look kind of crazy, right? And so it's interesting to think about why. And so one of the reasons why is that the data we feed these things, right? We tend to use, me included, a lot of these data sets kind of unthinkingly, right? But like ImageNet, which is the basis of like a lot of the computer vision stuff we do, is over half American and Great Britain, right? Like when it comes to the countries that actually have most of the population in the world, I can't even see them here. They're somewhere in these impossibly thin lines. Because remember, these data sets are being created almost exclusively by people in US, Great Britain, and nowadays increasingly also China. So there's a lot of bias in the content we're creating because of a bias in the kind of people that are creating that content, even when, in theory, it's being created in a very kind of neutral way. But you can't argue with the data, right? It's obviously not neutral at all. And so when you have biased data creating biased algorithms, you then need to say, like, well, what are we doing with that? So we've spent a lot of time talking about image recognition. So a couple of years ago, this company, Deep Learning, advertised their image recognition system, which can be used to do mass surveillance on large crowds of people. Find any person passing through who is a person of interest in theory. And so putting aside even the question of like, is it a good idea to have such a system? You've got to think, is it a good idea to have such a system where certain kinds of people are 300 times more likely to be misidentified? And then thinking about it, so this is now starting to happen in America, right, where these systems are being rolled out. And so there are now systems in America that will identify a person of interest in a video and send a ping to the local police. And so these systems are extremely inaccurate and extremely biased. And what happens then, of course, is if you're in a predominantly black neighborhood where the probability of successfully recognizing you is much lower, and you're much more likely to be surrounded by black people, and so suddenly all of these black people are popping up as persons of interest, or in a video of a person of interest, or the people in the video are all recognized as in the vicinity as a person of interest, you suddenly get all these pings going off the local police department, causing the police to run down there, and therefore likely to lead to a larger number of arrests, which is then likely to feed back into the data being used to develop the systems. So this is happening right now. And so, like, thankfully, a very small number of people are actually bothering to look into these things. I mean, ridiculously small, but at least it's better than nothing. And so, for example, and one of the best ways that people get publicity is to do kind of funny experiments like, let's try the mugshot image recognition system that's being widely used and try it against the members of Congress and find out that there are 28 members of Congress who would have been identified by this system. Obviously, incorrectly. Oh, I didn't know that. Okay, black members of Congress. Not at all surprised to hear that. Thank you, Rachel. We see this kind of bias in a lot of the systems we use, not just image recognition, but text translation. When you convert she as a doctor, he as a nurse, into Turkish, you quite correctly get a gender-inspecific pronoun, because that's what Turkish uses. You could then take that and feed it back into Turkish with your gender-inspecific pronoun, and you will now get he is a doctor, she is a nurse. So the bias, again, this is in a massively widely rolled out, carefully studied system. And it's not like even these kind of things, like little one-off things that then get fixed quickly. These issues have been identified in Google Translate for a very long time, and they're still there, and they don't get fixed. So the kind of results of this are, in my opinion, quite terrifying. Because what's happening is that in many countries, including America, where I'm speaking from now, algorithms are increasingly being used for all kinds of public policy, judicial, and so forth purposes. For example, there's a system called Compass, which is very widely used to decide who's going to jail. And it does that in a couple of ways. It tells judges what sentencing guidelines they should use for particular cases, and it tells them also which people the system says should be let out on bail. But here's the thing. White people, it keeps on saying, let this person out, even though they end up reoffending, and vice versa. It's systematically like out by double compared to what it should be in terms of getting it wrong with white people versus black people. So this is like kind of horrifying because, I mean, amongst other things, the data that it's using in this system is literally asking people questions about things like, did any of your parents ever go to jail? Do any of your friends do drugs? Like, they're asking questions about other people who they have no control over. So not only are these systems biased, very systematically biased, but they're also being done on the basis of data which is totally out of your control. So this is kind of, did you want to add something to that? Oh yeah, are your parents divorced is another question that's being used to decide whether you go to jail or not. Right? So when we raise these issues kind of on Twitter or in talks or whatever, there's always a few people, always white men, a few people who will always say like, that's just the way the world is. That's just reflecting what the data shows. But when you actually look at it, it's not, right? It's actually systematically erroneous, and systematically erroneous against people of color, minorities, the people who are less involved in creating the systems that these products are based on. Sometimes this can go a really long way. So, for example, in Myanmar, there was a genocide of the Rohingya people. And that genocide was very heavily created by Facebook. Not because anybody at Facebook wanted it. I mean, heavens no. I know a lot of people at Facebook. I have a lot of friends at Facebook. They're really trying to do the right thing, right? They're really trying to create a product that people like, but not in a thoughtful enough way. Because when you roll out something where literally in Myanmar, a country that most people didn't have, maybe half of people didn't have electricity until very recently, and you say, hey, you can all have free internet as long as it's just Facebook, you've got to think carefully about what you're doing, right? And then you use algorithms to feed people the stuff they will click on. And of course, what people click on is stuff which is controversial, stuff that makes their blood boil. So when they actually started asking the generals in the Myanmar army that were literally throwing babies onto bonfires, they were saying, we know that these are not humans. We know that they are animals because we read the news. We read the internet, right? And because this is the stories that the algorithms are pushing, right? And the algorithms are pushing the stories because the algorithms are good. They know how to create eyeballs, how to get people watching and how to get people clicking. And again, nobody at Facebook said, let's cause a massive genocide in Myanmar. They said, let's maximize the engagement of people in this new market on our platform, right? So they very successfully maximized engagement. Yes? Please.
It's important to note, people warned executives at Facebook how the platform was being used to incite violence as far back as 2013, 2014, 2015. In 2015, someone even warned executives that Facebook could be used in Myanmar in the same way that the radio broadcasts were used in Rwanda during the Rwandan genocide. And as of 2015, Facebook only had four contractors who spoke Burmese working for them. They really did not put many resources into the issue at all, even though they were getting very, very alarming warnings about it.
So, I mean, so why does this happen, right? A part of the issue is that ethics is complicated, and you will not find Rachel or I telling you how to do ethics. You know, how do you fix this? We don't know. We can just give you kind of things to think about, right? Another part of the problem we keep hearing is, it's not my problem. I'm just a researcher. I'm just a techie. I'm just building a data set. I'm not part of the problem. I'm part of this foundation that's far enough away that I can imagine that I'm not part of this, right? But, you know, if you're creating ImageNet, and you want it to be successful, you want lots of people to use it, you want lots of people to build products on it, lots of people to do research on top of it. If you're trying to create something that people are using, you want them to use, then please try to make it something that won't cause massive amounts of harm and doesn't have massive amounts of bias. And it can actually come back and bite you in the ass, right? The Volkswagen engineer who ended up actually encoding the thing that made them systematically cheat on their diesel emissions tests, on their pollution tests, ended up in jail. Not because it was their decision to cheat on the tests, but because their manager told them to write that code, and they wrote the code. And therefore, they were the ones that ended up being criminally responsible, and they were the ones that were jailed, right? So if you do, in some way, a shitty thing that ends up causing trouble, that can absolutely come back around and get you in trouble as well. Sometimes it can cause huge amounts of trouble. So if we go back to World War II, right, then this was one of the first great opportunities for IBM to show off their amazing tabulating system. And they had a huge client in Nazi Germany. And Nazi Germany used this amazing new tabulating system to encode all of the different types of Jews that they had in the country and all the different types of problem people. So Jews were 8, Gypsies were 12, then different outcomes were coded. Executions were 4, death in a gas chamber was 6. A Swiss judge ruled that IBM was actively involved facilitating the commission of these crimes against humanity, right? So there are absolutely plenty of examples of people building data processing technology that are directly causing deaths, sometimes millions of deaths, right? So we don't want to be one of those people. And so you might have thought, oh, you know, I'm just creating some data processing software, and somebody else is thinking I'm just a salesperson, and somebody else is thinking I'm just the biz dev person opening new markets, but it all comes together, right? So we need to care. And so one of the things we need to care about is getting humans back in the loop, right? And so when we pull humans out of the loop, is one of the first times that trouble happens. I don't know if you remember, I remember this very clearly when I first heard that Facebook was firing the human editors that were responsible for basically curating the news that ended up on the Facebook pages. And I got to say, at the time, I thought, that's a recipe for disaster. Because I've seen again and again that humans can be the person in the loop that can realize this isn't right. It's very hard to create an algorithm that can recognize this isn't right, or else humans are very good at that. And we saw that's what happened, right? After Facebook fired the human editors, the nature of stories on Facebook dramatically changed. Right? And you started seeing this proliferation of conspiracy theories, and the algorithms went crazy with recommending more and more controversial topics. And of course, that changed people's consumption behavior, causing them to want more and more controversial topics. So one of the really interesting places this comes in, and Cathy O'Neill, who's got a great book called Weapons of Math Destruction, thank you, Rachel, and many others have pointed out, is that what happens to algorithms is that they end up impacting people. For example, Compass sentencing guidelines go to a judge. Now, you can say the algorithm's very good. In Compass's case, it isn't. It actually turned out to be about as bad as random because it's a black box and all that. But even if it was very good, you could then say, well, the judge is getting the algorithm. Otherwise, they'd just be getting a person. People also give bad advice. So what? Humans respond differently to algorithms. It's very common, particularly for a human that is not very familiar with the technology themselves, like a judge, to see oh, that's what the computer says. The computer looked it up and it figured this out. Right? It's extremely difficult to get a non-technical audience to look at a computer recommendation and come up with a nuanced decision-making process. So what we see is that algorithms are often put into place with no appeals process. They're often used to massively scale up decision-making systems because they're cheap. And then the people that are using the outputs of those algorithms tend to give them more credence than they deserve because very often they're being used by people that don't have the technical competence to judge them themselves. So a great example, right, was here's an example of somebody who lost their healthcare. And they lost their healthcare because of an error in a new algorithm that was systematically failing to recognize that there are many people that need help with, was it Alzheimer's? Cerebral palsy and diabetes. Thanks, Rachel. And so this system, which had this error that was later discovered, was cutting off these people from the home care that they needed so that cerebral palsy victims no longer had the care they needed. So their life was destroyed, basically. And so when the person that created that algorithm with the error was asked about this and was specifically said, should they have found a better way to communicate the system, the strengths, the failures, and so forth, he said, yeah, I should probably also dust under my bed. That was the level of interest they had. And this is extremely common. I hear this all the time. And it's much easier to see it from afar and say, okay, after the problem's happened, I can see that that's a really shitty thing to say. But it can be very difficult when you're in the middle of it.
I just want to say one more thing about that example. And that's that this was a case where it was separate. There was someone who created the algorithm. Then I think different people implemented the software. And this is in use in over half of the 50 states. And then there was also the particular policy decisions made by that state. And so this is one of those situations where nobody felt responsible because the algorithm creators oh no, it's the policy decisions of the state that were bad, and the state can be oh no, it's the ones who implemented the software. And so everyone's just pointing fingers and not taking responsibility.
And, in some ways maybe it's unfair, but I would argue the person who is creating the data set and the person who is implementing the algorithm is the person best placed to get out there and say, hey, here are the things you need to be careful of, and make sure that they're a part of the implementation process. So we've also seen this with YouTube, right? It's similar to what happened with Facebook. And we're now we've heard examples of students watching the Fast AI courses who say, hey, Jeremy and Rachel, watching the Fast AI courses, really enjoyed them. And at the end of one of them, the YouTube autoplay fed me across to a conspiracy theory. And what happens is that once the system decides that you like the conspiracy theories, it's going to just feed you more and more. And then what happens is that... Yeah, please, go on.
Just briefly, you don't even have to like conspiracy theories. The goal is to get as many people hooked on conspiracy theories as possible, is what the algorithm is trying to do, kind of whether or not you've expressed interest.
Right. And so the interesting thing, again, is I know plenty of people involved in YouTube recommendation systems. None of them are wanting to promote conspiracy theories. But people click on them, right? And people share them. And what tends to happen is also people that are into conspiracy theories consume a lot more YouTube media. So it actually is very good at finding a market that watches a lot of hours of YouTube. And then it makes that market watch even more. So this is an example of a feedback loop. And the New York Times is now describing YouTube as perhaps the most powerful radicalizing instrument of the 21st century. Now I can tell you, my friends that worked on the YouTube recommendation system did not think they were creating the most powerful radicalizing instrument of the 21st century. And to be honest, most of them today, when I talk to them, still think they're not. They think it's all bullshit. You know, not all of them, but a lot of them now are at the point where they just feel like they're the victims here. People are unfairly, they don't get it. They don't understand what we're trying to do. It's very, very difficult when you're right out there in the heart of it. So you've got to be thinking from right at the start, what are the possible unintended consequences of what you're working on? And as the technical people involved, how can you get out in front and make sure that people are aware of them?
And I just also wanted to say that in particular, many of these conspiracy theories are promoting white supremacy. They're, kind of far-right ethno-nationalism, anti-science. And I think, maybe 5 or 10 years ago, I would have thought conspiracy theories are a more fringe thing, but we're seeing the kind of huge societal impact it can have for many people to believe these.
Yeah. And, partly it's you see them on YouTube all the time. It starts to feel a lot more normal. Right? So one of the things that people are doing to try to say like how to fix this problem is to explicitly get involved in talking to the people who might or will be impacted by the kind of decision-making processes that you're enabling. So for example, there was a really cool thing recently where literally statisticians and data scientists got together with people who had been inside the criminal system, i.e. had gone through the bail and sentencing process of criminals themselves, and talking to the lawyers who worked with them, and put them together with the data scientists, and actually kind of put together a timeline of how exactly does it work, and where exactly the places that there are inputs, and how do people respond to them, and who's involved. This is really cool, right? This is the only way for you as a kind of a data product developer to actually know how your data product's going to be working. A really great example of somebody who did a great job here was Evan Estola at Meetup, who said, hey, a lot of men are going to our tech meetups, and if we use a recommendation system naively, it's going to recommend more tech meetups to men, which is going to cause more men to go to them, and then when women do try to go, they'll be like, oh my God, there's so many men here, which is going to cause more men to go to the tech meetups. Yeah, so showing recommendations to men and therefore not showing them to women. Yes, yeah. So what Evan and Meetup decided was to make an explicit product decision that this would not even be representing the actual true preferences of people. It would be creating a runaway feedback loop. So let's explicitly stop it, right, before it happens, and not recommend less meetups to women and tech meetups to women and more tech meetups to men. And so I think that's just, it's really cool. It's like it's saying we don't have to be slaves to the algorithm. We actually get to decide. Another thing that people can do to help is regulation. And normally when we kind of talk about regulation, there's a natural reaction of like, how do you regulate these things? That's ridiculous. You can't regulate AI. But actually when you look at it, again and again, and this fantastic paper called Data Sheets for Data Sets has lots of examples of this. There are many, many examples of industries where people thought they couldn't be regulated. People thought that's just how it was. Like cars, People died in cars all the time because they literally had sharp metal knobs on dashboards, steering columns weren't collapsible, and all of the discussion in the community was, that's just how cars are, and when people die in cars, it's because of the people. But then eventually the regulations did come in. And today, driving is dramatically safer, like dozens and dozens of times safer than it was before, right? So often there are things we can do through policy. So to summarize, we are part of the 0.3 to 0.5% of the world that knows how to code. Right? We have a skill that very few other people do. Not only that, we now know how to code deep learning algorithms, which is like the most powerful kind of code I know. Right? So I'm hoping that we can explicitly think about, like, at least not making the world worse and perhaps explicitly making it better. Right? And so why is this interesting to you as an audience in particular? And that's because FastAI in particular is trying to make it easy for domain experts to use deep learning. And so this picture of the goats here is an example of one of our international fellows from a previous course who was a goat dairy farmer and told us that they were going to use deep learning on their remote Canadian island to help study udder disease in goats. And to me, this is a great example of, like, a domain expert's problem which nobody else even knows about, let alone know that it's a computer vision problem that can be solved with deep learning. So in your field, whatever it is, you probably know a lot more now about the opportunities in your field to make it a hell of a lot better than it was before. You'll probably be able to come up with all kinds of cool product ideas, right? Maybe build a startup or create a new product group in your company or whatever. But also, please be thinking about what that's going to mean in practice, and think about, where can you put humans in the loop, right? Where can you put those pressure release valves? Who are the people you can talk to who could be impacted, who could help you understand, right? And get the kind of humanities folks involved to understand history and psychology and sociology and so forth. So that's our plea to you. If you've got this far, you're definitely at a point now where you're ready to, make a serious impact on the world. So I hope we can make sure that that's a positive impact. See you next week. Welcome to Lesson 7, the last lesson of Part 1. This will be a pretty intense lesson. And so don't let that bother you, because partly what I want to do is to kind of give you enough things to think about to keep you busy until Part 2. And so, in fact, some of the things we cover today, I'm not going to tell you about some of the details. I'll just point out a few things where I'll say, like, okay, that we're not talking about yet, we're not talking about yet. And so then come back in Part 2 to get the details on some of these extra pieces, right? So today will be a lot of material pretty quickly. It might require a few viewings to fully understand it all, a few experiments and so forth. And that's kind of intentional. I'm trying to give you stuff to keep you amused for a couple of months. Wanted to start by showing some cool work done by a couple of students, Reshma and npada01, who have developed an Android and an iOS app. And so check out Reshma's post on the forum about that, because they have a demonstration of how to create both Android and iOS apps that are actually on the Play Store and on the Apple App Store. So that's pretty cool. First ones I know of that are on the app stores that are using FastAI. And let me also say a huge thank you to Reshma for all of the work she does, both for the FastAI community and the machine learning community more generally, and also the women in machine learning community in particular. She does a lot of fantastic work, including providing lots of fantastic documentation and tutorials and community organizing and so many other things. So thank you, Reshma, and congrats on getting this app out there. We have lots of Lesson 7 notebooks today, as you see, and we're going to start with the one So the first notebook we're going to look at is Lesson 7, ResNet MNIST. And what I want to do is look at some of the stuff we started talking about last week around convolutions and convolutional neural networks and start building on top of them to create a fairly modern deep learning architecture largely from scratch. When I say from scratch, I'm not going to re-implement things we already know how to implement, but kind of use the pre-existing PyTorch bits of those. So we're going to use the MNIST data set, which, so urls.mnist has the whole MNIST data set. Often we've done stuff with a subset of it. So in there's a training folder and a testing folder. And as I read this in, I'm going to show some more details about pieces of the DataBlocks API so that you see how to kind of see what's going on. Normally with the DataBlocks API, we've kind of said blah, dot, blah, dot, blah, dot, blah, and done it all in one cell. But let's do them one cell at a time. So first thing you say is, what kind of item list do you have? So in this case, it's an item list of images. And then where are you getting the list of file names from? In this case, by looking in a folder recursively. And that's where it's coming from. You can pass in arguments that end up going to Pillow, because Pillow or PIL is the thing that actually opens that for us. And in this case, these are black and white rather than RGB. So you have to use Pillow's convert mode equals L. For more details, refer to the Python imaging library documentation to see what their convert modes are. But this one is going to be grayscale, which is what MNIST is. So inside an item list is an items attribute, and the items attribute is kind of the thing that you gave it. It's the thing that it's going to use to create your item. So in this case, the thing you gave it really is a list of file names. That's what it got from the folder. When you show images, normally it shows them in RGB, and so in this case we want to use a binary color map. So in FastAI you can set a default color map. For more information about CMap and color maps, refer to the matplotlib documentation, and so this will set the default color map for FastAI. Okay, so our image item list contains 70,000 items, and it's a bunch of images that are 1 by 28 by 28. Remember that PyTorch puts channel first, so they're one channel, 28 by 28. You might think, well, why aren't they just 28 by 28 matrices rather than a 1 by 28 by 28 rank 3 tensor? It's just easier that way. All the conv2D stuff and so forth works on rank 3 tensors, so you want to include that unit access at the start, and so FastAI will do that for you even when it's reading one channel images. So the .items attribute contains the thing that's kind of read to build the image, which in this case is the file name. But if you just index into an item list directly, you'll get the actual image object. Okay, and so the actual image object has a show method, and so there's the image. So once you've got an image item list, you then split it into training versus validation. You nearly always want validation. If you don't, you can actually use the .noSplit method to create a kind of empty validation set. You can't skip it entirely. You have to say how to split, and one of the options is noSplit, right? And so remember, that's always the order. First, create your item list, then decide how to split. In this case, we're going to do it based on folders. In this case, the validation folder for MNIST is called testing. So in kind of FastAI parlance, we use the same kind of parlance that Kaggle does, which is the training set is what you train on. The validation set has labels, and you do it for testing that your model's working. The test set doesn't have labels, and you use it for doing inference or submitting to a competition or sending it off to somebody who's held out those labels for, vendor testing or whatever. Okay? So just because a folder in your data set is called testing doesn't mean it's a test set, right? This one has labels, so it's a validation set. Okay, so if you want to do inference on lots of things at a time rather than one thing at a time, you want to use the test equals in FastAI to say this is stuff which has no labels, and I'm just using for inference. Okay, so my split data is a training set and a validation set, as you can see. So inside the training set, there's a folder for each image, for each class. So now we can take that split data and say label from folder
So first you create the item list, then you split it, then you label it. And so you can see now we have an X and a Y, and the Y are category objects. Category object is just a class, basically. So if you index into a label list, such as ll.train as a label list, you will get back an independent variable, X and Y. So in this case, the X will be an image object, which I can show, and the Y will be a category object, which I can print. That's the number, it's the number 8 category, and there's the 8. Next thing we can do is to add transforms. In this case, we're not going to use the normal get transforms function because we're doing digit recognition, and digit recognition, like you wouldn't want to flip it left, right, that would change the meaning of it. You wouldn't want to rotate it too much, that would change the meaning of it. Also because these images are so small, kind of doing zooms and stuff is going to make them so fuzzy as to be unreadable. So normally for small images of digits like this, you just add a bit of random padding. So I'll use the random padding function, which actually returns 2 transforms, the bit that does the padding and the bit that does the random crop. So you have to use star to say put both these transforms in this list. So now we can call transform. This empty array here is referring to the validation set transforms. So no transforms for the validation set. Now we've got a transformed labeled list. We can pick a batch size and choose data bunch. We can choose normalize. In this case, we're not using a pre-trained model, so there's no reason to use ImageNet stats here. And so if you call normalize like this, without passing in stats, it will grab a batch of data at random and use that to decide what normalization stats to use. And that's a good idea if you're not using a pre-trained model. Okay, so we've got a data bunch, and so in that data bunch is a data set, which we've seen already. But what is interesting is that the training data set now has data augmentation because we've got transforms. So plot multi is a fast AI function that will plot the result of calling some function for each of this row by column grid. So in this case, my function is just grab the first image from the training set. And because each time you grab something from the training set, it's going to load it from disk, and it's going to transform it on the fly, right? So people sometimes ask, like, how many transformed versions of the image do you create? And the answer is kind of infinite. Each time we grab one thing from the data set, we do a random transform on the fly. Okay, so potentially every one will look a little bit different. So you can see here, if we plot the result of that lots of times, we get 8s in slightly different positions because we did random padding. You can always grab a batch of data then from the data bunch, because remember a data bunch has data loaders, and data loaders are things that you grab a batch at a time. And so you can then grab an X batch and a Y batch, look at their shape, batch size by channel, by row, by column. All FastAA data bunches have a show batch, which will show you what's in it in some sensible way. Okay, so that's a quick walkthrough of the data block API stuff to grab our data. So let's start out creating a simple CNN, a simple component. So the input is 28 by 28. So let's define, I like to define, when I'm creating architectures, a function which kind of does the things that I do again and again and again. I don't want to call it with the same arguments because I'll forget, I'll make a mistake. So in this case, all of my convolutions are going to be kernel size 3, stride 2, padding 1. So let's just create a simple function to do a conv with those parameters. So each time I have a convolution, it's skipping over 1 pixel, so it's doing jumping 2 steps each time. So that means that each time we have a convolution, it's going to halve the grid size. So I've put a comment here showing what the new grid size is after each one. So after the first convolution, we have 1 channel coming in, because it's, remember, it's a grayscale image with 1 channel. And then how many channels coming out? Whatever you like, right? So remember, you always get to pick how many filters you create, regardless of whether it's a fully connected layer, in which case it's just the width of the matrix you're multiplying by, or in this case with a 2D conv, it's just how many filters do you want. So I picked 8, and so after this it's stride 2, so the 28 by 28 image is now a 14 by 14 feature map with 8 channels, so specifically therefore it's an 8 by 14 by 14 tensor of activations. Then we'll do batch norm, then we'll do ReLU. So the number of input filters to the next conv has to equal the number of output filters from the previous conv. And we can just keep increasing the number of channels. Because we're doing stride 2, it's going to keep decreasing the grid size. Notice here it goes from 7 to 4, because if you're doing a stride 2 conv over 7, it's going to be kind of math.ceiling of 7 divided by 2. Batch norm ReLU conv, we're now down to 2 by 2. Batch norm ReLU conv, we're now down to 1 by 1. Right? So after this, we have a batch size, a feature map of, let's see, 10 by 1 by 1. Does that make sense? We've got a grid size of 1 now. So it's not a vector of length 10. It's a rank 3 tensor of 10 by 1 by 1. So our loss functions expect generally a vector, not a rank 3 tensor. So you can chuck flatten at the end, and flatten just means remove any unit axes. So that will make it now just a vector of length 10, which is what we always expect. So that's how we can create a CNN. So then we can turn that into a learner by passing in the data and the model and the loss function and if optionally some metrics. So we're going to use cross entropy as usual. So we can then call learn.summary and confirm. After that first conv, we're down to 14 by 14. And after the second conv, 7 by 7, then 4 by 4, 2 by 2, 1 by 1. The flatten comes out calling it a lambda, but that, as you can see, it gets rid of the 1 by 1, and it's now just a length 10 vector for each item in the batch. So a 128 by 10 matrix of the whole mini batch. So just to confirm that this is working okay, we can grab that mini batch of X that we created earlier. There's our mini batch of X. Pop it onto the GPU and call the model directly. Remember, any PyTorch module, we can pretend it's a function. And that gives us back, as we hoped, a 128 by 10 result. Okay, so that's how you can directly get some predictions out. LR find, fit one cycle, and bang. We already have a 98.6% accurate convnet. And this is trained from scratch, of course. It's not pre-trained. We literally created our own architecture. It's about the simplest possible architecture you can imagine. 18 seconds to train. So that's how easy it is to create a pretty accurate digit detector. So let's refactor that a little. Rather than saying conv batch norm ReLU all the time, FastAI already has something called conv underscore layer, which lets you create conv batch norm ReLU combinations. And it has various other options to do other tweaks to it, but the basic version is just exactly what I just showed you. So we can refactor that like so. So that's exactly the same neural net. And so, you know, let's just train it a little bit longer. And it's actually 99.1% accurate if we train it for all of a minute. So that's cool. So how can we improve this? Well, what we really want to do is create a deeper network. And so a very easy way to create a deeper network would be after every stride 2 conv, add a stride 1 conv. Because the stride 1 conv doesn't change the feature map size at all. So you can add as many as you like. Right? But there's a problem. There's a problem. And the problem was pointed out in this paper, very, very, very influential paper called Deep Residual Learning for Image Recognition by Kai-Ming He and colleagues then at Microsoft Research. And they did something interesting. They said, let's look at the training error. So forget generalization even. Let's just look at the training error of a network trained on Sci-Fi 10. And let's try one network with 20 layers, just basic 3x3 convs, just basically the same network I just showed you, but without batch norm. Let's try a 20-layer one and a 56-layer one on the training set. So the 56-layer one has a lot more parameters. It's got a lot more of these stride 1 convs in the middle. So the one with more parameters should seriously overfit, right? So you would expect the 56-layer one to zip down to zero-ish training error pretty quickly. And that is not what happens. It is worse than the shallower network. So when you see something weird happen, really good researchers don't go, oh no, it's not working. They go, that's interesting. So Kai-Ming He said, that's interesting. What's going on? And he said, I don't know, but what I do know is this. I could take this 56-layer network and make a new version of it which is identical, but has to be at least as good as the 20-layer network. And here's how. Every 2 convolutions, I'm going to add together the input to those 2 convolutions, add it together with the result of those 2 convolutions. So in other words, he's saying, instead of saying output equals conv2 of conv1 of x, instead he's saying output equals x plus conv2 of conv1 of x. So that 56 layers worth of convolutions in that, his theory was, has to be at least as good as the 20-layer version because it could always just set conv2 and conv1 to a bunch of 0 weights for everything except for the first 20 layers because the x, the input, could just go straight through. So this thing here is, as you see, called an identity connection. It's the identity function. Nothing happens at all. It's also known as a skip connection. So that was a theory, right? That's what the paper describes as the intuition behind this, is what would happen if we created something which has to train at least as well as a 20-layer neural network because it kind of contains that 20-layer neural network. There's literally a path. You can just skip over all the convolutions. And so what happens? And what happened was he won ImageNet that year. He easily won ImageNet that year. And in fact, even today, we had that record-breaking result on ImageNet speed training ourselves. In the last year, we used this too. ResNet has been revolutionary. And anytime, here's the trick, if you're interested in doing some research, some novel research, anytime you find some model for anything, whether it's like medical image segmentation or, some kind of GAN or whatever, and it was written a couple of years ago, they might have forgotten to put ResNets in, res blocks. This is what we normally call a res block. They might have forgotten to put res blocks in. So replace their convolutional path with a bunch of res blocks, and you'll almost always get better results faster. It's a good trick. So at NeurIPS, which Rachel and I and David all just came back from, and Sylvain, we saw a new presentation where they actually figured out how to visualize the loss surface of a neural net, which is really cool. This is a fantastic paper, and anybody who's watching this, Lesson 7, is at a point where they will understand most of the most important concepts in this paper. You can read this now. You won't necessarily get all of it, but I'm sure you'll get enough to find it interesting. And so the big picture was this one. Here's what happens if you draw a picture where kind of X and Y here are 2 projections of the weight space, and Z is the loss. And so as you move through the weight space, a 56-layer neural network without skip connections is very, very bumpy. And that's why this got nowhere, because it just got stuck in all these hills and valleys. The exact same network with identity connections, with skip connections, has this loss landscape. Right? So it's kind of interesting how Hurt recognized back in 2015, this shouldn't happen, here's a way that must fix it, and it took 3 years before people were able to say, oh, this is kind of why it fixed it. It kind of reminds me of the batch norm discussion we had a couple of weeks ago, of people realizing a little bit after the fact sometimes what's going on and why it helps. So, in our code, we can create a res block in just the way I described. We create an nn.module, we create 2 conv layers. Remember, a conv layer is conv2d batch norm ReLU. Conv2d ReLU batch norm. So create 2 of those, and then in forward, we go conv1 of x, conv2 of that, and then add x. There's a resblock function already in FastAI, so you can just call resblock instead, and you just pass in something saying how many filters do you want. So, yeah, so there's the resblock that I defined in our notebook. And so with that resblock, we can now take every one of those. I've just copied the previous CNN, and after every conv2, except the last one, I added a resblock. So this has now got 3 times as many layers. So it should be able to do more compute, right? But it shouldn't be any harder to optimize. So what happens? Well, let's just refactor it one more time. Since I go conv2 resblock so many times, let's just pop that into a little mini sequential model here. And so I can refactor that like so. Like, keep refactoring your architectures if you're trying novel architectures, because you'll make less mistakes. Very few people do this. Most research code you look at is clunky as all hell, and people often make mistakes in that way. So don't do that. You're all coders, so use your coding skills to make life easier. Okay, so there's my ResNet-ish architecture, and LR-find, as usual, fit for a while, and I get 99.54. So that's interesting, because we've trained this literally from scratch with an architecture we built from scratch. I didn't look up this architecture anywhere, it was just the first thing that came to mind. But in terms of where that puts us, 0.45% error is around about the state of the art for this data set as of 3 or 4 years ago. Now, today MNIST is considered a kind of trivially easy data set. So I'm not saying like, wow, we've broken some records here. People have got beyond 0.45% error. But what I'm saying is that, we can't, this kind of ResNet is a genuinely extremely useful network still today. And this is really all we use in our fast ImageNet training still. And one of the reasons as well is that it's so popular, so the vendors of the library spend a lot of time optimizing it, so things tend to work fast. Whereas some more modern style architectures using things like separable or grouped convolutions tend not to actually train very quickly in practice. If you look at the definition of resblock in the FastAI code, you'll see it looks a little bit different to this. And that's because I've created something called a merge layer. And a merge layer is something which in the forward, just skip dense for a moment, the forward says x plus x dot orig. So you can see there's something ResNet-ish going on here. What is x dot orig? Well, if you create a special kind of sequential model called a sequential EX, so this is like FastAI's sequential extended, it's just like a normal sequential model, but we store the input in x.orig, right? And so this here, sequential EX conv layer, merge layer will do exactly the same as this. Okay, so you can create your own variations of ResNet blocks very easily with just sequential EX and merge layer. So there's something else here, which is when you create your merge layer, you can optionally set dense equals true. What happens if you do? Well, if you do, it doesn't go x plus x dot image. It goes cat x comma x dot image. In other words, rather than putting a plus in this connection, it does a concatenate. So that's pretty interesting because what happens is that you have your input coming into your res block. And once you use concatenate instead of plus, it's not called a res block anymore, it's called a dense block. And it's not called a res net anymore, it's called a dense net. So the dense net was invented about a year after the ResNet. And if you read the DenseNet paper, it can sound incredibly complex and different, but actually it's literally identical, but plus here is replaced with cat. So you have your input coming into your dense block, right? And you've got a kind of few convolutions in here, and then you've got some output coming out, and then you've got your identity connection. And remember, it doesn't plus, it concats. So if this is the channel axis, it gets a little bit bigger. Right? And then so we do another dense block, right? And at the end of that we have, all of this coming in. We have, okay, so at the end of that we have, the result of the convolution as per usual, but this time the identity block is that big, right? So you can see that what happens is that with dense blocks, it's getting bigger and bigger and bigger. And kind of interestingly, the exact input is still here, right? So it actually, no matter how deep you get, the original input pixels are still there, and the original layer 1 features are still there, and the original layer 2 features are still there. So, as you can imagine, dense nets are very memory intensive. There are ways to manage this. Just from time to time, you can have a regular convolution that squishes your channels back down, but they are memory intensive. But they have very few parameters. So for dealing with small data sets, you should definitely experiment with dense blocks and dense nets. They tend to work really well on small data sets. Also, because it's possible to kind of keep those original input pixels all the way down the path, they work really well for segmentation, right? Because for segmentation, you kind of want to be able to reconstruct the original resolution of your picture, so having all of those original pixels still there is super helpful. So that's ResNets, and one of the main reasons, other than the fact that ResNets are awesome, to tell you about them is that these skip connections are useful in other places as well. And they're particularly useful in other places and other ways of designing architectures for segmentation. So in building this lesson, I keep trying to take old papers and saying, imagining, what would that person have done if they had access to all the modern techniques we have now? And I try to kind of rebuild them in a more modern style. So I've been really rebuilding this next architecture we're going to look at, called a UNet, in a more modern style. Recently, and got to the point now, I keep showing you this semantic segmentation paper with the state-of-the-art for Canvid, which was 91.5. This week I got it up to 94.1 using the architecture I'm about to show you. So we keep pushing this further and further and further. And it really was all about adding all of the modern tricks, many of which I'll show you today, some of which we'll see in part 2. So what we're going to do to get there is we're going to use this UNet. So we've used a UNet before. I've improved it a bit since then. So we've used a UNet before. We used it when we did the Canvid segmentation, but we didn't understand what it was doing. So we're now in a position where we can understand what it was doing. And so the first thing we need to do is kind of understand the basic idea of how you can do segmentation. So if we go back to our Canvid notebook, in our Canvid notebook, you'll remember that basically what we were doing is we were taking these photos and adding a class to every single pixel. And so when you go data.showBatch for something which is a segmentation item list, it will automatically show you these color-coded pixels. So here's the thing, like, in order to color code this as a pedestrian, but this as a bicyclist, it needs to know what it is. It needs to actually know that's what a pedestrian looks like, and it needs to know that's exactly where the pedestrian is, and this is the arm of the pedestrian and not part of their shopping basket. It needs to really understand a lot about this picture to do this task. And it really does do this task. Like, when you looked at the results of our top model, I can't see a single pixel by looking at it by eye. I know there's a few wrong, but I can't see the ones that are wrong. It's that accurate. So how does it do that? So the way that we're doing it to get these really, really good results is, not surprisingly, using pre-training. So we start with a ResNet 34. And you can see that here, UNet learner data, models.resnet34. And if you don't say pre-trained equals false, by default you get pre-trained equals true, because why not? So we start with a ResNet 34, which starts with a big image. So in this case, this is from the UNet paper now. Their images, they started with one channel by 572 by 572. This is for medical imaging segmentation. So after your stride 2 conv, they're doubling the number of channels to 128, and they're halving the size, so they're now down to 280 by 280. In this original UNet paper, they didn't add any padding, so they lost a pixel on each side each time they did a conv. That's why you're losing these two. But so basically half the size, and then half the size, and then half the size, and then half the size, until they're down to 28 by 28 with 1,024 channels, right? So that's what the UNet's downsampling path, this is called the downsampling path, look like. Ours is just a ResNet 34. So you can see it here, learn.summary, right? This is literally a ResNet 34. So you can see that the size keeps halving, channels keep going up, and so forth. Okay? So eventually, you've got down to a point where if you use a UNet architecture, it's 28 by 28 with 1,024 channels. With the ResNet architecture, with a 224 pixel input, it would be 512 channels by 7 by 7. So it's a pretty small grid size on this feature map. Somehow, we've got to end up with something which is the same size as our original picture. So how do we do that? How do you do computation which increases the grid size? Well, we don't have a way to do that in our current bag of tricks. We can use a stride 1 conv to do computation and keep grid size, or a stride 2 conv to do computation and halve the grid size. So how do we double the grid size? We do a stride half conv, also known as a deconvolution, also known as a transposed convolution. There is a fantastic paper called A Guide to Convolution Arithmetic for Deep Learning that shows a great picture of exactly what does a 3 by 3 kernel stride half conv look like. And it's literally this. If you have a 2 by 2 input, so the blue squares are the 2 by 2 input, you add not only 2 pixels of padding all around the outside, but you also add a pixel of padding between every pixel. And so now if we put this 3 by 3 kernel here, and then here, and then here, you see how the 3 by 3 kernel is just moving across it in the usual way? You will end up going from a 2 by 2 output to a 5 by 5 output. So if you only added 1 pixel of padding around the outside, you would end up with a 3 by 3 output, right? So, sorry, 4 by 4. So this is how you can increase the resolution. This was the way people did it until maybe a year or two ago. That's another trick for improving things you find online, because this is actually a dumb way to do it. And it's kind of obvious it's a dumb way to do it for a couple of reasons. One is that, like, have a look at this. Nearly all of those pixels are white. They're nearly all zeros. So, like, what a waste. What a waste of time. What a waste of computation. There's just nothing going on there. Also, this one, when you get down to, like, that 3 by 3 area, 2 out of the 9 pixels are non-white. But this one, 1 out of the 9 are non-white. So they're kind of like, there's different amounts of information going into different parts of your convolution. So, like, it just doesn't make any sense to kind of throw away information like this and to kind of do all this unnecessary computation and have different parts of the convolution having access to different amounts of information. What people generally do nowadays is something really simple, which is if you have let's say a 2 by 2 input with these are your pixel values, A, B, C, and D, and you want to create a 4 by 4, why not just do this? A, B, 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 C, 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 D, 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 D. So I've now upscaled from 2 by 2 to 4 by 4. I haven't done any interesting computation, but now on top of that, I could just do a stride 1 convolution, and now I have done some computation, right? So an upsample, this is called nearest neighbor interpolation. Nearest neighbor interpolation. So you can just do, and that's super fast, which is nice. So you can do a nearest neighbor interpolation and then a stride 1 conv, and now you've got some computation which is actually kind of using, there's no zeros here. This is kind of nice because it gets a mixture of A's and B's, which is kind of what you would want, and so forth. Another approach is instead of using nearest neighbor interpolation, you can use bilinear interpolation, which basically means instead of copying A to all of those different cells, you take a kind of a weighted average of the cells around it. So, for example, if you were, looking at what should go here, you would kind of go like, oh, it's about 3 A's, 2 C's, 1 D, and 2 B's, and you kind of take the average. Not exactly, but roughly, just a weighted average. Bilinear interpolation you'll find in any, all over the place. It's a pretty standard technique. Anytime you look at a picture on your computer screen and change its size, it's doing bilinear interpolation. So you can do that and then a stride 1 conv. So that was what people were using. Well, that's what people still tend to use. That's as much as I'm going to teach you this part. In part 2, we'll actually learn what the FastAI library is actually doing behind the scenes, which is something called pixel shuffle, also known as subpixel convolutions. It's not dramatically more complex, but complex enough that I won't cover it today. There's the same basic idea. All of these things is something which is basically letting us do a convolution that ends up with something that's twice the size. And so that gives us our upsampling path, right? So that lets us go from 28 by 28 to 54 by 54 and keep on doubling the size. So that's good. And that was it until UNet came along. That's what people did. And it didn't work real well, which is not surprising because, like, in this 28 by 28 feature map, how the hell is it going to have enough information to reconstruct a 572 by 572 output space? That's a really tough ask. So you tended to end up with these things that lacked fine detail. What Olaf Ronneberger and et al. Did was they said, hey, let's add a skip connection, an identity connection. And amazingly enough, this was before ResNets existed. So this was like a really big leap, really impressive. And so, but rather than adding a skip connection that skipped every 2 convolutions, they added skip connections where these grey lines are. In other words, they added a skip connection from the same part of the downsampling path to the same sized bit in the upsampling path. And they didn't add, that's why you can see the white and the blue next to each other, they didn't add, they concatenated. So basically these are like dense blocks, right? But the skip connections are skipping over larger and larger amounts of the architecture, so that over here, you've literally got, well, nearly, the input pixels themselves coming into the computation of these last couple of layers. And so that's going to make it super handy for resolving the fine details in these segmentation tasks, because you've like literally got all of the fine details. On the downside, you don't have very many layers of computation going on here, just 4, right? So you better hope that by that stage you've done all the computation necessary to figure out, is this a bicyclist or is this a pedestrian? But you can then add on top of that something saying like, is this exact pixel where their nose finishes, or is that the start of the tree? So that works out really well. And that's a UNet. So this is the UNet code from FastAI. And the key thing that comes in is the encoder. The encoder refers to that part. In other words, in our case, a ResNet 34. In most cases, they have this specific older style architecture. But like I said, replace any older style architecture bits with ResNet bits and life improves, particularly if they're pre-trained. So that certainly happened for us. So we start with our encoder. So our layers of our UNet is an encoder, then batch norm, then ReLU, and then middle conv, which is just conv layer, comma, conv layer. Remember, conv layer is a conv ReLU batch norm in FastAI. And so the middle conv is these 2 extra steps here at the bottom. Okay, just doing a little bit of computation. It's kind of nice to add more layers of computation where you can. So encoder, batch norm, ReLU, and then 2 convolutions. And then we enumerate through these indexes. What are these indexes? I haven't included the code, but these are basically, we figure out what is the layer number where each of these stride 2 convs occurs, and we just store it in an array of indexes. So then we can loop through that, and we can basically say for each one of those points, create a UNet block, telling us how many upsampling channels there are and how many cross-connection. These things here are called cross-connections, or at least that's what I call them. So that's really the main works going on in the UNet block. As I said, there's quite a few tweaks we do, as well as the fact we use a much better encoder. We also use some tweaks in all of our upsampling using this pixel shuffle. We use another tweak called ICNR. And then another tweak, which I just did in the last week, is to not just take the result of the convolutions and pass it across, but we actually grab the input pixels and make them another cross connection. That's what this last cross is here. You can see we're literally appending a res block with the original inputs. So you can see our merge layer. So really all the work's going on in UNet block. And UNet block is, it has to store the activations at each of these downsampling points. And the way to do that, as we learned in the last lesson, is with hooks. So we put hooks into the ResNet 34 to store the activations each time there's a stride 2 conv. And so that's, you can see here, we grab the hook. Okay? And we grab the result of the stored value in that hook, and we literally just go torch.cat, so we concatenate the upsampled convolution with the result of the hook, which we chuck through batch norm, and then we do 2 convolutions to it. And actually, something you could play with at home is pretty obvious here. Anytime you see 2 convolutions like this, there's an obvious question is, what if we used a ResNet block instead? So you could try replacing those 2 convs with a ResNet block. You might find you get even better results. Now, they're the kind of things I look for when I look at an architecture is like, oh, 2 convs in a row, probably should be a ResNet block. Okay, so that's UNet. And, you know, it's amazing to think, you know, it preceded ResNet, it preceded DenseNet. It wasn't even published in a major machine learning venue. It was actually published in MICI, which is a specialized medical image computing conference. For years, actually, you know, it was largely unknown outside of the medical imaging community. And actually what happened was Kaggle competitions for segmentation kept on being easily won by people using UNets. And that was the first time I saw it getting noticed outside the medical imaging community. And then gradually a few people in the academic machine learning community started noticing, and now everybody loves UNet, which I'm glad, because it's just awesome. Identity connections, regardless of whether they're a plus style or a concat style, are incredibly useful. They can basically get us close to the state of the art on lots of important tasks. So I want to use them on another task now. And so the next task I want to look at is image restoration. So image restoration refers to starting with an image. And this time we're not going to create a segmentation mask, but we're going to try and create a better image. And there's lots of kind of versions of better. There could be different image. So the kind of things we can do with this kind of image generation would be take a low-res image, make it high-res, take a black and white image, make it color, take an image where something's been cut out of it and try and replace the cut out thing. Take a photo and try and turn it into what looks like a line drawing. Take a photo and try and make it look like a Monet painting. These are all examples of kind of image-to-image generation tasks, which you'll know how to do after this part of the class. So in our case, we're going to try to do image restoration, which is going to start with low resolution, poor quality JPEGs with writing written over the top of them, and get them to replace them with high resolution, good quality pictures in which the text has been removed. 2 questions? Okay, let's go.
Why do you concat before calling conv2, conv1, not after?
Because if you did conv1, if you did your convs before you concat, then there's no way for the channels of the 2 parts to interact with each other. You don't get any, so remember in a 2D conv, it's really 3D, right? It's moving across 2 dimensions, but in each case, it's doing a dot product of all 3 dimensions of a rank 3 tensor, row by column by channel. So generally speaking, we want as much interaction as possible. We want to say, this part of the downsampling path and this part of the upsampling path. If you look at the combination of them, you find these interesting things. So generally, you want to have as many interactions going on as possible in each computation that you do.
How does concatenating every layer together in a dense net work when the size of the image feature maps is changing through the layers?
That's a great question. So if you have a stride 2 conv, you can't keep dense netting, right? So that's what actually happens in a dense net, is you kind of go like dense block growing, dense block growing, dense block growing, so you're getting more and more channels. And then you do a stride 2 conv without a dense block. And so now it's kind of gone. And then you just do a few more dense blocks and then it's gone. So in practice, a dense block doesn't actually keep all the information all the way through, but it just up until every one of these stride 2 convs. And there's kind of various ways of doing these bottlenecking layers where you're basically saying, hey, let's reset. It also helps us keep memory under control because at that point we can decide how many channels we actually want. Good questions. Thank you. Right. So in order to create something which can turn crappy images into nice images, we need a data set containing nice versions of images and crappy versions of the same images. So the easiest way to do that is to start with the nice images and crapify them. And so the way to crapify them is to create a function called crapify, which contains your crapification logic. So my crapification logic, you can pick your own, is that I open up my nice image, I resize it to be really small, 96 by 96 pixels, with bilinear interpolation. I then pick a random number between 10 and 70. I draw that number into my image at some random location. And then I save that image with a JPEG quality of that random number. And a JPEG quality of 10 is like absolute rubbish. A JPEG quality of 70 is not bad at all. Okay? So I end up with high quality images, low quality images that look something like these. And so you can see this one, you know, there's the image, and this is after transformation, so that's why it's been flipped. And you won't always see the image because we're zooming into them, so a lot of the time the image is cropped out. So yeah, it's trying to figure out how to take this incredibly JPEG artifacty thing with text written over the top and turn it into this. So I'm using the Oxford Pets dataset again, the same one we used in lesson 1. So there's nothing more high quality than pictures of dogs and cats. I think we can all agree with that. The crapification process can take a while, but FastAI has a function called parallel. And if you pass parallel a function name and a list of things to run that function on, it will run that function on them all in parallel. So this actually can run pretty quickly. The way you write this function is where you get to do all the interesting stuff in this assignment. Try and think of an interesting crapification which does something that you want to do, right? So if you want to, you know, colorize black and white images, you would replace it with black and white. If you want something which can, you know, take like large cutout blocks of image and replace them with kind of hallucinated image, you know, add a big black box to these. If you want something which can kind of take old family photo scans that have been like folded up and have crinkles in, try and find a way of like adding dust prints and crinkles and so forth, right? Anything that you don't include in Crapify, your model won't learn to fix, because every time it sees that in your photos, the input and output will be the same, so it won't consider that to be something worthy of fixing. Okay, so we now want to create a model which can take an input photo that looks like that and output something that looks like that. So obviously what we want to do is use a UNet, because we already know that UNets can do exactly that kind of thing, and we just need to pass the UNet that data. Okay, so our data is just literally the file names of each of those from each of those two folders. Do some transforms, data bunch, normalize. We'll use ImageNet stats because we're going to use a pre-trained model. Why are we using a pre-trained model? Well, because like if you're going to get rid of this 46, you need to know what probably was there, and to know what probably was there, you need to know what this is a picture of, right? Because otherwise, how can you possibly know what it ought to look like? So, you know, let's use a pre-trained model that knows about these kinds of things. So we create our UNet with that data. The architecture is ResNet 34. These three things are important and interesting and useful, but I'm going to leave them to part 2. Okay, for now, you should always include them when you use a UNet for this kind of problem. And so now we're going to, and this whole thing I'm calling a generator. Okay, it's going to generate. This is generative modeling. We're kind of, there's not a really formal definition, but it's basically something where the thing we're outputting is like a real object, in this case an image. It's not just a number. So we're going to create a generator learner, which is this UNet learner, and then we can fit. We're using MSC loss, right? So in other words, what's the mean squared error between the actual pixel value that it should be and the pixel value that we predicted? MSC loss normally expects 2 vectors. In our case, we have 2 images. So we have a version called MSC loss flat, which simply flattens out those images into a big long vector. There's never any reason not to use this. Even if you do have a vector, it works fine. If you don't have a vector, it'll also work fine. So we're already, down to 0.05 mean squared error on the pixel values, which is not bad after 1 minute 35. Like all things in fast AI pretty much, because we are doing transfer learning by default, when you create this, it'll freeze the pre-trained part. And the pre-trained part of a UNet is this part, the downsampling part. That's where the ResNet is. So let's unfreeze that and train a little more. And look at that. So with 4 minutes of training, we've got something which is basically doing a perfect job of removing numbers. It's certainly not doing a good job of upsampling, but it's definitely doing a nice... sometimes when it removes a number, it maybe leaves a little bit of JPEG artifact, but it's certainly doing something pretty useful. And so if all we wanted to do was kind of watermark removal, we'd be finished. We're not finished because we actually want this thing to look more like this thing. So how are we going to do that? The reason that we're not making as much progress with that as we'd like is that our loss function doesn't really describe what we want. Because actually the mean squared error between the pixels of this and this is actually very small. Right? And if you actually think about it, most of the pixels are very nearly the right color. But we're missing the texture of the pillow. And we're missing the eyeballs entirely, pretty much. Right? And we're missing the texture of the fur. Right? So we want some loss function that does a better job than pixel mean squared error loss of saying, like, is this a good quality picture of this thing? So there's a fairly general way of answering that question, and it's something called a generative adversarial network, or GAN. And a GAN tries to solve this problem by using a loss function which actually calls another model. And let me describe it to you. So we've got our crappy image, right? And we've already created a generator. It's not a great one, but it's not terrible, right? And that's creating predictions, like this. We have a high-res image, like that, and we can compare the high-res image to the prediction with pixel MSE. Okay. We could also train another model, which we would variously call either the discriminator or the critic. They both mean the same thing. I'll call it a critic. We could try and build a binary classification model that takes all the pairs of the generated image and the real high-res image and tries to learn to classify which is which. So look at some picture and say, like, hey, what do you think? Is that a high-res cat or is that a generated cat? How about this one? Is that a high-res cat or a generated cat? So just a regular, standard binary cross-entropy classifier. So we know how to do that already. So if we had one of those, we could now fine-tune the generator, and rather than using pixel MSE as the loss could be, how good are we at fooling the critic? So can we create generated images that the critic thinks are real? So that would be a very good plan, right? Because if it can do that, if the loss function is, am I fooling the critic, right, then it's going to learn to create images which the critic can't tell whether they're real or fake. So we could do that for a while, train a few batches, but the critic isn't that great. The reason the critic isn't that great is because it wasn't that hard. Like, these images are really shitty, so it's really easy to tell the difference. right? So after we train the generator a little bit more using the critic as the loss function, the generator is going to get really good at fooling the critic. So now we're going to stop training the generator and we'll train the critic some more on these newly generated images. So now that the generator is better, it's now a tougher task for the critic to decide which is real and which is fake. So we'll train that a little bit more. And then once we've done that, and the critic's now pretty good at recognizing the difference between the better generated images and the originals, we'll go back and we'll fine-tune the generator some more using the better discriminator, the better critic as the loss function. And so we'll just go ping pong, backwards and forwards. That's again. Well, that's our version of again. I don't know if anybody's written this before. We've created a new version of again, which is kind of a lot like the original GANs, but we have this neat trick where we pre-train the generator and we pre-train the critic. I mean, GANs have been kind of in the news a lot. They're a pretty fashionable tool, and if you've seen them, you may have heard that they're a real pain to train. But it turns out, we realized that really most of the pain of training them was at the start. If you don't have a pre-trained generator and you don't have a pre-trained critic, then it's basically the blind leading the blind, right? You basically, like the critics, well, the generator is trying to generate something which fools the critic, but the critic doesn't know anything at all, so it's basically got nothing to do. And then the critic's kind of trying to decide whether the generated images are real or not, and like that's really obvious, so that just does it. And so they kind of like don't go anywhere for ages, and then once they finally start picking up steam, they go along pretty quickly. So if you can find a way to generate things without using a GAN, like mean squared error pixel loss, and discriminate things without using a GAN, like predict on that first generator, you can make a lot of progress. So let's create the critic. So to create just a totally standard FastAI binary classification model, we need two folders. One folder is containing high-res images, one folder containing generated images. We already have the folder with the high-res images, so we just have to save our generated images. So here's a teeny tiny bit of code that does that. We're going to create a directory called ImageGen, pop it into a variable called PathGen. We're going to a little function called savepreds that takes a data loader, and we're going to grab all of the file names, because remember that in an item list, the .items contains the file names, if it's an image item list. So here's the file names in that data loader's data set. And so now let's go through each batch of the data loader, and let's grab a batch of predictions for that batch, right? And then reconstruct equals true means it's actually going to create FastAI image objects for each of those, each thing in the batch. And so then we'll go through each of those predictions and save them. And the name we'll save it with is the name of the original file, but we're going to pop it into our new directory. So that's it. That's how you save predictions. And so you can see I'm kind of increasingly not just using stuff that's already in the FastAI library, but trying to show you how to write stuff yourself, right? And generally it doesn't require heaps of code to do that. And so if you come back for part 2, this is what, you know, lots of part 2 were kind of like, here's how you use things inside the library, and of course, here's how we wrote the library. So we're increasingly writing our own code. Okay, so save those predictions, and then let's just do a pil.image.open on the first one, and yep, there it is. Okay, so there's an example of a generated image. So now I can train a critic in the usual way. It's really annoying to have to restart Jupyter Notebook to reclaim GPU memory. So one easy way to handle this is if you just set something that you knew was using a lot of GPU to none, like this learner, and then just go gc.collect. That tells Python to do memory garbage collection, and after that, you'll generally be fine. You'll be able to use all of your GPU memory again. If you're using NVIDIA SMI to actually look at your GPU memory, you won't see it clear because PyTorch still has a kind of allocated cache, but it makes it available. So you should find this is how you can avoid restarting your notebook. Okay, so we're going to create our critic. It's just an image item list from folder in the totally usual way. And the classes will be the image gen and images. We'll do a random split because we want to know how well we're doing with the critic to have a validation set. We just label it from folder in the usual way, add some transforms, data bunch, normalize. So it's a totally standard object classifier. Okay, so we've got a totally standard classifier. So here's what some of it looks like. So here's one from the real images, generated images, generated images. Okay, so it's got to try and figure out which class is which. Okay, so we're going to use binary cross entropy as usual. However, we're not going to use a ResNet here. And the reason we'll get into in more detail in part 2, but basically when you're doing a GAN, you need to be particularly careful that the generator and the critic can't kind of both push in the same direction and like increase the weights out of control. So we have to use something called spectral normalization to make GANs work nowadays. We'll learn about that in part 2. So but anyway, if you say GAN critic, that will give you, FastAI will give you a binary classifier suitable for GANs. I strongly suspect we probably can use a ResNet here. We just have to create a pre-trained ResNet with spectral norm. Hope to do that pretty soon. We'll see how we go. But as of now, this is kind of the best approach. There's this thing called GAN critic. A GAN critic uses a slightly different way of averaging the different parts of the image when it does the loss. So anytime you're doing a GAN at the moment, you have to wrap your loss function with adaptive loss. Again, we'll look at the details in part 2. For now, just know this is what you have to do and it'll work. So other than that slightly odd loss function and that slightly odd architecture, everything else is the same. We can call that to create our critic. Because we have this slightly different architecture and slightly different loss function, we did a slightly different metric. This is the equivalent GAN version of accuracy for critics. And then we can train it, and you can see it's 98% accurate at recognizing that kind of crappy thing from that kind of nice thing. And of course, we don't see the numbers here anymore, right? Because these are the generated images. The generator already knows how to get rid of those numbers that are written on top. Okay, so let's finish up this GAN. Now that we have pre-trained the generator and pre-trained the critic, we now need to get it to kind of ping-pong between training a little bit of each. And the amount of time you spend on each of those things and the learning rates you use is still a little bit on the fussy side. So we've created a GAN learner for you, which you just pass in your generator and your critic, which we've just simply loaded here from the ones we just trained. And it will go ahead and when you go learn.fit, it will do that for you. It'll figure out how much time to train the generator and then when to switch to training the discriminator, the critic, and it'll go back on and forward. These weights here is that what we actually do is we don't only use the critic as the loss function. If we only use the critic as the loss function, the GAN could get very good at creating pictures that look like real pictures, but they actually have nothing to do with the original picture, the original photo at all. So we actually add together the pixel loss and the critic loss. And so those two losses are kind of on different scales. So we multiply the pixel loss by something between about 50 and about 200. Again, something in that range generally works pretty well. Something else with GANs. GANs hate momentum when you're training them. It kind of doesn't make sense to train them with momentum because you keep switching between generator and critic, so it's kind of tough. Maybe there are ways to use momentum, but I'm not sure anybody's figured it out. So this number here, when you create an atom optimizer, is where the momentum goes. So you should set that to 0. So anyway, if you're doing GANs, use these hyperparameters. It should work. Okay, so so that's what GAN Learner does, and so then you can go fit, and it trains for a while. And one of the tough things about GANs is that these loss numbers, they're meaningless. You can't expect them to go down, right? Because as the generator gets better, it gets harder for the discriminator, the critic. And then as the critic gets better, it gets harder for the generator. So the numbers should stay about the same, right? So that's one of the tough things about training GANs, is it's kind of hard to know how are they doing. So the only way to know how are they doing is to actually take a look at the results from time to time. I haven't, and so if you put show image equals true here, it'll actually print out a sample after every epoch. I haven't put that in the notebook because it makes it too big for the repo, but you can try that. So I've just put the results at the bottom, and here it is. So pretty beautiful, I would say. We already knew how to get rid of the numbers, but we now don't really have that kind of artifact of where it used to be. And it's definitely sharpening up this little kitty cat quite nicely. It's not great, always. Like, there's some weird kind of noise going on here. Certainly a lot better than the horrible original. Like, this is a tough job to turn that into that. But there are some really obvious problems. Like here, these things ought to be eyeballs, and they're not. So why aren't they? Well, our critic doesn't know anything about eyeballs. And even if it did, it wouldn't know that eyeballs are particularly important. You know, we care about eyes. Like when we see a cat without eyes, it's a lot less cute. I mean, I'm more of a dog person, but, you know, it just doesn't know that this is a feature that matters. Particularly because the critic, remember, is not a pre-trained network. So I kind of suspect that if we replace the critic with a pre-trained network that's been pre-trained on ImageNet but is also compatible with GANs, it might do a better job here. But it's definitely a shortcoming of this approach. So we're going to have a break. Question first, and then we'll have a break, and then after the break I will show you how to find the cat's eyeballs again.
For what kind of problems do you not want to use UNets?
Well, UNets are for when the size of your output, you know, is similar to the size of your input and kind of aligned with it. There's no point kind of having cross connections if that level of spatial resolution in the output isn't necessary or useful. So yeah, any kind of generative modeling, and you know, segmentation is kind of generative modeling, right? It's generating a picture which is a mask of the original objects. Yeah, so probably anything where you want that kind of resolution of the output to be of the same kind of fidelity as the resolution of the input. Obviously, something like a classifier makes no sense, right? You in a classifier, you just want the downsampling path, because at the end you just want a single number, which is like, is it a dog or a cat, or what kind of pet is it, or whatever. Great. Okay, so let's get back together at 8:05. Just before we leave GANs, I'll just mention there's another notebook you might be interested in looking at, which is Lesson 7 WGAN. When GANs started a few years ago, people generally used them to kind of create images out of thin air, which I personally don't think is a particularly useful or interesting thing to do. But it's kind of a good, I don't know, it's a good research exercise, I guess. So we implemented this WGAN paper, which was kind of really the first one to do a somewhat adequate job somewhat easily. And so you can see how to do that with the FastAI library. It's kind of interesting because the data set we use is this LSUN Bedrooms data set, which we've provided in our URLs, which just, as you can see, has bedrooms, lots and lots and lots of bedrooms. And the approach, you'll see in the prose here that Sylvain wrote, the approach that we use in this case is to just say, can we create a bedroom? And so what we actually do is that the input to the generator isn't an image that we clean up. We actually feed to the generator random noise. And so then the generator's task is, can you turn random noise into something which the critic can't tell the difference between that output and a real bedroom? And so we're not doing any pre-training here or any of the stuff that makes this kind of fast and easy. So this is a very traditional approach, but you can still see, you still just go, GAN learner, and there's actually a WGAN version, which is, this kind of older style approach. But you just pass in the data and the generator and the critic in the usual way, and you call fit. And you'll see, in this case we have a show image on. After epoch 1, it's not creating great bedrooms, or 2 or 3. And you can really see that in the early days of these kinds of GANs, it doesn't do a great job of anything. But eventually, after, a couple of hours of training, producing somewhat like bedroom-ish things, So anyway, it's a notebook you can have a play with, and it's a bit of fun. So I was very excited when we got FastAI to the point in the last week or so that we had GANs working in a way where kind of API-wise they're far more concise and more flexible than any other library that exists. But also kind of disappointed with them. They take a long time to train and the outputs are still like so-so. And so the next step was like, well, can we get rid of GANs entirely? So the first step with that, obviously the thing we really want to do is come up with a better loss function. We want a loss function that does a good job of saying this is a high quality image without having to go all the GAN trouble. And preferably it also doesn't just say it's a high quality image, but it's an image which actually looks like the thing it's meant to. So the real trick here comes back to this paper from a couple of years ago, Perceptual Losses for Real-Time Style Transfer and Super Resolution. Justin Johnson et al. Created this thing they call perceptual losses. It's a nice paper, but I hate this term because there's nothing particularly perceptual about them. I would call them feature losses. So in the FastAI library, you'll see this referred to as feature losses. And it shares something with GANs, which is that after we go through our generator, which they call the image transform net, and you can see it's got this kind of U-net-shaped thing. They didn't actually use U-nets because at the time this came out, nobody in the machine learning world much knew about U-nets. Nowadays, of course, we use U-nets. But anyway, something U-net-ish. I should mention, like in these kind of these architectures where you have a downsampling path followed by an upsampling path, the downsampling path is very often called the encoder. As you saw in our code, actually, we called that the encoder. And the upsampling path is very often called the decoder. In generative models, generally, including generative text models, neural translation, stuff like that, they tend to be called the encoder and the decoder, 2 pieces. Anyway, so we have this, this generator, and we want a loss function that says, is the thing that it's created like the thing that we want? And so the way they do that is they take the prediction. Remember, y hat is what we normally use for a prediction from a model. We take the prediction and we put it through a pre-trained image network. So at the time that this came out, the pre-trained image network they were using was VGG. People still, it's kind of old now, but people still tend to use it because it works fine for this process. So they take the prediction and they put it through VGG, the pre-trained image network. It doesn't matter too much which one it is. And so normally the output of that would tell you, hey, is this generated thing, a dog or a cat or an airplane or a fire engine or whatever, right? But in the process of getting to that final classification, it goes through lots of different layers. And in this case, they've color-coded all the layers with the same grid size in the feature map with the same color. So every time we switch colors, we're switching grid size. So there's a stride 2 conv, or in VGG's case, they still used to use max pooling layers, which kind of similar idea. And so what we could do is say, hey, let's not take the final output of the VGG model on this generated image, but let's take kind of something in the middle. Let's take the activations of some layer in the middle. So those activations, you know, it might be a feature map of like 256 channels by 28 by 28, say. And so those kind of 28 by 28 grid cells will kind of roughly semantically say things like, hey, in this part of that 28 by 28 grid, is there something that looks kind of furry? Or is there something that looks kind of shiny? Or is there something that looks kind of circular? Is there something that kind of looks like an eyeball? Or whatever. So what we do is that we then take the target, so the actual Y value, and we put it through the same pre-trained VGG network, and we pull out the activations at the same layer, and then we do a mean squared error comparison. So it'll say like, okay, in the real image, grid cell 1,1 of that 28 by 28 feature map, you know, is furry and blue and round-shaped, and in the generated image, it's furry and blue and not round-shaped. So it's kind of like an okay match. So that ought to go a long way towards fixing our eyeball problem, because in this case, the feature map's going to say there's eyeballs here, here, but there isn't here. So do a better job of that, please. Make better eyeballs. So that's the idea. Okay? And so that's what we call feature losses, or Johnson et al. Called perceptual losses. So to do that, we're going to use the Lesson 7 SuperRes notebook. And this time the task we're going to do is kind of the same as the previous task, but I wrote this notebook a little bit before the GAN notebook, before I came up with the idea of like putting text on it and having a random JPEG quality. So the JPEG quality is always 60, there's no text written on top, and it's 96 by 96. So, and it's before I realized what a great word crapify is, so it's called resize. So here's our crappy images and our original images. Kind of a similar task to what we had before. So I'm going to try and create a loss function which does this. So the first thing I do is I define a base loss function, which is basically like, how am I going to compare the pixels and the features, you know, and the choices mainly are like MSE or L1. Doesn't matter too much which you choose. I tend to like L1 better than MSE, actually, so I picked L1. Right? So anytime you see base loss, we mean L1 loss. You could use MSE loss as well. So let's create a VGG model, right? So just using the pre-trained model. In VGG, there's an attribute called .features, which contains the convolutional part of the model. So here's the convolutional part of the VGG model, because we don't need the head, because we only want the intermediate activations. So then we'll chuck that on the GPU. We'll put it into eval mode, because we're not training it. And we'll turn off requires grad, because we don't want to update the weights of this model. We're just using it for inference, right, for the loss. So then let's enumerate through all the children of that model and find all of the max pooling layers, because in the VGG model, that's where the grid size changes. And as you can see from this picture, we kind of want to grab features from every time just before the grid size changes. So we grab layer I-1, so that's the layer before it changes. So there's our list of layer numbers just before the max pooling layers. And so all of those are ReLUs, not surprisingly. So those are where we want to grab some features from. And so we put that in blocks. It's just a list of IDs. So here's our feature loss class, which is going to implement this idea. So basically, when we call the feature loss class, we're going to pass it some pre-trained model. And so that's going to be called M feet. That's the model which contains the features which we want to generate want our feature loss on. So we can go ahead and grab all of the layers from that network that we want the losses for, that we want the features for to create the losses. So we're going to need to hook all of those outputs, because remember, that's how we grab intermediate layers in PyTorch, is by hooking them. So this is going to contain our hooked outputs. So now in the forward of feature loss, we're going to call make features passing in the target. So this is our actual Y, which is just going to call that VGG model and go through all of the stored activations and just grab a copy of them. And so we're going to do that both for the target, call that out feat, and for the input. So that's the output of our generator, in feat. And so now let's calculate the L1 loss between the pixels, because we still want the pixel loss a little bit. And then let's also go through all of those layers features and get the L1 loss on them. Right? So we're basically going through every one of these end of each block and grabbing the activations and getting the L1 on each one. So that's going to end up in this list called feature losses, which I then sum them all up. Okay? And, by the way, the reason I do it as a list is because we've got this nice little callback that if you put them into a thing called .metrics in your loss function, it'll print out all of the separate layer loss amounts for you, which is super handy. So that's it. That's our perceptual loss or feature loss class. And so now we can just go ahead and train a UNet in the usual way with our data and our pre-trained architecture, which is a ResNet34, passing in our loss function, which is using our pre-trained VGG model. And this is that callback I mentioned, loss metrics, which is going to print out all the different layers losses for us. These are two things that we'll learn about in part 2 of the course, but you should use them. LR find. I just created a little function called doFit that does fit one cycle and then saves the model and then shows the results. So as per usual, because we're using a pre-trained network in our UNet, we start with frozen layers for the downsampling path, train for a while, and as you can see, we get not only the loss, but also the pixel loss and the loss at each of our feature layers. And then also something we'll learn about in part 2 called gram loss, which I don't think anybody's used for SuperRes before as far as I know, but as you'll see, it turns out great. So that's 8 minutes, so much faster than a GAN, and already, as you can see, this is our output, modeled output, pretty good. So then we unfreeze and train some more, and it's a little bit better. And then let's switch up to double the size, and so we need to also halve the batch size to avoid running out of GPU memory, and freeze again, and train some more, so it's now taking half an hour, even better. And then unfreeze and train some more. So all in all, we've done about an hour and 20 minutes of training. And look at that. It's done it. Like, I mean, it knows that eyes are important. So it's really made an effort. It knows that fur is important. So it's really made an effort. So it started with something with like JPEG artifacts around the ears and all this mess and like eyes that are just kind of vague light blue things. And it really created a lot of texture. This cat is clearly kind of like looking over the top of one of those little clawing frames covered in fuzz. So it actually recognized that this thing is probably kind of a carpety material. So it's created a carpety material for us. So, I mean, that's just remarkable. So, talking of remarkable, we can now... so I've never seen outputs like this before without a GAN. So I was just so excited when we were able to generate this, and so quickly. 1 GPU, hour and a half. So like, if you create your own crapification functions and train this model, you'll build stuff that nobody's built before. Because like nobody else that I know of is doing it this way. So there are huge opportunities, I think. So check this out. What we can now do is we can now, instead of starting with our low res, I actually stored another set at size 256, which are called medium res. So let's see what happens if we upsize a medium res. So we're going to grab our medium res data, and here is our medium res stored photo. And so can we improve this? So you can see there's still a lot of room for improvement. Like you see the lashes here are very pixelated. Place where there should be hair here is just kind of fuzzy. So watch this area as I hit down on my keyboard. Bump. Look at that. It's done it. You know, it's taken a medium res image and it's made a totally clear thing here. You know, the furs reappeared. Like, look at the eyeball. Let's go back. The eyeball here is just kind of a general blue thing. Here, it's added all the right texture, you know. So I just think this is super exciting. You know, here's a model I trained in an hour and a half using standard stuff that you've all learnt about, a UNet, a pre-trained model, a feature loss function, and we've got something which can turn that into that, or, you know, this absolute mess into this. And like, it's really exciting to think what could you do with that, right? So one of the inspirations here has been a guy called Jason Antich. And Jason was a student in the course last year. What he did, very sensibly, was decide to focus, basically nearly quit his job and work 4 days a week, well really 6 days a week, on studying deep learning. And as you should do, he created a kind of capstone project. And his project was to combine GANs and feature losses together. And his crapification approach was to take color pictures and make them black and white. So he took the whole of ImageNet, created a black and white ImageNet, and then trained a model to recolorize it. And he's put this up as de-oldify. And now he's got these actual old photos from the 19th century that he's turning into color. And like, what this is doing is incredible. Like, look at this. The model thought, oh, that's probably some kind of copper kettle, so I'll make it like copper colored. And oh, these pictures are on the wall. They're probably like different colors to the wall. And maybe that looks a bit like a mirror. Maybe it would be reflecting stuff outside, you know. These things might be vegetables. Vegetables are often red, you know, let's make them red. It's extraordinary what it's done. And you could totally do this too. Like, you can take our feature loss and our GAN loss and combine them. So I'm very grateful to Jason because he's helped us build this lesson. And it's been really nice because we've been able to help him too, because he hadn't realized that he can use all this pre-training and stuff. And so hopefully you'll see de-oldify in the next couple of weeks be even better at de-oldification. But hopefully you all can now add other kinds of decrapification methods as well. So I'm, you know, I like every course, if possible, to show something totally new, because then every student has the chance to basically build things that have never been built before. So this is kind of that thing, you know, but between the much better segmentation results and these much simpler and faster decrapification results, I think you can build some really cool stuff. Did you have a question?
Is it possible to use similar ideas to UNet and GANs for NLP? For example, if I want to tag the verbs and nouns in a sentence or create a really good Shakespeare generator.
Yeah, pretty much. We don't fully know yet. It's a pretty new area, but there's a lot of opportunities there. And we'll be looking at some in a moment, actually. So I actually tried training this, well, I actually tried testing this on this, remember this picture I showed you of a slide last lesson? And it's a really rubbishy looking picture. And I thought, what would happen if we tried running this just through the exact same model? And it changed it from that to that. So I thought that was a really good example. You can see something it didn't do, which is this weird discoloration. It didn't fix it, because I didn't crapify things with weird discoloration, right? So if you want to create really good image restoration, like I say, you need really good crapification. Okay, so here's what we've learned so far, right, in the course, some of the main things. So we've learned that neural nets consist of sandwich layers of affine functions, which are basically matrix multiplications, slightly more general version, and nonlinearities, like ReLU. And we learned that the results of those calculations are called activations, and the things that go into those calculations that we learn are called parameters, and that the parameters are initially randomly initialized, or we copy them over from a pre-trained model, and then we train them with SGD or faster versions. And we learned that convolutions are a particular affine function that work great for autocorrelated data, so things like images and stuff. We learned about batch norm, dropout, data augmentation, and weight decay as ways of regularizing models, and also batch norm helps train models more quickly. And then today we've learned about res/dense blocks. We've obviously learned a lot about image classification and regression, embeddings, categorical and continuous variables, collaborative filtering, language models and NLP classification, and then kind of segmentation, UNet, and GANs. So go over these things and make sure that you feel comfortable with each of them. If you've only watched this series once, you definitely won't. People normally watch it, 3 times or so to really understand the detail. So one thing that doesn't get here is RNNs. So that's the last thing we're going to do, RNNs. Okay. So RNNs, I'm going to introduce a little kind of diagrammatic method here to explain RNNs. And the diagrammatic method, I'll start by showing you a basic neural net with a single hidden layer. Square means an input. So that'll be batch size by number of inputs, right? So kind of, batch size by number of inputs. An arrow means a layer, broadly defined, such as matrix product followed by ReLU. A circle is activations. Okay, so in this case we have one set of hidden activations, and so given that the input was number of inputs, this here is a matrix of number of inputs by number of activations, so the output will be batch size by number of activations. It's really important you know how to calculate these shapes, right? So go learn.summary lots to see all the shapes. So then here's another arrow, so that means it's another layer, matrix product followed by nonlinearity. In this case we're going to the output, so we use softmax. And then triangle means an output. Okay, and so this matrix product will be number of activations by number of classes, so our output is batch size by number of classes. Okay, so let's reuse that key. Remember, triangle output, circle is activations, hidden state, we also call that, and rectangle is input. So let's now imagine that we wanted to get a big document, split it into sets of 3 words at a time, and grab each set of 3 words and then try to predict the third word using the first 2 words. So if we had the data set in place, we could grab word 1 as an input, chuck it through an embedding, right, create some activations, pass that through a matrix product and nonlinearity, grab the second word, put it through an embedding, and then we could either add those 2 things together or concatenate them. Generally speaking, when you see kind of 2 sets of activations coming together in a diagram, you normally have a choice of concatenate or add. And that's going to create a second bunch of activations, and then you can put it through one more fully connected layer and softmax to create an output. So that would be a totally standard, fully connected neural net with one very minor tweak, which is concatenating or adding at this point, which we could use to try to predict the third word of every, from pairs of 2 words. Okay. So remember, arrows represent layer operations, and I removed in this one the specifics of what they are because they're always an affine function followed by a nonlinearity. Okay, let's go further. What if we wanted to predict word 4 using words 1 and 2 and 3? It's basically the same picture as last time, except with one extra input and one extra circle. But I want to point something out, which is each time we go from rectangle to circle, we're doing the same thing. We're doing an embedding, which is just a particular kind of matrix multiply, where you have a one-hot encoded input. Each time we go from circle to circle, we're basically taking one piece of hidden state, one set of activations, and turning it into another set of activations by saying we're now at the next word. And then when we go from circle to triangle, we're doing something else again, which is we're saying let's convert the hidden state, these activations, into an output. So it would make sense, so you can see I've colored each of those arrows differently. So each of those arrows should probably use the same weight matrix because it's doing the same thing. So why would you have a different set of embeddings for each word, or a different set of, a different matrix to multiply by to go from this hidden state to this hidden state versus this one? Okay. So this is what we're going to build. So we're now going to jump into human numbers, which is less than 7 human numbers. And this is a data set that I created, which literally just contains all the numbers from 1 to 9,999 written out in English. Okay? And we're going to try and create a language model that can predict the next word in this document. It's just a toy example for this purpose. So in this case, we only have one document, and that one document is the list of numbers. So we can use a text list to create an item list with text in for the training and the validation. In this case, the validation set is the numbers from 8,000 onwards, and the training set is 1 to 8,000. We can combine them together, turn that into a data bunch. So we only have one document, so train 0 is the document. Grab its.text, that's how you grab the contents of a text list, and here are the first 80 characters. It starts with a special token, XXBOS. Anything starting with XX is a special FastAI token. BOS is the beginning of stream token. It basically says this is the start of a document. It's very helpful in NLP to know when documents start so that your models can learn to recognize them. The validation set contains 13,000 tokens, so 13,000 words or punctuation marks, because everything between spaces is a separate token. The batch size that we asked for was 64. And then by default, it uses something called BPTT of 70. BPTT, as we briefly mentioned, stands for backprop through time. That's the sequence length. So for each of our, with each of our kind of 64 document segments, we split it up into lists of 70 words that we look at one time. So what we do is we grab this, for the validation set, entire string of 13,000 tokens, and then we split it into 64 roughly equal-sized sections. Okay? People very, very, very often think I'm saying something different. I did not say they are of length 64. They're not. They're 64 equally sized, roughly, segments. So we take the first 1/64th of the document, piece 1. Second 64th, piece 2. Okay? And then for each of those 1/64th of the document, we then split those into pieces of length 70. So each batch, right, so let's now say, okay, for those 13,000 tokens, how many batches are there? Well, divide by batch size and divide by 70. So there's about 2.9 batches. So there's going to be 3 batches. So let's grab an iterator for our data loader, grab 1, 2, 3 batches, the X and the Y, and let's add up the number of elements, and we get back slightly less than this because there's a little bit left over at the end that doesn't quite make up a full batch. Okay? So this is the kind of stuff you should play around with a lot, lots of shapes and sizes and stuff and iterators. As you can see, it's 95 by 64. I claimed it was going to be 70 by 64. That's because our data loader for language models slightly randomizes BPTT, just to give you a bit more kind of shuffling, get a bit more randomization. It helps the model. And so here you can see the first batch of X. Yeah, remember we've numericalized all these. And here's the first batch of Y. And you'll see here, this is 2, 18, 10, 11, 8. This is 18, 10, 11, 8. So this one is offset by 1 from here, because that's what we want to do with a language model. We want to predict the next word. So after 2 should come 18. And after 18 should come 10. Right? You can grab the vocab for this data set, and a vocab has a textify. So if we call exactly the same, look at the same thing but with textify, that'll just look it up in the vocab. So here you can see XXBOS 8001, whereas in the Y, there's no XXBOS, it's just 8001. So after XXBOS is 8, after 8 is 1000, after 1000 is 1. Okay? And so then after we get 8023 comes X2, and look at this, we're always looking at column 0, so this is the first batch, the first mini batch. Comes 8024, and then X3, all the way up to 8040, right? And so then we can go right back to the start, but look at batch 1, right? So index 1, which is batch number 2, and now we can continue. A slight skip from 8040 to 8046, that's because the last mini batch wasn't quite complete. So what this means is that every mini batch joins up with the previous mini batch, you know. So you can go straight from X1, 0 to X2, 0. It continues 8023, 8024, right? And so if you look at the same thing for colon, comma 1, you'll also see they join up. So all the mini batches join up. So that's the data. We can do show batch to see it. And here is our model, which is doing this, right? So here is, this is just the code copied over, right? So it contains one embedding, i.e. the green arrow, one hidden to hidden brown arrow layer, and one hidden to output, right? So each colored arrow has a single matrix, okay? And so then in the forward pass, we take our first input, X0, and put it through input to hidden, the green arrow, okay? To create our first set of activations, which we call H. Assuming that there is a second word, because like sometimes we might be at the end of a batch where there isn't a second word, assuming there is a second word, then we would add to H the result of X1 put through the green arrow. Remember, that's IH, right? And then we would say, okay, our new H is the result of those two added together, put through our hidden to hidden, orange arrow, and then ReLU, then batch nom. And then for the second word, do exactly the same thing. And then finally, blue arrow, put it through HO. Right? So that's how we convert our diagram to code. So nothing new here at all. So now let's do, okay, and just, you know, so we can chuck that in a learner and we can train it, 46%. Okay. Let's take this code and recognize it's pretty awful. There's a lot of duplicate code. And as coders, when we see duplicate code, what do? We refactor. So we should refactor this into a loop. So here we are. We've refactored it into a loop. So now we're going for each xi and x and doing it in a loop. Guess what? That's an RNN. An RNN is just a refactoring. It's not anything new. This is now an RNN. Okay? And let's refactor our diagram from this to this. This is the same diagram. Okay, but I've just replaced it with my loop. It does the same thing. So here it is. It's got exactly the same in it, literally exactly the same. Just popped a loop here. Before I start, I just have to make sure that I've got some, a bunch of zeros to add to. And of course, I get exactly the same result when I train it. Okay, so next thing that you might think then, and one nice thing about the loop though, is now this will work even if I'm not predicting the 4th word from the previous 3, but for the 9th word from the previous 8. It'll work for any arbitrarily long sequence, which is nice. So let's up the BPTT to 20, since we can now. And let's now say, okay, instead of just predicting the nth word from the previous n minus 1, let's try to predict the 2nd word from the 1st, and the 3rd from the 2nd, and the 4th from the 3rd, and so forth, right? Because previously, like look at our loss function. Previously, we were comparing the result of our model to just the last word of the sequence. Which is very wasteful, because there's a lot of words in the sequence. So let's compare every word in X to every word in Y. So to do that, we need to change this so it's not just one triangle at the end of the loop, but the triangle is inside this, right? So that, in other words, after every loop, predict, loop, predict, loop, predict. So here's this code. It's the same as the previous code, but now I've created an array. And every time I go through the loop, I append HOH to the array. So now for n inputs, I create n outputs. So I'm predicting after every word. Previously I had 46%. Now I have 40%. Why is it worse? Well, it's worse because now, like when I'm trying to predict the 2nd word, I only have 1 word of state to use. Right? So like, and when I'm looking at the 3rd word, I only have 2 words of state to use. So it's a much harder problem for it to solve. So the obvious way to fix this then would, the key problem is here. I go h equals torch.zeros, like I reset my state to 0 every time I start another BPTT sequence. Well, let's not do that. Let's keep h, right? And we can, because remember, each batch connects to the previous batch. It's not shuffled like happens in image classification. So let's take this exact model and replicate it again, but let's move the creation of h into the constructor. Okay, there it is. So it's now self.h. Okay, and so this is now exactly the same code, but at the end, let's put the new h back into self.h. Okay, so it's now doing the same thing, but it's not throwing away that state. And so therefore now, we actually get above the original. We get all the way up to 54% accuracy. So this is what a real RNN looks like. You always want to keep that state, right? But just keep remembering, there's nothing different about an RNN. It's a totally normal, fully connected neural net. Okay, it's just that you've got a loop you refactored. What you could do, though, is at the end of your every loop, you could not just spit out an output, but you could spit it out into another RNN. So you could have an RNN going into an RNN. And that's nice because we've now got more layers of computation. You would expect that to work better. Well, to get there, let's do some more refactoring. So let's take this code and replace it with the equivalent built-in PyTorch code, which is, you just say that. So nn.rnn basically says, do the loop for me. Okay, we've still got the same embedding, we've still got the same output, we've still got the same batch norm, we've still got the same initialization of h, but we just got rid of the loop. So one of the nice things about RNN is that you can now say how many layers you want. So this is the same accuracy, of course. So here I'm going to do it with 2 layers. But here's the thing. When you think about this, right, think about it without the loop. It looks like this, right? It's like, keeps on going. And we've got a BPTT of 20, so there's 20 layers of this. And we know from that visualizing the loss landscapes paper that deep networks have awful, bumpy loss surfaces. So when you start creating long timescales and multiple layers, these things get impossible to train. So there's a few tricks you can do. One thing is you can add skip connections, of course. But what people normally do is instead, they put inside, instead of just adding these together, they actually use a little mini neural net to decide how much of the green arrow to keep and how much of the orange arrow to keep. And when you do that, you get something that's either called a GRU or an LSTM, depending on the details of that little neural net. And we'll learn about the details of those neural nets in part 2. They really don't matter, though, frankly. So we can now say, let's create a GRU instead. So it's just like what we had before, but it'll handle longer sequences and deeper networks. Let's use 2 layers. Boom. And we're up to 75%. Okay. So that's RNNs. And the main reason I wanted to show it to you was to remove the last remaining piece of magic. And this is one of the least magical things we have in deep learning. It's just a refactored, fully connected network. So don't let RNNs ever put you off. And with this approach, where you basically have a sequence of n inputs and a sequence of n outputs, which we've been using for language modeling, you can use that for other tasks, right? For example, the sequence of outputs could be for every word, there could be something saying, is this something that is sensitive and I want to anonymize or not? You know, so like, is this private data or not? Or it could be a part of speech tag for that word. Or it could be something saying, how should that word be formatted? Or whatever. And so these are called sequence labeling tasks. And so you can use this same approach for pretty much any sequence labeling task. Or you can do what I did in the earlier lesson, which is once you finish building your language model, you can throw away the kind of this HO bit and instead put there a standard classification head. And then you can now do NLP classification, which, as you saw earlier, will give you state-of-the-art results even on long documents. So this is a super valuable technique and not remotely magical. Okay, so that's it, right? That's deep learning, or at least, the kind of the practical pieces from my point of view. Having watched this one time, you won't get it all. And I don't recommend that you do watch this so slowly that you get it all the first time, but that you go back and look at it again, take your time, and there'll be bits that you go like, oh, now I see what he's saying, and then you'll be able to implement things you couldn't implement before, and you'll be able to dig in more than before. So definitely go back and do it again. And as you do, write code, not just for yourself, but put it on GitHub, right? It doesn't matter if you think it's great code or not. The fact that you're writing code and sharing it is impressive, and the feedback you'll get if you tell people on the forum, hey, I wrote this code, it's not great, but, it's my first effort. Anything you see jump out at you. People will say oh, that bit was done well. Hey, but did you know for this bit you could have used this library and saved you some time? You'll learn a lot by interacting with your peers. As you've noticed, I've started introducing more and more papers. Now, part 2 will be a lot of papers, and so it's a good time to start reading some of the papers that have been introduced in this section. All the bits that say derivation and theorems and lemmas, you can skip them. I do. They add almost nothing to your understanding of practical deep learning, right? But the bits that say why are we solving this problem and what are the results and so forth are really interesting. And then, try and write English prose. Not English prose that you want to be read by Jeff Hinton and Jan LeCun, but English prose that you want to be read by you as of 6 months ago, right? Because there's a lot more people in the audience of you as of 6 months ago than there is of Jeffrey Hinton and Jan LeCun, right? That's the person you best understand. You know what they need, right? Go and get help and help others. Tell us about your success stories. But perhaps the most important one is get together with others, right? People's learning works much better if you've got that social experience. So start a book club, get involved in meetups, create study groups, and build things, right? And again, it doesn't have to be amazing. Like, just build something that you think the world would be a little bit better if that existed. Or you think it would be kind of slightly delightful to your 2-year-old to see that thing. Or you just want to show it to your brother the next time they come around to see what you're doing. Whatever, right? Like, just finish something, finish something. And then try and make it a bit better. So, for example, something I just saw this afternoon is the Elon Musk tweet generator. Okay. So looking at lots of older tweets, creating a language model from Elon Musk, and then creating new tweets, such as humanity will also have an option to publish on its own journey as an alien civilization. It will always, like all human beings. Mars is no longer possible. AI will definitely be the central intelligence agency. Okay, so this is great. I love this. And I love that Dave Smith wrote and said, these are my first ever commits. Thanks for teaching a finance guy how to build an app in 8 weeks, right? So, I think this is awesome. And I think, like, clearly a lot of care and passion has been put into this project. Will it systematically change the future direction of society as a whole? Maybe not, but maybe Elon will look at this and think like, oh, maybe I need to rethink my method of prose. I don't know. I think it's great. And so, yeah, create something. Put it out there. Put a bit of yourself into it. Or get involved in Fast AI. The Fast AI project, there's a lot going on. You can help with documentation and tests, which might sound boring, but you'd be surprised how incredibly not boring it is to take a piece of code that hasn't been properly documented and research it and understand it and ask Sylvain and I on the forum what's going on, why did you write it this way, we'll send you off to the papers that we were implementing. Writing a test requires deeply understanding that part of the machine learning world to really understand how it's meant to work. So that's always interesting. Stas Beckman has created this nice dev projects index, which you can go onto the forum in the Fast AI dev section and find, actually the dev project section, and find here's some stuff going on that you might want to get involved in. Or maybe there's stuff you want to exist, you could add your own. Create a study group. Dina's already created a study group for San Francisco starting in January. This is how easy it is to create a study group, right? Go on the forum, find your little time zone subcategory, and add a post saying, let's create a study group. Okay? But make sure you, give people a little Google sheet to sign up, some way to actually do something, A great example is Pierre, who's been doing a fantastic job in Brazil of running study groups for the last couple of parts of the course. And, he keeps posting these pictures of people having a good time and learning deep learning together, creating wikis together, creating projects together. Great experience. And then come back for part 2, right, where we'll be looking at all of this interesting stuff, in particular going deep into the FastAI code base to understand how did we build it exactly. We'll actually go through, as we were building it, we created notebooks of here is where we were at